Welcome to the Machine Learning course by Simplilearn. Machine learning is one of the most important skills in today's job market because companies want professionals who can learn from data and make smart predictions. In this course, you will start from the basic and slowly move towards building real machine learning models. You will not only just learn definitions but also understand how algorithms work, why model fails, and how they are used in real projects. By the end of this course, you will have a strong foundation in machine learning that can help you grow into roles like data analyst, machine learning engineer, or even data scientist. So let's talk about the agenda now. First, we will understand what machine learning is and how it is different from traditional programming. Second, we will learn core concepts like train, test, split, overfitting, and how models learn from data. Third, we will understand linear regression and the math behind it in simple way. Next, we'll learn how to evaluate models using matrices like R squared or adjusted R squared. Then we'll prepare the data by handling categorical value and checking model assumptions. After that, we will build and deploy a complete machine learning project using Streamlit. Finally, we'll learn classification using logistic regression and evaluate results using a confusion matrix. So before we move on, here's a quick information for you. If you are serious about building a strong career in AI and machine learning, the Professional Certificate in AI and Machine Learning by Simplilearn in partnership with Purdue University is a great option to consider. This 6-month live online program is designed for working professionals and focuses on real in-demand skills like machine learning, deep learning, generative AI, ChatGPT, LLMs, and agentic AI. You will learn through live interactive classes, work on 15 plus hands-on projects, and use industry tools while getting guidance from industry experts and IBM Masterclass. On completion, you'll also receive a certificate from Simplilearn in collaboration with Purdue University, along with career support to help you move into high-growth AI roles. So hurry up and enroll now, and you can find the course link in the description box below and in the pinned comments. Before we move on, here's a short quiz to test your understanding. What is machine learning mainly used for? Writing fixed rules, learning patterns from data, designing website, or storing files?
So friends, let's start with it. Let me give the machine learning. Even before starting machine learning, what we need to understand is what is ideally the need of machine learning. So friends, we all have heard that data is the new oil today. So when I say data is the new oil, what do we exactly mean? If I come back to my days of doing my engineering somewhere around the year uh, 2005 to 2009, where I passed in 2009 when I was doing my bachelor's of engineering. So I would say that during our time when I started, I was using the 1.4 MB floppy disk. So that was in itself a big achievement. Then a 4 MB floppy disk came into picture. Then during our time only a compact disk came, which could have saved data up to 100 MB. So we were very happy. During our time only, a special CD came which is called as data CD, which can save data up to 700 MB, specifically for saving data. Not for so basically saving movies or anything, that was good. Then came the DVD. Then during our time only came the Blu-ray, because if someone is a millennial, maybe he might not be knowing it. So Blu-ray CD came, and then during I actually experienced this. Pen drive came, very small size. And then we started having pen drives of bigger size and further bigger size. And then it all is going fast and fast from here only. Earlier, computers were as big as a room. Now we have powerful computers with GPU all into a laptop. So everyone's standard of living, or I would say the minimum things that we need to survive, that baseline has increased. There was a time where in every home there used to be only one working person feeding the whole family. Today, many people have to work. That has also changed. Plus, in every home, there was one landline telephone. Mobile in itself was a big thing. Today, every person has a mobile phone. So, that has become a need. No one can survive without a phone. That's a fact. What I want to say is the baseline standard of living, irrespective of whether you are poor, middle class, or high class, the baseline standard of living has increased. We all have in our house a flat TV. Gone are those days where you had TVs which have a box behind which is projecting. That's gone. We all have flat TV. Everyone has a mobile phone, right? And I think the cost of everyone's mobile phone is somewhere between, on an average, 7,000 to 20,000 on an average. And every person in the family has it. Even if you are poor, at least there will be one bike in your house. And if you are rich, then you have a bike and a car, right? So these all things have become bare minimum now. So basically, we are progressing, right? That's the overall story. Now, the thing which I wanted to say is we were talking about data. So, data is what we call today as the new oil. In fact, Simplilearn, somewhere in the year just before COVID, the advertisement used to come whenever I used to open YouTube. Have you heard data is the new oil and blah 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 blah? That advertise used to continue after that. And then after that, I used to skip that ad. But data is the new oil. That was one of the very important thing. So data is the new oil doesn't really mean that data is the oil, but data is as precious as oil. I remember when I was small, right? We used to live in a small house because my father actually came from zero to infinity. So what I wanted to say over here is uh, so it was a building something like this, where in the center we had a staircase. There were four floors in the building. So four houses on the ground floor. Here, four houses here. First floor, four houses. Second floor, four houses. Third floor, four houses. Fourth floor, four houses. And the last floor. That was how it was. And I remember we used to stay here, right? So people used to come to take surveys with a pad having papers and a pen in their hand. They used to ask questions like, which shampoo do you use? Which soap do you use? What is your average family income? Do you have a bike? Do you have a car? How many people are working in your family? And such questions which are usually taken in a survey. What do you like? And then after that, if you give that survey, they used to take around 10 minutes to sometimes 15 minutes of the time. If you take that survey, they used to give a free complimentary bottle of their product. Could be a shampoo or could be a small new taster of a new milk product which they are launching or anything. Many people used to come like that. But what were we do? But what were all of them doing? Data collection. I don't think so. Today, people like this exist anymore because all the data that we are generating is coming from here, right? Am I correct? Earlier, the data was collected for entire family, that too after so many efforts. Today, every person is generating data. Our session is getting recorded. We are also generating data, right? So if I am going on to the Instagram, right? So the kind of reels which will be recommended to me will also be purely based on my watch history, etc. Or if I go on to my YouTube, again the kind of reels which are recommended to me will be on the type of my watch history. Oh, what happened over here? That's sad. So essentially, because they have my data, they have studied that. Right? That is sad.
This baby elephant lost.
How is that possible? So, what I wanted to say is every one of us is generating data. And that is exactly where machine learning, right? So, I say machine learning is a powerful concept as well as framework for making the best out of it. So, today we say that we are living in what we called as the age of information or the age of data. Next thing over here, let me ask you a question. Who is the most advanced and intelligent on the planet at the moment? Who is the most advanced and intelligent on the planet at the moment? What will be your question? What will be your answer? So, can I tell to my machine, if machine is smart, then let's consider TV. Does your TV automatically call you and say that, hey, your favorite program, Tarak Mehta Ka Ulta Chashma, is coming in 15 minutes. Please come and watch it. Does it say? Then how is that intelligent? How is it the most intelligent, most advanced? Elon Musk is just one person. So again, when you say Elon Musk, I assume that it's going to be humans. A ChatGPT though can't do anything. It can just generate text. Just because of that, we can't really call it smart. Someone which is just generating the text. For example, if I go to ChatGPT and say that book me my flight tickets for tomorrow from Mumbai to Bangalore for 11 a.m. Can ChatGPT do that for me? Can it do? Can it book my flight tickets? If I give it a budget, tell me, can it do or it cannot do? Because someone said that it is very intelligent. It has information, but it can't perform actions. We can say that's exactly where agentic AI is coming into picture. But again, it is not the most smart as of now, at least. That's what one thing is for sure. So if you say that is what is called as human, then obviously the question comes to our mind is why do we really need machine learning? this is what is there, then why do we really need machine learning? And the answer is you cannot, although you say humans are very smart, but humans cannot, yes, very nicely said Sandesh. Humans cannot make decision at a scale. For example, if I say I have a data set of 1 lakh rows, and if I say study these 1 lakh rows and take a decision, you cannot do that. You cannot remember so many things. That is exactly where machines can help. So why do we need machine learning? We need it to make data-driven decisions at a scale. That's something which is very, very important. So, as a human, whenever we have to make a decision, we use what is called as power of reasoning or intuition. So let me ask you a very simple question. Since you said humans are most intelligent, you have a friend of yours who you know since past 10 years. He comes to you and asks you, will you lend me 10,000 rupees? What is your answer? A friend of you comes to you and asks for this. What will be your answer? You know him since past 10 years. Will you lend him or not? It's a human decision. You don't need a machine for that. I actually did the same thing, but I never got it back. Yes, I never got it back. So that person was in my college group only, 2005 to 2009. He took the money and he never returned me. Working now as a manager or some team leader in some company, but he did not return me. And now he drinks a lot and he has totally changed. He has divorced as well. So people change over time, is what I wanted to say. So I was saying people change over the time. Same, right? Yes. So we really can't actually rely on this. And more than whether he returns or not, I'm more interested in understanding how we took the decision. How did you all take the decision? So I'm sure you might have looked at the past history with this friend, in the sense you may be like, let's say, in the past, how many years? 10 years. You interacted with your friends. Let's say in the past 10 years, you interacted with your friend total 100 times. So basically, you met your friend 100 times. So when he comes and asks you, can you lend me 10,000 rupees? Let's say all of a sudden, I'm your friend, I come to you and I say that, Shekhar, please give me 10,000 rupees, I am in need. So will Shekhar remember all the 100 interactions which he had with me instantly when I ask him this question? Is it possible for our brain to remember everything? Impossible, right? Yes, maybe out of this 10, Shekhar, or in our case, human, may be able to remember only the most prominent, or we can even say the most recent 10 interactions. So what will Shekhar say? That out of 10 times, my friend Darshan was 7 times good with me. 3 times he was not that helpful. But overall, Darshan is a good guy. So I will lend him money. And that's how Shekhar takes a decision. But imagine all of this data, if it is saved in a machine, let's assume all of these 100 interactions are saved in a Microsoft Excel file where interaction and then it was a good interaction or not. Interaction, was that good or not? It was good, not good, dot 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 dot. Now when machine has to take a decision, machine is like, okay, Darshan, this guy was 79 times good with you and 21 times he was not that good with you. So according to me, you take a decision, yes. And that is how machine also takes a decision. So both of your decisions are correct. But whose decision in this case is more reliable? Whose decision is more reliable? Both of you are correct. That's good. Machine. Yes. Machine, at least for now, we understand that the decision of machine is more reliable. But there is a problem. Is this machine learning? No, this is not machine learning. So here, I think this decision which is there, it is just easily possible by applying a group by on the Excel file or maybe filtering out the yes and the filtering out of no. This has been something since a long time since Microsoft Excel came. Is this machine learning? No. Plus here, let's say instead of 100, if you had 50,000 interactions, then every time for taking a decision, you have to refer this Excel file, find out how many positive, how many negative, and then take a decision. That's not machine learning. Mm. This is like data analysis, EDA, what you were doing. So, obviously, we still don't understand what is machine learning. Well, let me ask you. If you go to a doctor, then, so let's say for a person to become a doctor in 5 years of his time, he has to study so many books. For a person to become a doctor, let's say he has to study so many books. So now, when Shekhar is not feeling well, why Shekhar? Darshan, I'm not feeling well. So let me talk about me only. When Darshan is not feeling well, he goes to the doctor who has actually studied this, right? So I go to my family doctor and I say that, hey, this is the problem. What should I do? So if I remember the Microsoft Excel file wala example where we had to look into this and find out how many good and how many bad were there, and we were taking a decision. So when I go and tell to the doctor that I am not well, does this guy as well open each and every book or whichever book is relevant and then says that, okay, Darshan, you are having throat, and for that I think you should have this medicine? Does it happen like that? No. So what exactly, how does he take a decision? How does he take a decision then? What do you think? How a human mind is taking decision? Experience. So you mean to say books are not important? The knowledge that is studied? Knowledge and experience. Processing the data which is already there in the brain. Memory. Awesome. That is exactly where we are coming. So we can actually say, that if I find out the weight of all these books, if it is coming to around 250 kilogram, the doctor has studied 250 kilograms of data. I say the doctor has studied 250 kilograms of the data. But all of this data is saved into his brain, which is something like this, right? That's how a human brain is. Can someone tell me what is the weight of a human brain? What's the weight of a human brain? Google it and quickly tell me. अरे कुछ भी 4.5 kg. Insane. It's around 1.3 to 1.4 kg. That's it. That's perfectly said. So that means 250 kilogram of data is saved into 1.3 kilogram of data or brain. And whenever I go to the doctor is taking the decision on this 1.3 kilogram, which has knowledge of his books, right? As you said, knowledge of his books, plus, as you said, his experience, plus, as you said, his logic, and many other things. Now, that is what we call as machine learning for now. For now, because the doctor didn't save all this data. He learned the information from this data. We all know there is a difference between data and information. He learned the information and it is being used for taking a decision. It is being used for taking a decision. This is something very, very important. Very, very important. So when you say machine learning is creating a machine learning model, the model is not storing the data. I am repeating it. It is not storing the data, but it is storing the feature learning. That's something very important. So you will see usually the size of a machine learning model, even if you ask it to make it, even if you say that, hey, this is the 14 GB of data, could be a Microsoft Excel file. I want you to study that. The size of a machine learning model is between few KBs to maximum, the highest around 700 MB. So you can understand this is how it is going to take a decision. So it is not referring to the file. So that also means just like when a doctor has to take a decision, when I go to him, what kind of disease am I having and what he should recommend me, I can comfortably say that this doctor does not require this. He does not require this. He can take decision only on the basis of brain. In the same way, when you have to now predict whether your friend will lend money to you or not based on the past data, you don't require the past data. You only require what is called as a model. Are you all able to understand? So it's all about learning the features. Right? Yes. So now I am going ahead. So now I'm very soon, maybe in another 5 minutes, I will be starting with actually what is machine learning. So I'm going to Google. Now we need to spend at least at least 30 minutes on this. At least this single image. Yes, you heard it right. 30 minutes on this single image. But why is this? Consider a very simple problem. What used to happen so far? So we will talk with respect to traditional programming. So let us say you have to create a very simple application to perform addition of two numbers. Then you had to write a program. Who will write a program? A software developer will end up writing a program. Let's say you want to perform the addition of two numbers. Then write a program add.py. And then that program, when executed on a computer, you might be getting an executable file. And then you ask the program, because you are written a program that can perform the addition, you ask it, 2 plus 3. So this program takes this, performs 2 plus 3s, and gives the output as 5. Or maybe if you ask it, what is 1.1 plus 2.2? This will end up answering 3.3. So what I want to tell you in this scenario, the output is deterministic in nature. What I mean by deterministic is 2 plus 3 can be this. It's almost fine, huh? So can I say 2 plus 3 is equal to 5.001? Can I say 2 plus 3 is equal to 4.9999999? No. So you mean to say the answer has to be 5 and only 5. It has to be deterministic. Can I say 1.1 plus 2.2 can be 3.30000001? Will you agree to this answer? That's exactly what I am saying. So let's say, consider a very traditional application, not a software program like addition.py, but let's say you created a bank website. So let's say you created a perfect website for a bank like HDFC. So as a customer, the customer said that I have 1 lakh rupees to invest, and I'm gonna invest it for 3 years. The rate of interest which is being offered is, let's say, 5.12%. So after 3 years, I am entitled to get 1.4 lakh rupees. As a customer, will you agree if the bank is paying you instead of 1.4 lakh rupees, 1 lakh 39,992 rupees? Instead of 1.40, the bank is paying this. So it's around 8 rupees less. Will you agree? No, you'll be like, no. As per these calculations, I am entitled to get this much. I want this much only. It's not coming out to that. So essentially, the output in the earlier programs was deterministic. But machine learning is different. And how is it different? That's exactly what we are going to understand now. Did you all understand what is traditional programming with the help of the addition and the bank example? Then I can go ahead to define machine learning then. Everyone is clear with what is traditional programming? So let's say, consider I am your Python teacher and I completely taught you Python. And I say that, guys, tomorrow is your exam on Python. So study and come. And then you come to me and say, syllabus and all things are very high. Can you help us with some sample questions? And because I have been taking this subject since a very long time, I do have a lot of questions already ready with me. Let's assume I have 80 questions. And the best part is, I also have their sample answers. What I say is, since you come requesting for some sample questions, I am like, okay, no problem. Tomorrow I have to take their exam. Out of these 100 questions, let me think of giving them around 80 questions to study. And these 20 questions, as a teacher, I will keep it separately so that I can use it for asking them in the examinations. So now I give you these 80 questions and also their 80 answers. But this is what is not shared with you. I'm not giving you this. Only this and this is shared. So what you do, you go home and then you study. And what do you exactly mean by study? You understand the relationship between this question, this answer, this question, this answer, this question, this answer. so on and so forth. You understand the relationship between every question and every answer. And where is it saved? It is saved into your brain. This entire information is saved into your brain. So what I do is tomorrow when you come for the examination, these are the questions which you have never seen. As a teacher, I give these questions to you in the examination. Because you had studied this, you answer these 20 questions. Let us assume that these are the 20 answers that you gave. So I can say these are your predictions and these are your actual answers. As a teacher, I will compare the 20 answers which are actual and the 20 ones that you predicted. I am going to compare this and calculate how much good you are on this data. And that's exactly what I call as the accuracy on the test. And that's how I evaluate you. I could have also done one more thing. Because you studied these 80 questions and 80 answers, I might say that, okay, let me ask them the same 80 questions. So obviously you are expected to give 80 answers. So whatever you studied, the same thing I asked, and these are the predictions, and these are the answers. Again, I can compare this to because these are your predictions. These are the actual or the model answers. I can compare and find out what we call as training accuracy. Are you understanding this figure, what we did in this so far? This is kind of very, very important for machine learning, right? Yes. So I repeat, I had 100 questions. I divided into 80-20, where 80 questions and answers I ask you to study. And later on, when your study is over and it's saved into the brain, I ask you this 20 questions which you didn't study, and you answered on those 20. These 20 I compare with the actual ones, and I find out how good you are on unseen, something which you never saw. And then I ask you the same 80 questions. You give that answers, and I see the actual ones. I compare them and I calculate your training accuracy. So in machine learning also we end up doing something same. So here this brain is nothing but called as a model. Now see what I mean to say is uh, in uh, whenever you talk about these predictions, you don't actually mug up the data. You are storing the features. How many of you, when I say that go and understand the relationship, when I say go and understand the relationship in between the question and the answer, how many of you literally ratta mug up the things? How many of you mug up the things? Question, answer, question, answer, question, answer. Do you do that? I'm exactly talking about like the Chatur of Three Idiots. If you ask him what is machine, how did he answer? Do you learn it that way so that tomorrow when I ask you what is machine and you start speaking machine says this, you don't. In fact, if I just randomly go and go on to, let's say, even if I ask you to, let's say, even if I ask you to study these two paragraphs. Let's say I give you 10 minutes of time and I say that study this, and then I'll be asking you to rewrite it on a plain piece of paper. Do you think you will be able to actually write down each and every word as it is? I'm sure the answer is no. But if I say, would you be able to reproduce the same concept without writing once you study? The answer would be yes, because you will be writing those all things in your own words. And that is exactly what is happening over here. When you are understanding the relationship between the question and the answer, and you say it is saved into your brain is not actually mugging up the data, but it is saving the pattern. Now, here, coming on to this figure, what I want to say is now this time the 80 questions and the 80 answers that you study, this is the input. And in return, what you get is nothing but a program or the brain or the model. So if you now remember, earlier the program was written by the software developer, but now here the program is actually written down by the computer. And it's not actually a program, it's a model. So earlier you see data and program was on the left side and results were on the right hand side. But now you have data and results on the left hand side and the program on the right hand side. So you don't need a software developer to write the program, but rather here your machine is the one who is actually going to know or who is actually going to do what you call as the feature learning. And you get this. But you cannot really trust the output of a machine. The machine may be right, the machine may be wrong. The machine says, yes, Darshan, I am done studying. But how do you trust that machine? The only way you can trust that machine is by asking it questions. Tomorrow you come and say, when I ask you to study these questions, tomorrow, let's say Raj comes to me and says that, yes, Darshan, I am done with my study. Huh? Now, Raj says that I'm done with my study, everything is saved in my brain. Should I trust him? He might not have studied. He might have studied. How do I trust him? How do I really know whether he has studied or not? Unless and until I evaluate it. That's exactly how, right from junior KG till whatever we are today, we have come, right? So junior to senior, senior to first standard, second standard, so on, so forth, 10th standard, so on, so forth, 12th standard, then medical engineering. That's how every time we have given an exam, the teacher is not like, okay, Raj is a very good boy, so Raj is going from first standard to second standard directly. No. Irrespective of whether it's good or bad, he has to go through Agni Pariksha. Examination is important. He might say he has studied, but what is the guarantee that he studied? I will take his exam. If he passes in the exam, then I allow him to go to the next standard. So, in the same way, the computer or the machine may say that, yes, I have understood the relationship between the 80 questions and the 80 answers. But that could be wrong understanding as well. So, unless and until you validate it, that's going to be a challenge. Always, always remember it. And that's why here as well, we are doing the same thing in machine learning. So, machine learning is about this single figure that you see on the screen. You give some data to the machine to study. It understands the relationship. Once the relationship is understood, you ask it something which it has not studied and it will predict. This prediction you compare with the actual, and based on that, you calculate the accuracy and confirm how good or bad is the model. Right? So that is essential what is machine learning. But there are some challenges as well over here, which I have to now discuss. Technically, they are called as overfitting and underfitting. So when you say that, okay, Raj has studied well, how do you actually quantify whether he really studied well or not? So I was saying over here, now we are good to get into this understanding. So, I remember we were talking about overfitting and underfitting. So what did we do over here? See, here we asked the I asked you to study these 80 questions and 80 answers. And then after the study is over, you said the data is saved in my brain. Then I confirmed whether you are really understanding the things or not by asking you this exam questions. You answered for this exam. I compared it and I found out the test accuracy. In the same way, I said that let me ask the same questions that you studied. You answered it again and I compared it and I calculated what we call as the train accuracy after this. So now the question is, now that we have calculated it, the question is, what is a good model? A good machine learning model is the one which satisfies the below two conditions. Test accuracy must be greater than equal to 80%. And the second one is the train accuracy minus test accuracy difference must be less than equal to 5%. Then we say it's a good model. Now, this is something which is very, very important to be noted by everyone. If the difference in between the train and test accuracy is less than 5% and the test accuracy is at least 80%, then you call it as a good machine learning model. Here we say, let's consider a very simple scenario. I'll keep it open and let's say we have the train accuracy, we have the test accuracy, and this is the decision. Consider the first scenario. Let's say, listen to this very carefully. Let's say over here, the train accuracy is 100%. The test accuracy is 98%. Is that a good model or not? What did I say? The train accuracy minus test accuracy difference must be less than 5%. It is. Test accuracy, is it at least greater than 80%? Yes. Then we say it's a good model. So I say yes, it's a good model. Consider second scenario. Let's say over here you have 98% accuracy and over here you have 97% accuracy. Is it a good model? This must be minimum 80% and the difference must be less than 5%. So tell me, is it a good model? So let me actually talk about it as a good model. Let me take the third decision. Let's say you are having a 92% accuracy over here and you have 87% accuracy over here. Is it a good model? The test accuracy must be minimum 80%, that is there, and difference must be less than equal to 5%. So 92 and 87, this is less than equal to 5%. Yes. So yes, we call it as a good model. Consider the fourth scenario. Imagine here you have 92 and here you have 85. Is it a good model? Because even though the condition 1 is satisfied, but the condition 2, which is the difference less than 5%, is not satisfied. In fact, remember, we call this scenario as what is called technically as overfitting. I'll talk about it. Consider one more scenario. I'm going to take one more example of this. Consider one more example. Let's say this is 90 and this is 80. This is again not a good model. In fact, technically, we call this scenario as overfitting. What is overfitting? Overfitting, nothing but what you call as this. This is a perfect scenario of what we call as overfitting. This is the perfect scenario of overfitting. Why? Because he mugged up the data. He did not bother to understand the meaning of the data. And because of which he was able to confidently answer wrongly. That's very important point. Huh? Confidently answer wrongly. That's an important thing. Confidently answer wrongly. Now, basically, when a model tries to understand the relationship by mugging up the data, and what you see is it's doing very nicely on what it studied. But when you change the question, it is not able to do nicely. Then we say the scenario is overfitting. Like, for example, let's think about it from the human perspective. If you had a question like, what are the features of Python? And the respective answer for this. This is the question that you study. What are the features of Python? And you have the answer to that. But in the unseen part, you have that question. Explain the features of Python. And I ask you to answer it. What will you say? Will you come to me and say, Darshan, this is an out of syllabus question. This is something which I never saw. Or your brain will be able to understand, array, it's quite logical. It is nothing but the same question asked in a different way. Will your brain be able to figure out that this is more or less the same question? If you are able to do that, then you are not the Chatur of three idiots. But Chatur was not able to do that. By changing one or two words, he actually mugged up the data. So what happened is, if you ask Chatur to reiterate whatever he has learned in the speech, he did that very nicely. So if Rancho would have not changed his speech, then Chatur's output would have been awesome. Essentially, the actual and predicted would have been the same. And on the unseen also, he would have been good. But because he mugged up the data, he did not understand when the data is changed and he did not understand the generalization. And that is what is called as an overfitting. So when I say overfitting, always remember the Chatur of three idiots, or you can remember it this way. If he's very good on training, very good, but not good on testing. So you can also consider that, imagine, there is a student I'm training a student in private on his maths subject. He's a 12th standard student. I'm training him in private. So before his board exams, I took many prelim exams for the student. And I was happy to say that he was getting 96%, 97%, 98% in many exams which I took. 99%, 95%. So overall, I could see that he was always getting above 93%. And so I was very happy that he is ready for his board exam. And when the board exam actually he ended up giving, he could only get 83%. That's where I realized that this guy was mugging up the data. So he is very good on what I teach him. But little change. And he was not able to generalize well. And this is exactly what is called as overfitting. This is exactly what is called as overfitting. So if a model is doing good on training but not able to perform equally good on testing, difference of 5% is acceptable. But if it's not able to do equally good on testing, then we say that it is overfitting. Just like this board exam student as well. But let's consider I have a student, Rohan. So what I tell to Rohan that, hey Rohan, tomorrow is your Python exam. Study and come these 80 questions. Now Rohan is a badmash. Rohan is a badmash. I asked him to study 80 questions. He did not study. He should have invested at least 6 hours of time for studying. But Rohan is alsi, badmash. He did not study. He hardly studied it for 30 minutes. So, do you think in 30 minutes he will be able to understand this, which ideally requires 6 hours? If he is a prodigy child, then it's a different story. But a normal person, will he be able to understand? No, right? He won't be able to understand. He didn't invest so much time. And therefore, now what will happen if I give him the test paper? Will he be able to perform good on the unseen data? Tell me one thing. Will Rohan be able to perform good on the seen data? No. That's called as underfitting. That's called as underfitting. So when Rohan has not studied only, how do you expect him to perform good? So imagine this is 70 and this is 68. We call this scenario as underfitting. Why? Because this is not an industry accepted model. Industry accepted model says that test accuracy must be at least 80%. It's not there. Difference must be less than 5%. This is there, but both are not satisfied. So it's not a good model. So it can be either overfitting or underfitting. What is this? This is underfitting. Why? Because he didn't get a good accuracy on training, neither on testing. So the model must have that good at least. So this is how you end up taking a decision. So we don't want to create a model which will overfit or which will underfit. And that's exactly what are we looking for. So in this way, there can be multiple scenarios. We can discuss it later. For now, this much is more than sufficient. So overfitting versus underfitting. Now, now let's understand. You only have to give me your inputs. Consider. I'll take an example. I want to buy a house. The price of a house is going to depend on what all factors. So let's say I am specifically looking for a 2 BHK in Marthali area in Bangalore, where we know that the price of the house ranges between 1 CR to, let's say, 1.3 CR. Let's assume. So the price of the house depends on what all factors. So number one factor I can say that it depends on how much is the area of the house in square feet. It depends on which floor are you buying the house, because the more higher you buy, you got to pay for the floor size. It also depends on who is the builder who is building the property. It also depend. It also depends on over here whether the society has a swimming pool or not. See, I'm not saying that whether it has amenities or not. I'm being very specific. Swimming pool hai ki nahi hai? Yes or not. Whether the society has a gym or not. What is the distance to the nearest shopping mall? What is the distance to the nearest school? What is the distance to the nearest vegetable market? What is the distance to the nearest bus stop? What is the distance to the nearest metro? What is the how many number of bedrooms are there in the house? Then is the society having a garden or not? Is there a temple in the society or not? And many such other factors. In the same way, I never said amenities. I said swimming pool. I said gym. I never said amenities and concluded. Be as much concrete, as much atomic as possible. Help me out. I have to buy a mobile phone. So the price of the mobile phone depends on what all factors? Brand. Whether you're buying Apple, Samsung, Oppo, Vivo, Xiaomi, etc. Depends on the RAM. It depends on the camera megapixel. Yes. It depends on, okay, color also. Yeah, color also matters. Nothing wrong in that. It also depends on, yes, whether it is 5G or 4G. It also depends on, OS means brand, it will get covered. Now, okay, I can write that, but that makes sense. It depends on processor. As you all said, internal memory. Shweta, I have the right to scold you now. The price of the phone depends on the price of the phone. Huh? Are you trying to say the price of a phone depends on the price of the phone? I know, I caught you. Subconsciously, you said that. So, now, next is yes, display type. Definitely, display type. And, and screen size, yes, that's again important factor. Screen size, yes, waterproof, dustproof, that also I agree, etc., etc. Let's go on to the next one, the third one. There is a reason why am I talking about this. Yes, speaker mic quality, that's also correct, Shanu. Let's say in one hand I have Apple. This all is machine learning, huh? In one hand I have Apple, and in another hand I have orange. How do you identify that this is an apple and this is an orange? Color. Okay, that's a good one. Noted. And shape, taste. Okay, don't say features this time. Taste. Smell. Yes, that's very important. Smell. We can also look at texture, na? If you are a blind person, you can actually feel it. How is it to touch? Feel type. Okay. And if I get into little technical stuff, then you can look into the mineral content, vitamin C content, etc., etc., etc. things. Hard, soft, yes. Essence, that's also important. Okay. One more example, then I'll conclude this topic and we'll go on a break. There is a reason why I'm discussing this. It's not for time pass. There is a reason for that. Because we have to start with types of machine learning once we come back. And that's exactly kind of I'm creating a background for that topic. I want to talk about the very standard and the famous data set of machine learning, which is called as iris data set. So if you look over here, now if you see carefully, do you see all these three flowers look more or less the same and it is difficult to differentiate that these are three different flowers, right? Yes. So these three belong to the same species iris, but they are three different flowers, Setosa, versicolor, and virginica. So what they had done is they had the data set, the original data set consists of total 150 rows. What they did is for every flower, they had taken 50 setos of flowers, 50 versicolor flowers, and 50 virginica. Here for demonstration, they have shown only two, but there are total 50. So they have taken total of 150 flowers, total of 150 flowers. And what did they do is they measured the length of the petal, width of the petal for each of the 150 flowers. They measured the length of the sepal, width of the sepal. As you can see, sepal length, sepal width, petal width. And what is that flower? In this way, you have total 150 values. So here in this, I can actually say iris data set, which is setosa or versicolor or virginica, that depends on sepal length, sepal width, petal length, and petal width. So here, what I want to tell you is whatever you are trying to predict in machine learning, you call it as dependent variable. Whatever variables you use for predicting it are called as independent variables. Technically, independent variables are very popularly indicated by X and dependent variables are indicated by Y in machine learning. Though it's not mandatory, but you will see almost 100% of the people using the same conventions. You are also requested to use the same. It's not mandatory, but you are requested to use the same. So here, if you say, I can say that if I'm considering the price of the house as the dependent variable, then this brand can be considered as first independent variable, RAM as second, this as third, this has fourth, this as fifth, this has sixth, this has seventh, this has eighth, this has ninth, this has 10th. Now coming up this. So I asked you to study 80 questions. These questions are now called as independent variable and answer is called as dependent. So this part which I asked you to study is called as the train part. This part which I kept hidden from you is called as test part. So because of this is X train, X test, oh sorry, Y train. This is X test, this is Y test. When you give to this model, what are you giving? You are giving this model to predict on X train. The model predicts Y prediction on train. So you will see I'll be using the same conventions in the code. So we ask the model to study the relationship between X train, Y train, and the model creates a, it will study the relationship. And then when you ask it questions on X train, the output is what we save into Y prediction train. And you compare this. Similarly, to the model, when I ask purely unseen data X test, the model is going to predict that, and I'll be saving it into the name Y predicted test. Comparing this to, I calculate the test accuracy. And then these two are compared to figure out whether the model is doing good or not. So if I come back to this example, you can consider over here, this is independent variable. This is the dependent variable. So overall, we call this as X, this as Y. Specifically, I can say X1, X2, X3, X4. So if I have to uh, uh, explain this problem, then I can say we have the same thing now. So if you remember, we had total 150 row number 1 to row number 150. So row number 1 to 120, which is nothing but 80%, and this is the 20%. That's the test. That's the train. Sepal length, sepal width, petal length, petal width. Versus this model understands the relationship between this 120 rows, which is x1, x2, x3, x4 versus y. Just like here I said, the model understands, okay, if these are the things, then it is setosa. If these are the things, then it is setosa. If these are the things, then it is versicolor. If these are the things, then it is versicolor, and so on. It understands this, and ultimately, on the basis of this, it creates what is called as a model. Model is created, and then to this model, as we discussed, when you ask it to predict on X train, it predicts this. When you ask it to predict on X test, it predicts this. And then, as we decided, using this, you get the train accuracy. Comparing this, you get the test accuracy. Technically, this is X train, Y train, X test, Y test, Y prediction train, Y prediction test. And that's how you actually end up creating a machine learning model quickly. So if I have to just take it here, that's how we have it. I'll do one thing. The case study will be iris dataset modeling. Let's do the necessary imports. I import the NumPy, Pandas, Matplotlib, Seaborn. I also import warnings. Then I say getting the iris dataset. This is the dataset. Then I say I divided the data into X and Y. So X is expected to be all of this. That's what I said from the data frame. Everything except the species column goes into X. And similarly, Y is only the species column. So this is Y. Then I say doing the division. So you can see over here, we add this data, we divided into X and Y. Then further into this, because I said you can see X train का shape 120, 4. Y train का shape 120, 1 row, 1 column only. X test का shape, which is this 30, 4. And Y test का shape 30, because I divided it into 80, 20, 20% in the test part. So 80, 20. Okay. I'm creating a machine learning model. So I'm creating a model of logistic regression. I'm asking the model to fit. Fit means study. Understand the relationship between X train, Y train. That's exactly what I used to say. Understand the relationship between X train, Y train. So I'm asking it to do that. And it says I am done understanding. Then I say, okay, then let us predict on the training and testing data. So I say my Y prediction on the train is model predicting on X train. Similarly, model. So I got the model to predict on what it studied into this, what it has never seen, but similar to what it studied into this. Then I will like to calculate the accuracy. I'm calculating the accuracy of the training, and I'm calculating the accuracy of the testing. You see, train accuracy and test accuracy. And then I'm printing it 97% accuracy on the train, 96% accuracy on the test, and this is the end of this notebook. Essentially, in any machine learning model, these will be the steps. I will once again go through it. First, we did the necessary imports. We had been doing it earlier as well. That's not new. The data set I loaded, it's already available in Seaborn, so I use that and the data is loaded. Okay, then next thing is we have to divide the data. This is my independent variable. This is my dependent variable. So ideally, how many rows are there in the data set? I can actually say df dot shape 150 comma 5, 150 rows and 5 columns. So this 150 comma 5 is taken and then you divide it. So obviously I said divide it in such a way that it has to be 20% data in the testing. So 150 rows are there. That means 120 will be over here, 30 will be over here. So that's what I did over here, and I get four parts: X train, X test, and Y train, Y test. Then then I say I'll create a logistic regression model. So I imported the logistic regression model and I said, logistic regression, please go and understand the relationship between X train, Y train. So that's exactly what is happening. Once it has understood, I say, logistic regression, go and predict on X train, predict on this part, and I get the prediction here. We call it as Y prediction train, this one. Logistic regression, go and predict on X test, which is this part. Saved over here. I call it as Y predicted test. Then I say calculate the accuracy by comparing Y train and Y predicted train. So Y train is this part, Y predicted train is this part. Compare this and calculate accuracy. Similarly, I said calculate the accuracy by comparing Y test and Y predicted test. This and this. So I get the train accuracy, I get the test accuracy. That's what I printed. Train accuracy printed, test accuracy printed. 97.5% on train and 96% on test. Done creation of the machine learning model. Let me come to you and ask you. Overall, did you understand what I did? Overall only. I don't want in-depth understanding. Mota mota, whatever I taught you, the same thing is required in the code, right? This is one of the very important thing, very important thing, right? So you understand that whatever theory I am teaching you is not just a theory, but it's actually code only. You'll not understand code. This is what we have. And that's where I close this and we will go on a break. So just once again to confirm, I hope you are convinced with the overall flow. Okay, now friends, we understand what is machine learning. We have also seen a very raw implementation on Iris dataset. Now, let's talk about machine learning. So, friends, machine learning is broadly divided into two types. First is supervised learning. Second is unsupervised learning. And the third is reinforcement learning. Now, supervised learning is a learning where a supervisor is available. Like right now, if you are learning something from me, I can call it as a supervised learning. Why? Because I'm the supervisor, I'm available. So if you have any question, ask me. Here only I will clarify it. That's called as a supervised learning. A supervisor is there. What is unsupervised? Where a supervisor is not there. Example, you are watching some video on YouTube. So let's say if you go to YouTube and here you are saying that I want to do machine learning on Iris dataset. And let's say you're randomly picking up this data. So the author over here, let's say by the channel Hackers Realm, he says he has analyzed the Iris dataset with various this. And he started explaining. You watch it, you are over here, he read the data, did some analysis. Then after that, this is the correlation matrix. Then he is getting into dividing the data, extend, extension, all these things done. And you have this. Now, let's say at some point of time, you are having a question. But is there anyone to help you out on this? You have a question, why is this warning coming? You wanted to ask. In my live session, you can ask me that why are you getting this warning, how to get rid of this. But on a YouTube video, what can you maximum do? Maybe you put in some comment below and wait for this person to answer. And you wait for this person to answer. So it is an unsupervised learning. You don't get the live support. So technically, we say supervised learning is a type of learning where you have labeled the data. Labeled means independent and dependent variable both are available. And unsupervised learning is a type of learning where you have unlabeled data, which means only and only X is given, and you need to find or derive Y. You need to find or you need to derive Y. That is exactly what we call as unsupervised learning. What is supervised learning? Where you have access to the supervised data. So how do you actually do this? Supervised learning is further divided into two parts. The first one is a regression problem. The next one is a classification problem. So regression is the one where the dependent variable is continuous in nature, and classification is the one where the dependent variable is categorical in nature. Regression is the one where it is continuous, and classification is the one where it is categorical in nature. So over here, example, if you come back here, see example 1 and 2. What you are predicting is the price of the house. It is continuous because the price of the house, as I said, can be anywhere between 1 to 1.3 CR. Any value it can take. Or price of the phone also. So I may buy it as 20,000. Someone buys it at 20,300. Someone else buys it at 20,145. So there are various possibilities over here. So now, similarly, the other two, right? So example 1 and 2 is where you're predicting continuous value. It's not the same everywhere. In classification, the target variable is categorical in nature. Like if you consider apple versus orange, or you consider iris dataset, there are limited number of categories, so we call it as a classification problem. I repeat, whenever you have labeled data, that means independent variable and dependent variable both are given, you call it as a supervised problem. So if the dependent variable is continuous, that is called as regression, and if the dependent variable is categorical, that is called as classification. That's one thing over here for me. We can also say, well, Amitoj, what we used was a classification approach only. Logistic regression is a classification algorithm. It is not a regression algorithm. Give me some time, I will come and justify on this, but logistic regression is not a classification algorithm. What we use was regression. What we use was classification only. It's not a regression algorithm. I know that. I know that. I usually come to when we study these algorithms and all, we'll be discussing all of these things, of course. Okay, now this is one part of the thing. And what all algorithms come and said that let us actually write it. No, I'll not write it. Why to unnecessarily invest time? We will do it in a smart way. Now, see, we understood that regression algorithms as the one where you are going to have the target variable to be continuous in nature, and the classifications are the one where you have target variables to be categorical in nature. Then after this, the next thing over here, unsupervised. Now, unsupervised is the one where only X is given, but Y is not there. Now, that is little weird, right? How can it be possible that dependent variable is not there? I'll tell you, let's take an example to understand this thing. So, what am I considering over here is, let's say I am collecting, we are how many in the, we are 55 in the class right now, right? So, I am saying that everyone, please come and deposit your phones on this table. Please come and deposit your phones on this table. So I'm depositing my phone. You deposit your phone. In this way, many people, all the 54 phones are deposited on my table. Okay. So we have total 54 phones. Now the thing is, I invite Preetham on the stage. And I asked Preetham, these are 54 phones. I want you to group it on the basis of similarity. So, Preetham, what will you as an individual consider for grouping this phone based on some similarity factor? Okay. So, let's say Preetham says brand. So, if Preetham is dividing the phones on the basis of brands, in our class, considering there are 54 people, how many groups is Preetham likely to get? Likely. Mota mota, what do you think? How many groups will Preetham get? 3 to 4, 2 to 3, 10, 4 to 5, 5 to 6, 6 to 7, 5 to 10. Yes. Let me take a realistic figure. Let's say he gets around 5 to 7 groups. Samsung, Apple, Oppo, Xiaomi, Vivo, nothing, and 5 to 7 groups. Okay, I go to Rahul. Rahul says, no, no, Darshan sir, I will not group by brand. If I have to group it, I am going to group it by color of the phone, major color. So it's not that white and off-white I'm gonna separately. White, red, blue, yellow, pink. So if he does like that, maybe he gets around again 5 to 6 groups. Someone else comes, he said that I am going to group it on the number of cameras. The number of cameras means, see, in my phone, if you see, there are two cameras over here. So I'm talking about this as the number of cameras. So if I'm grouping it on the number of camera, not the camera megapixel, how many groups will I get in my group, in my class? Maybe 3 to 4, not more than that. Someone says, no, no, I am going to group it on the basis of internal memory. Is the memory half GB, 512 GB, 1 TB, etc., etc. So he gets again around 3 to 4 groups. Now the thing is, who is wrong in this case? Whose grouping is wrong? By brand, by color, by cameras, or by ROM? Whose grouping is wrong? No one, right? Yes, no one. That's exactly what is the thing. So consider over here now, how is the data that you are having? So I have collected the data of 54 phones, right? So phone number one, phone number two, right up to 54. And there can be various features. The first feature could be what is the brand of the phone. So let's say if I'm talking about me, let's say it's Apple. Then the second feature could be what is the model of the phone. So let's say I'm saying iPhone 15. Then the third feature could be what is the color of the phone. So let's say the color of the phone is green. Then fourth feature could be what is the RAM of the phone, which honestly speaking, I don't know. What is the ROM of the phone? In this way, there are, let's say, around independent variable, 30 independent variable talking about various features. And that is it what we have. So let us say we decide to group it as per the brand. Then, okay, brand, okay, let's say brand, or let's say decide to group it by any other thing. So what will happen is anywhere, let's say if you're grouping it by brand, then anywhere you see uh, the phones which are by Apple. So let's say I say that wherever I see Apple phone, I'm gonna call it as group one. Wherever I see Samsung phone, group two. Xiaomi phone, group three. Oppo phone, group four. Nothing phone, group five. Vivo phone, group six. So here, my dependent variable is what? Who is finding? I. I am finding dependent variable. Earlier it was given. So here I will be assigning group one. Maybe if this is a Samsung phone, I assign group two, and so on and so forth. I'll assign any one of these values over here. Once I have this, then I can convert it into a supervised problem. But in unsupervised, you are not given any kind of in unsupervised, you are not given any kind of this. That's important. Are you all understanding what is unsupervised learning? You don't have a target variable, you don't have a dependent variable. That is what is important. So now, in unsupervised learning, there are uh, following domains. The first domain is called as clustering. And here you have the algorithm k-means. You have hierarchical clustering, which we just saw. You have DB scan algorithm. The next one that you have, it is called feature selection algorithms. Here you study algorithms like recursive feature elimination and variance inflation factor. Variance inflation factor. You'll study that. It's better we talk about it later. Third is you also have dimensionality reduction algorithms. So here you have PCA, LDA. So you know when they are used, so consider scenarios where the number of independent variables are not just 100, 200, but you have the number of independent variables as 1000, 3000, 5000. These many are the number of independent variables that you have, and in that case, it becomes a challenge. So how do you actually reduce it? How do you actually reduce it? And that's where the challenge starts. So these algorithms are mainly used for reducing the dimension. Now there is a difference between feature selection and dimensionality reduction. It's a little difficult to make you understand right now, but we'll be understanding it as and when we go ahead. Then the fourth one is what we call as anomaly detection algorithms. And the fifth one, so there are five types inside this. Here there were only two types, but here there are five types. Association rule mining algorithm, where you have algorithms like a priori or FP growth. That is how you study this. Then the next type of learning is what you call as reinforcement learning. So what is reinforcement learning? Well, reinforcement learning is learning from our own past experiences. So if I take example, let's say about the Tesla's autonomous car. Elon Musk and his team has already trained the model with some pre-built knowledge. And using that knowledge, it takes a decision. But the best part of that is taking decision was still fine. But after taking the decision, after taking the decision, it will also automatically learn in real time setting. Like for example, let's say I was driving a car some point of time on a highway. This was the going way, this was the coming way, and this was my car. There was a truck which was here. I gave a right indicator and I moved my car over here, but this truck person should have braked. He instead accelerated. And when my car was here, he dumped my car here. So that's a learning that there are some crazy idiot nonsense drivers who don't understand that they have to brake if there is a safe distance and allow the person to go. So these all are nothing but what we call as learnings. The car also learns from experiences. So whatever knowledge it has, it keeps on updating its knowledge base, and that is what is called as reinforcement learning. Learning from your own past observations. This is another 40 hour of syllabus. In our syllabus or in anywhere, right? Reinforcement learning is not a part of our syllabus. Our syllabus is mainly talking about supervised and unsupervised part. Now coming on to the supervised algorithms as well. If you talk about this, see, that's why I didn't write it down. So if you see, following are the algorithms. Linear regression, k nearest neighbor regression, decision tree regression, support vector regression, Adaboost regressor, gradient boosting regressor, random forest regressor, extra tree regressor, ANN regressor, and here, Amitoj, logistic regression. It's a classification algorithm, LDA, K nearest neighbor classifier, decision tree classifier, support vector classifier, AdaBoost. Yes, that's correct. You heard it right. They are available in both the cases. AdaBoost regressor, AdaBoost classifier, gradient boosting regressor, gradient boosting classifier, random forest regressor, random forest classifier, extra tree regressor, extra tree classifier. Similarly for ANN. And there are many more algorithms, but these are the popular ones which they have listed over here. So I come and quickly put this, and that gives you some idea about the available algorithms. Just read it once, and now also read this chart overall. And yes, so now we are good to get started with our very first algorithm, which is called as the linear regression algorithm. Enough of introduction. Let's get into the very first algorithm. So I come down, and this is where I give you the introduction. Honestly speaking, no, but you can create a model in Java or C++ as well. But created in Python can be used in Java or C. No, that won't be compatible, right? And why do you have to create it in Python or Java? For inferencing, see, if it has understood everything using the language as Python, of course, it cannot be programmed with any other language. That's too early, actually. We are going to get into that only. In fact, now when I said we'll be starting with the machine learning algorithm, we actually get into that. That's correct. So, so friends, let's get started with the very first algorithm, which is called as linear regression. So here we are, linear regression. It is a supervised machine learning algorithm. This algorithm can be used if and only if there is a linear relationship between independent and dependent variable. So what is exactly meant by linear? Right. So I said this algorithm can be used if and only if there is a linear relationship between the two. So what is meant by linear? See here, consider this. I'll consider several scenarios. This is independent variable, this is dependent variable. Let's consider the temperature versus sales. Now, overall, we understand that as the temperature increases, let's consider the sales of ice cream as I always consider increases. So this relationship can be more or less modeled on a straight line, something like this. So I say that overall we see that the relationship is linear. That means I can say that as x increases, y increases, or I can say x is directly proportional to y. But as one increases, if other increases, we call it as linear. You have an independent variable, you have a dependent variable. Consider one more example. Let the x-axis be the number of cigarettes you smoke, and y-axis be the number of years left in your life. Do you all agree that the more cigarettes you smoke, the more early you die? Now, don't give me any odd examples that he has survived so long, he is smoking. What is the scenario in most of the people? Do you all agree that the more number of cigarettes you smoke, the more early you are likely to die? Yes. So the thing is this relationship linear? Because here we see that as x increases, y decreases. So I can also say that x is inversely proportional to y, but I can still say that this is linear because it can be represented on a straight line. This also can be represented on a straight line. Now, I don't know what can be the example of this, but just tell me, do you see this as a linear relation? This one? No. So this is something which is not linear. Essentially, if and only if the relationship is like this, then only it can be used, else it doesn't make sense in going for this. Else it doesn't make sense in going for this. That is something which is very, very important. And that's exactly what we call as linear versus nonlinear. So if your relationship is linear, then linear regression can be used, else you can't use it. As simple as that. Correlation is different from the linear regression. And the reason I say correlation is different from linear regression is because correlation can be between any two variables. So I can find out the correlation. That's a very good point. Correlation can be between anything. It can be between two independent variables, x1 and x2. It can be between some other independent variables. But a regression will always be between independent and dependent variable. Although mathematically you are going to find a single value only, but correlation is just going to tell you whether they move together. Regression will be helping you to predict the unseen value. So that is how they are different. Right. Yes. So we are going to talk about that. You will actually understand what is that. Got it. Very good. So yeah, well, at least let's complete with the algorithm for understanding part of the algorithm. Remaining things we can at least take it later. So let us get started with a very basic understanding of regression algorithm. So some basics. Going back to school, we studied in school something which is called as the slope of the line. Some of you might remember it, some of you might not remember it. I'm not assuming anything whether you know it or not. So I'll get started from the scratch only. So here in school, we studied that if this is a line, then every line has an equation which is of the form y is equal to mx plus c. Y is equal to mx plus c. Correct? This is what we had studied. Here, m is nothing but the slope of the line which is given as change in y upon change in x, which can also be written as y2 minus y1 upon x2 minus x1. So what is y2 and what is y1? On this line, if you assume anywhere, any 2 points on a line, on a line, not on a curve, on a line, anywhere you assume any 2 points. Let's assume these two because these are directly available. And what are these? 8, 6, 2, 3. So I can assume this to be x1, y1, x2, y2, which means that if I am doing y2 minus y1, it is going to be essentially 6 minus 3 upon 8 minus 2. So m is going to be is equal to, which is 0.5. And if some of you say that, no, Darshan, why are you not assuming this as x1, y1 and this as x2, y2? So if I assume it like that, then what is the final answer? Tell me quickly. What will be the final answer? If I assume this as x2, y2, this as x1, y1? Same. Because this is minus 3 upon minus 6, which is still 0.5. In fact, even if you assume any other 2 points also, it will always be 0.5. And the next is, what is this c? C is nothing but called as y-intercept, the distance from 0 to wherever this line intersects the y-axis. That's called as c. So if this line would have been intersecting here, then c would have been this distance on a negative side. So it's called as a y-intercept. So in my case, the equation of the line becomes, that is, what is the equation of the line? What do you exactly mean by the slope of the line? That's another thing which I want to say. So slope of the line means for every 1 unit you travel on x-axis, how much do you climb on the y-axis? Means, see here, from here, how much I traveled on x-axis? 6 units, right? I moved from 2 to 8, total 6 units. And how much did I climb on the y-axis? If I go like this and like this, then you can see I traveled 3 because this is going to be 3 and this is going to be 6. 6 minus 3 is 3. So that means I can say that if I am traveling 3 units, that means if I'm traveling 6 units on x-axis, on the y-axis, I am climbing 3. If I travel 1 unit on x-axis, I should ideally travel half of it. Check it out. I'm here from 2. If I move to 3, how much do I climb up? 3 to 3.5, half of it. That means if I travel 12 over here, I travel 6. If I travel 16 over here, I travel 8, and so on. That is exactly what is called as M. For every 1 unit you travel on x-axis, you travel half on the y-axis. That's essentially what M is. Therefore, the M came out to be 0.5. And this is what is the basic equation of the line which we have understood in our school days. Yes, this is our basic understanding that we are having from our school days. So now I'm gonna put that over here. Now, mathematics of linear regression. I'm gonna explain you next time once again. Uh, this time I'm just going to give you a quick heads up. So now consider over here. Okay, let me ask you, before we start with the mathematics, let me ask you if uh, what is the slope of the line? Minimum and maximum value of slope of the line. What is the minimum and the maximum value of slope of a line? Okay, let's see. See here, you see this is the dynamic figure. You see the slope of the line is getting calculated here. If I make it more up, it crossed 1. Okay. See here, what did I say? I took the data set of 150 rows, divided it, and then I divided the data into 80% and 20%, which was done here. Here, I did say the test data must be 20%. So by default, this becomes 80%. I want some of you to try out 85-15 ratio. I want you to try out the 70-30 ratio. I want you to try out the 75-25 ratio. I want you to try out 60-40 ratio. And every time you will be getting the accuracy. I want you all to make a note of all the accuracies and tell me which ratio is giving you the highest accuracy. So any, you can try out any value of test size from 0.35 and below, every time decrementing by 0.05. So 0.35, 0.30, 0.25, 0.20, 0.10. I want you all to try out these all values every time, making a note of this accuracy and tell me which combination is giving you the least accuracy. Meanwhile, I'll just get this exported. Let me talk about what is exactly linear regression and when should you use it. So let me give you a heads up around what is linear regression algorithm. So I say linear regression. It signifies relationship between a dependent variable and one or more independent variables. Example, price of car is dependent on the length of the car. More the length of the car, higher is the price of the car. This is called as a linear relationship because as the value of independent variable increases, the value of dependent variable also increases linearly. Price of the car is dependent on the horsepower of the car. As the horsepower of the car increases, the price of the car also increases. This is also called as linear relationship because as the value of independent variable increases, the value of dependent variable also increases. Price of the car is dependent on the weight of the car. The explanation goes in the similar way. As the value of independent variable increases, the value of dependent variable also increases. Price of the car is dependent on the mileage of the car. This is called as linear relationship because as the value of the mileage of the car increases, the price of the car decreases. But here, the relationship is negative in nature, unlike all of the previous examples where it was positive in nature. So basically, we can say, so one thing is for sure, you might have seen every time I have been writing one word, dependent variable, independent variable. This one word you might have seen I have been using. I never talk about two independent variables. I always talk about one independent and one dependent. So here, independent, dependent. That's very important. Independent, dependent, independent, dependent. So if I'm considering temperature versus sales of ice cream, we know that as the temperature increases, the sales of the ice cream also increase. So roughly, you can see that this relationship can be plotted across a straight line because you can see the trend. So that means as temperature increases, sales of ice cream increases. That means I can say that X and Y is directly proportional. Yeah. So I was saying, if you consider the same example like we discussed earlier, this is the number of cigarettes a person smokes versus the number of years left in his or her life. So we know that the more number of cigarettes you smoke, the lesser are the number of the years which are left in his or her life. So here also we say the relationship is linear. Here also we say the relationship is linear. Here there is a positive relationship and here there is a negative relationship. Negative means as x increases, y decreases, or x is inversely proportional to y, but both are linear. But if you have a data which is like this, now in this scenario, this is the kind of relationship that you have between independent and dependent variable. This is what you call as nonlinear. Now, the very important thing is I want to talk about the difference between regression and correlation, because regression and correlation looks very similar. Correlation, it defines the association between any two random variables. Regression, it defines the association between dependent and independent variable only. Example, based on DNA and blood group, match a child will be associated to a parent or not. So, in correlation, you just try to find out the value which will signify whether these two things are having a tendency to go together or not. But in regression, you are using it as a machine learning problem to predict the future values. So in correlation, it describes a linear relationship, but in regression, you actually look at the best line on the data. So there is a difference. So basically, correlation can be between anything. So you can just consider in simple words that correlation is between independent variable versus independent variable. Regression is between independent variable and a dependent variable, because they are very simple, and you'll understand it in more detail as and when we get into the implementation of it. But for now, you can remember the most important difference as correlation can be between any two independent variables, and regression will be compulsorily between independent and dependent variable. I was saying, so we have already seen how correlation is different from the causation. But let me just try to give you some more differences in between the two. So, but you'll understand it 100% as and when you go ahead. Let's talk about it. Correlation versus regression. Correlation measures the strength and direction of linear relationship between two variables. Regression predicts one variable based on the other. We call this as purpose type of relationship. Symmetric in case of correlation. Correlation between is same as between in case of regression. Regression predicts y from x. So the direction matters. The direction matters. So basically, correlation between x1, x2 is same as between x2, x1. But over here in regression, the relationship between x and y is not as same as between y and x. I'll give you a clear example as well as we go ahead. The third point. Output. In correlation, the output is a single value between -1 and +1. In regression, we get an equation of the line y is equal to mx plus c. Slope. Intercept. Causality. Correlation does not imply causation. In regression, it is often used to infer or test. Causation. Variables role. In correlation, there is no distinction between independent and dependent variable. In regression, there is a clear distinction where x is the independent variable and y is the dependent variable. Units. Correlation is unitless. Standardized. In regression, the units matter. Output is in units of y. Let's try to clearly understand it with the help of example. Example 1. Height and weight of adults. Correlation will measure how strongly height and weight move together. And let's say they give a value of 0.85, indicating a strong positive correlation. This means that taller people tend to be heavier. Regression will predict the weight on given height using regression line. Here you get an equation after you apply the machine learning algorithm, which looks like y is equal to mx plus c. In this, we have to predict weight. So weight can be 0.9 multiplied by height plus 40. A person of height 170 centimeter is likely to weigh, this will be 170, which is finally equal to 193. Easy approximate. So you can see we are actually finding out something using something. In correlation, we are just comparing. If I take one more example of study time versus exam score. In correlation, we check whether more study time leads to better scores. Let's say we got the value of correlation as 0.7, which shows moderate positive. This means that more study hours are generally associated with better results. In regression, we predict exam score based on the study time. So again, you will be getting an equation which will look like this one, y is equal to mx plus c, where y is nothing but the exam score, let's say, which is y into study hours plus 50. So a student who studies for 4 hours is predicted to score. Exam score is equal to 0.4 plus 50, which is equal to 70. So you can see over here the use case of each of this is completely different. You saw this example of height and weight, study time versus exam score. The uses are completely different. In regression, we are trying to predict. In correlation, we are trying to see how they are going together. So therefore, I say coming in 10 seconds. Okay. So, early morning, when you get up now, it's all jam. In an hour, it becomes normal. Correlation tells us how two variables move together, strength and direction. Regression tells us how much one variable changes when the other changes, hence used for prediction. Yeah, that's how it is. For now, at least, that is how it is. Now, let's try to understand directly getting into the mathematics. So here, pinning a lot here. So I was saying some basics of what we have done in the school. In school days, we understood that the equation of the line is written as y is equal to mx plus c, where m is nothing but the slope of the line, which is nothing but change in y upon change in x, which is y2 minus y1 upon x2 minus x1. Yes, no need to be smart by giving suggestions over here. This is very basic. So please focus only on understanding. Anyway, that's school level. But I remember when I started machine learning, I had forgotten this also. So this is specifically for the students who are as weak as I was, right? Those who don't remember. Most of you might be remembering, but trust me, I had actually forgotten how to calculate the slope of the line. So now how do you calculate? Sorry, that is the slope of the line. And C is nothing but what you call as y-intercept. Now, how do you calculate M? M is calculated as change in y upon change in x, where consider any line on the xy axis. You assume anywhere, any 2 points on the line. Yes, that's important. Anywhere, any 2 points on the line. So let's consider the points which are already here. 8, 6, 2, 3. So I can assume this as x1, y1. This as x2, y2. So y2 minus y1 is 6 minus 3 upon x2 minus x1 is 8 minus 2, which is 3 upon 6, which is 0.5. Similarly, you can also say that no, I'll assume this as x2, y2, this as x1, y1. If that is the case, then it is 3 minus 6 upon 2 minus 8. Minus 3 upon minus 6, which is again 0.5. And even if you assume this point over here, maybe if you consider this as 12 comma 8, then still that will be 8 minus, let's assume this as the point, so 3 upon 12 minus 2, which is 5 upon 10, which is 0.5. So essentially, you assume this points anywhere, the answer will be this. And wherever this line intersects the y-axis, that distance is called as C, which is nothing but y-intercept. So imagine this line would have been like this. Then C would be minus 2 in that case. But our line is something like this. I would like to ask you one question. The slope of the line ranges between what and what? Slope of the line ranges in between minus infinity to infinity. So M can go on from minus infinity to plus infinity. Okay. So these all was just a quick context setting once again. And now I get on to the linear regression. Now, let's try to understand how linear regression actually works. So here, let's assume that on the x-axis and y-axis, we have the following data. So let's say on the x-axis, I have the area of the house in square feet, and on the y-axis, I have the price of the house. Do you all agree? As the area of the house increases, the price of the house also increase in a particular locality, yeah? In a particular locality, right? So let's say the area of the house is 2000 square feet. Let's say I'm assuming the price to be 2 crores. If the area of the house is 1500 square feet, I'm assuming it to be 1.5 cr and so on till the end. So let's assume the same thing over here. On the x-axis, I'm assuming the area of the house, and on the y-axis, I'm assuming price of the house. So obviously area cannot be 246. So let's say into 1000 square feet. And here, let's assume this is 2 CR, 4 CR, etc. So in this case, that's my independent variable and that's my dependent variable. What will I do is I will end up plotting all these values on a scatter plot. And it is expected that as one increases, the other also is expected to increase. Now, what is the end goal? See, the end goal over here is now that we have this data, we want to draw a line. The machine learning algorithm tries to draw a line in such a way that the line should pass through all the points. Is it possible to draw a line which passes through all the points? Yeah, I think this is how we can try it. But is this a line? No. We just understood that a line is like this, like this, like this. Anything which is straight is only a line. This looks like some stock market graph. So they say, let's try to draw a line which passes through maximum points, and the ones which it is not able to pass through is as near to the points as possible. So it should pass on through maximum points, and other points should be as near as possible. So is this line passing through maximum points and others are as near to it as possible? The first line? No. Is the second line better than the first line? Better? Okay. Is the third line even better than the second line? Yes. Is the fourth line even better than the third one? If I assume the fifth line, can you assume this is the best so far which is already drawn? So among so many things, if you look at this fifth one, can I say this is the line of best fit? Right? Yes. And obviously, if it is a line, we know that it will be having an equation. And since we have already worked on it, we know that this line has an equation which we just populated before coming to this, where it was having the m value calculated as 0.5 and what was the c value calculated as 2. Now, the thing is, how does this equation help? Let's say you created a linear regression model which is talking about predicting in this way. A friend of you comes to you and says that Darshan, you are a data scientist. I want to buy a house in this particular locality, and I am looking to buy a house which is 3,500 square feet, which is 3,500 square feet. Can you let me know what is the price at which I should buy it? And I say, yeah, definitely. What will I say? I have this equation 0.5 into 3.5 plus 2. Why 3.5? Because it's into 1000. Can you tell me what does this evaluate to? Half of 3 is 1.5, 1.75, 3.75. Correct. So can I say he will buy it at the best price to buy is 3.75 CR? Yes. He said he wants to buy a 3.5 CR house. So this is 2, this is 3, this is 3.5. And I say that you want to buy a 3.5 crore house, then this will be the price of best. And you can see this is 2, this is 4, this is 3, this would be 3.5, this is 3.75. That's perfectly. Yes. So this is where I did show it to you geometrically. This is where I did show it to you algebraically. Are you able to understand both the approaches? Some important points I want to discuss now. Some very important points I want to discuss now. But before that, let me just capture this screenshot. The equation of the line, as we just understood, a friend of mine comes to me and says that Darshan, I am looking for a 17,000 square feet house. Could you help me? What will be the price of the house? So, what will be the price? I want to hear it from you because we have just learned how to do that. So, what will be the price of the house? Okay, 10.5 CR. And this is exactly where I want to put forward my point. In this scenario, I completely understand that the equation works, but I want to raise a warning over here that the right answer to this should be, I don't know. Now, you might be thinking, why? Because here, if you see, we are extrapolating, and extrapolating is risky. Now you'll be like, what is extrapolating? See, if you remember the data points which we had from the earlier figure, see, I had drawn it like this. This was how the data was. There was not even a single house in our data set, which we did draw over here. When plotted, there was not even a single house in our data set which was above 14 CR. And here they are asking us to predict for 17 CR. Am I correct? Did these pink dots go anywhere above 14 CR in the previous figure? No, right? And here we are asking it to predict for 17 CR. And I say it is risky. Now you may say that Darshan sir, but looking at this trend, as the price of the house is increasing, sorry, as the area of the house is increasing, the price of the house will increase. So consider the area where you are living. So lower class, middle class, or maybe higher middle class. I'm sure not ultra rich. But what I want to say is imagine the area in which you are living. There will be lot of 1 BHK apartments, lot of 2 BHK apartments, lot of 3 BHK apartments. These are the common needs of the people. If you build up a 7 BHK apartment, let's say I'm a builder who comes to your locality and I build up a 7 BHK apartment where most of your paying capacity is somewhere between 50 lakhs to maximum 4 CR. and I'm building up a 7 BHK apartment and I'm selling it at 8 CR. Do you think there will be even a single customer capable of buying it? Or a ultra rich person comes and buy it in a locality where people like you and me stay? Do you think like that the sales will happen? No. That is why, though the price that you predict may be correct, but no one will buy it. So there is no business sense over here. I'll take one more example. Consider over here. Consider over here the same example of temperature versus sales of ice cream. So we know that temperature is 10 degree, 20 degree, 30 degree, 40 degree, 50 degree. As the temperature increases, sales of the ice cream increases. No doubt about that. Let's say the temperature becomes more. Temperature becomes even more. People will even stop getting out their houses. Even the Swiggy, Zomato will stop their deliveries. And the pattern would be like this. So, what you thought, where you plotted a linear regression algorithm because you had data given up to 50 degrees Celsius, and then someone said that okay, if the temperature is 60 degree, what will be the sales of the ice cream? What will you predict? You will predict, okay, it's 60 degree, and you want me to predict the sales of the ice cream. So 60 is here, and this goes here. So according to you, the sales of the ice cream is this, which is very high. But that is wrong. That is wrong. The actual sales of the ice cream is this. This is the actual sales of the ice cream. But what you predicted was this. And this is exactly what is called as extrapolation. You assuming that the trend will continue. That's risky. It may continue, it may not continue. So the idea is very simple. You should always ask the machine what it has studied, not out of the range what it has studied. So if a machine is being taught something, you should not ask him to predict out of the box values. Like for example, let's consider this application which I talked about. I remember this Streamlit app is what I had shown it to you earlier. Am I correct? Did I show you this app? Yes, very nice. So consider now in this data, in this data, let's consider you had the iris data set, not iris, you had the tips data set. So that data set which you had consisted of, we were predicting the tip given based on four independent variable, and one of the independent variable was total bill. I remember in the restaurant when I did df.describe, the total bill's minimum value was $1 and the total bill's maximum value was $17. I remember that very well. The size of the people coming, the minimum was 1 and the maximum was 6. So if you ask a model that, hey, can you predict if the total bill is $25 and if 12 people visited and rest all things you gave in range, can you predict the tip given? It will predict, but the chances of it being right are not so great. One should not do that. Tell me one way how we can avoid it. As a customer, the customer should know that it has to not give any value above this or below this. It has to be compulsorily between 1 to 6. How can you think of handling this? Just a logical move. Let's say this is the problem that you are facing. What input will you give? The customer should not give any value out of this range or out of this range. What can you do? It's nothing related to machine learning. It's nothing related to machine learning. You cannot change anything in machine learning. Think about what change can you make to this user interface. Yes, that's nice. You can put in an input validation. That's one of the very, very important thing. You can put in an input validation. So precisely, if you see, I have put in over here plus and minus. Plus and minus should be there, but the maximum plus, like for example, the minimum is 0. I cannot, you can see the minus is frozen right now. The minus is frozen. I cannot go below that, but the plus is available. See, minus is not available, plus is available, and it is incrementing. This plus should have the maximum range up to 17, and this minus should have minimum range up to 1. Similarly, here in size of the party, see, this is going up to this, but there are no cases where the model got a chance to predict it, and this is extrapolation. That is risky. So tomorrow, if I say 300 people are going, it is predicting the tip as $70. But that restaurant cannot accommodate 300 people. It has only a seating capacity of maximum 30 people. Similarly, I give the gender as M. The model was taught either male or female. If I'm giving M, it should not accept. It should not accept. It should not accept. Or if I say MALE, it should not accept. So these are the things that a user interface person will have to take care of. But again, it is your duty to tell it, because all the machine learning algorithms work on a very simple funda: garbage in, garbage out. Right? And extrapolation can be risky. Okay, so that was one thing. The next thing. The next thing is, you have seen, this is the last thing which I want to say. We just saw that in this example, we had one independent variable versus one dependent variable. So for that, we did go for a scatter plot, which was two-dimensional in nature, and that gave us the equation y equal to mx plus c. Consider the scenario where I have two independent variables. So this time the scatter plot would be three-dimensional in structure, and the equation of the line would be m1 x1 plus m2 x2 plus c. Consider the scenario where I have three independent variables. So the scatter plot will be, see, one independent variable 2D plot, two independent variable 3D plot, three independent variable 4D plot. And do you know how does a 4D plot look like? No, as a human, we cannot see anything about three dimension, but this equation can be m1 x1 plus m2 x2 plus m3 x3 plus c. In the same way, consider I have n independent variables. So the plot is n plus 1 dimensional. I cannot see how it looks like, but the equation will be m1 x1 plus m2 x2 plus mn xn Let's see. So essentially what I want to tell you is this figure may not be of help to us when we go anywhere about 2D, because 3D plots are also difficult to visualize. But this equation is very, very important, and you will see this equation coming into action when we actually get into the implementation part of it. So I will now get started with this, and let us get into it. So first of all, the idea is to implement simple linear regression and say, let's do the imports. Import numpy, pandas, matplotlib, cbot. Then I would say import warnings. Done. Then after this, I will also be reading the data frame. So I say data frame is equal to pd dot read CSV. The data is already available here. So you can see the data is very simple and straightforward. The number of hours student has studied versus the score that they have received in an exam. There are 25 students in this class. So to start with, that's an awesome problem statement. Going forward, we'll be looking into complicated ones only. But first one is very good for understanding. So yes. So description of all the columns. You see the first column is hours with the number of hours a student has studied versus the scores that he or she has received. Now, what did I say? What is important? We are here to implement linear regression, and if you look into the shape of the data, it has 25 rows and 2 columns. It has 25 rows and 2 columns. What do we want? I want, first of all, there must be linear relationship between the independent and the dependent variable. So let's do one thing. Let's plot a scatter plot to visualize the relationship between hours and this. So I say sns.scatter plot. The data frame is df, x and y axis, as you see, and title is there, x label is there, y label is there, and you can see this is how the scatter plot is. Do you see over here, there is a linear relationship between the hours studied by a student versus the score that he or she has received? Yes, that means linear regression is probably a good candidate to be tried out. In fact, instead of this, if I copy the code and instead of scatter plot, if I go for joint plot, everything I keep the same, but kind I'm keeping as scatter, right? So this is the same thing. I just replace scatter plot by joint plot, but kind is scatter. I see the histogram also, but I don't want to go for this. I actually go for kind is equal to REG. And see, when I just said joint plot of the same thing, Ali, you see this kind equal. So I was saying, you can see over here, when I say kind is equal to regression, we can see the line also. This was just for plotting. Of course, this is not machine learning, but it is kind of finding out the relationship. Okay. Now, see over here. Now that we have this data set, this data set consists of 25 rows and 2 columns. The first thing is to separate out x and y. So the hours must be the independent variable and score must be the dependent variable. So I will have to separate it out. Now, how can I separate it out? Well, I can say, I want to show you how do I select the hours column like this. That's how I select the hours column. Entire hours column is there. First thing, what is the data type? When I'm checking the data type of the hours column, it is series. And now, if I put the same thing like this, what is the difference in between the two syntaxes? What is the difference in the two syntaxes? Data type and the double square bracket. That's the difference. Now, here I say X is equal to df of hours and this. Now, this is important. What did we do? We separate the feature, or I can say independent and dependent variables. X is the independent variable, Y is the dependent variable. It must be a 2D array, and here it must be a 1D array. That is the rule of machine learning. You know why X must be a 2D array? Because here you are having one independent variable, but in real life, there will be more than one independent variable in almost every scenario. Yes or no? In real life, there will never be one independent variable. There will be many, maybe more than 20, maybe more than 100, maybe more than 500 also. That is the reason this has to be 2D and therefore double square bracket. Remember this, we will not go for single square bracket. So X and Y separated. I can look into the shape of X and Y. X is 25 comma 1, which means 25 rows and 1 columns, and Y is 25 comma, which means just 1. So this is what we have. Now, what is the next thing that we have to do? So for now, we had this data, which consisted of this X and Y. We separated X and Y. Now it is the time for us to divide X into two parts. The upper part will be called as train. The lower part would be called as test. So this will be called as X train and this will be called as X test. Also, we need to divide Y also into two parts where this is called as Y car train and this is called as Y test. We had discussed all these conventions yesterday. Am I correct? Did we discuss all these conventions? Yes. Now follow the two ink colors which I have used. Now, if you have to do this, machine learning says you want to do this, no worries. There is a class called as train test split. In machine learning, whatever you want to search for, you should just type sklearn ahead of it. So you want to go for train test split. You just type sklearn. Sklearn stands for scikit-learn. Almost, almost all machine learning algorithms are dumped into this library. Almost every ML, almost every 95% of the machine learning algorithms that you use, you will see it inside scikit-learn. I click on that, you get the official documentation, click on it. And I'm first of all going to come over here and I say train test split. How to use this? So if you see carefully, it says inside the sklearn, there is a sub-module which is called as model selection, which has the train test split class. So I say from sklearn dot model selection, import the class train test split. From sklearn dot model selection, import train test split, which is what we did so far. It says, Darshan, you give me X and Y that you have already divided because this X has to be further divided into two parts. Y also has to be further divided. So you give me X and Y and I say, yeah, sure. This is the X and this is the Y. Given? Now, logically, after giving X and Y, but see, X and Y has to be divided. But 25 rows are there. It asks me, Darshan, you want to divide it into what percentage? I decided 80-20 for now. We can change it. I decided 80-20. So that's the test size parameter. How much percentage you want in the test? You can give it over here. So I want 20% of the data. So I come and I say test size is equal to 0.2. I don't give train size. No. If train size is also none, it will be 25. If I only give test size and if I don't give train size, it will be automatically computed. It's all written in this documentation, but this is just I'm explaining you. Okay. Then I want to tell you the shuffle parameter is by default true. What happens? After it is done, I say, this is not how it is done. I actually wrote it here. This is where. So it gives me four parts. X train, X test, X train, X test, Y train, Y test. You cannot change the order. You cannot change the order. And this is what you get. You just have to supply train test split X and Y into this. And then I would like to print the shapes of each. So X train का shape, X test का shape, Y train का shape, Y test का shape. So obviously 25 rows are there because you said 80-20. It is splitted as 20 and 5. Quite obvious because you said 80-20. It's perfectly splitted like this. We understand it. Okay, so 20 rows are here, 5 rows are here, same is over here. You can see these are 2D and this is 1D. That was quite as expected. Okay, now let me actually look into X train. So do you all agree that ideally X train will be having the data because we have just seen when you look into the data frame, this is row 0, 1, 2, 3 up to 24. So obviously when I'm dividing it in such a way that the first 20 rows will be here and last 5 would be here. Do you all agree that row number 0 to row number 19 will be here and row number 20 to 24 would be here? So I repeat, 0 to 19 in the train and 20 to 24 in the test. Do you agree or not? Because I said 80-20 split. Ideally, yes. But that does not happen. And that does not happen for the very obvious reason that the shuffle is true. Shuffle is true. So when I do it, you see over here, you're not having it starting from 0 because our shuffle is true. So one way you can say is, Darshan, what we can do is we can make shuffle as false. If I make shuffle as false, then it would be perfect. So if I come over here and I say shuffle as false, I do that. And this is what you see. But this is not a good idea. This is not a good idea. You should never make shuffle as false. Why am I saying that you should never make shuffle as false? The reason I'm saying you should never make shuffle as false is because of some scenarios like this. Consider this scenario. If you see carefully, we have brand and the price of the phone. Apple phone costing this, Apple phone costing this, so on and so forth. We have 11 records of Apple phone, actually 10 records of Apple phone. Then after 10 records of Apple phone, I see there are around 10 records of Oppo phone. After that, I see there are around 10 records of Samsung phone. After that, there are 10 records of Vivo phone. So if you see carefully, right now the scenario is something like that. So I have 10 records of Apple phone. Then I have 10 records of Samsung phone. Then 10 records of some other phone. Then again 10 records of some other phone. And again 10 records of some other phone. This is essentially what is the information I have. Now, in this scenario, if I'm dividing the data into 80/20, then we know that this much part will be going into the training and this much part will be going into the testing. Do you all agree that this will be the training part and this will be the testing part? Yes. So, you know what are we doing? The machine learning model is getting a chance to study Apple phones and their prices, Samsung phone and their prices, Oppo phone and their prices, Vivo phone and their prices. But it never got a chance to study, let's say these are the Xiaomi phones. Why? Because the data was in group. So it is like you are asking it to study Apple, Samsung, Oppo, Vivo and predict it for Xiaomi, which is again a garbage input because it never studied. And the machine learning funda is very clear: garbage in, garbage out. If you have never given a single sample of Xiaomi phone to study, how do you expect it to predict correctly if there is no historical data? And this problem is happening because the data is available in groups. Are you all understanding why shuffle is important? Yes, because we really don't know in real life whether the data will be in groups or not. So, shuffle by default as well, they have intelligently kept as true only, and that's always good. You should only not shuffle when you are actually working on a time series problem. Else, in all other cases, it is advisable that you shuffle the data. Else, in all other cases, it is advisable that you shuffle the data. So now we understood that we have to keep the shuffle as true. Now the major concern, when I run this, I can see here I have 11, 15, 9 onwards. When I run it again, my shuffle is different. When I run it again, that means every time I'm going to run, my shuffle will be different. So later on, after this, when I create a machine learning model, at that time also, the model will be studying different data every time. So the overall results of the model will also be different. That is why the problem. So, how do I ensure that all of us are having the same shuffle? I want to ensure that you and me, everyone, is having the same shuffle always. How to make that possible? And for that, they have something which is called as a random state. Random state. That's the only documentation available about it. It is used to control the shuffling applied before the data is split. You should pass an integer value over here for reproducible output across multiple function calls. So random state can be given as any integer value. So random state is used to ensure that the split is reproducible. So if you run your code multiple times, you will get the same train test split. Then can be any integer value in the range 0 to 2 raised to 32 minus 1. That is this number. Also, I would say some of the common values which most of the people end up giving are this: 0, 1, 42, 100, 1, 2, 3, 4. Although you can give any number, but try out these only. They are good in most of the cases. So now what is the advantage? I gave the random state as 40 to see. Now I'm running and now I'm running this. I got 9, 13, 1, 22, 5 as the row. I run it again and I run this again. It doesn't change. See, this is cell number 34. This is 35. I run it again. This is 36. I run it again. 37. But this doesn't change. Run again. Run again. This does not change. This does not change. This does not change. So that is what is the magic. And this is not only applicable to my Jupyter notebook, friends. We can see that this thing is perfectly being found out over here. So we say, what I wanted to say, yeah, this is done. So right now the scenario is you had this data, you divided it into X and Y, and then so I was saying, we had this data, we divided it into X and Y. Now you can see how your X train is and your X test. Your X test will also be same as mine. You can check it out. 100% it will be same. So our train and test are the same. Now it is the time for us to go and create a machine learning model. So the model which I am going to create is linear regression. So I go and type linear regression sklearn. See, this sklearn is very important. This sklearn is very important, right? You can see every time I have been writing the same thing. So here I say enter. Hello, paths, dominant. So getting into this. Now I'll copy this. I'll come over here and I say now it is the time to go for model training. I'll be using linear regression from scikit-learn, and this is where you find it from sklearn.linear model. I repeat, from sklearn.linear model, you import linear regression. So you create an object, sorry, you just import the class. So in sklearn's module called as linear model, you have this class. Then you create an object of linear regression, which is this. You can name this object as anything. Object-oriented programming that we studied during Python. You import the class. First time you may find it little challenging to remember how to remember from linear model, but because it is linear regression, they have dumped it into a sub package which is called as linear model. So from sklearn.linear model, import linear regression. And then I'm creating an object of linear regression. So as we can understand, I am importing the linear regression class. Then I am creating an object or instance of that class. Then I say to the object that, okay, now you are ready. Go and understand the relationship between X train and Y train. Go and understand the relationship between X train and Y train. So I say linear regression, go and fit. Fit the model. Fit means study. Study the relationship between X train and Y train. And it says my study is over. It says my study is over. You can see it says fitted. If you try to understand what it has understood, it doesn't show you anything. It's just the intelligence captured, which is the line of best fit. Now, if you see, we just understood that. See, there are following parameters of this algorithm. There are following parameters. Right now, we are ignoring it. And each and every parameter is explained here. Fit intercept explained. Then copy X tolerance and jobs positive. Copy X tolerance and job positive. And after parameters, you have attributes. So coefficient is nothing but the slope, and intercept is the intercept. So obviously, we know that when fitting is done, we get a line of best fit, which will be having equation y is equal to mx plus c, where m is this and this. That is what is available in the COEF and intercept underscore parameter of the linear regression class. So if I show you this, see, linear regression, if you don't put the square bracket 0, you still get the output. LR dot, why LR? LR is the name of the object. LR dot COEF underscore, which gives me the slope, which is the value of m, and this is the value of c. But it is a list inside which I'm interested in the number. So I will pick up the value at index location 0. Okay. So I say, therefore, the equation of the line is y is equal to this. Let's consider, for example, if there is a student, who has studied for 5 hours, then I want to know what is the score that he is likely to get. So that's essentially what I'm trying to do. So what is the y that you are likely to get? So that is going to be m into x plus c. M and c values are already plugged in because m and c are there. I plugged in. So m into 5 plus c, that happened because m is this and this is this, and you get 51. So if he studies for 5 hours, he gets 51 as the score, 51 point something. That is what is going to be the score. And also one more thing over here, here m value is 9 point. So what does this mean? This means that for every 1 extra hour that the student studies, his score increases by 9.68. This means that every additional hour studied, the score approximately increases by y.68, by 9.68. And the intercept is the score when the number of hours studied is 0. So if a student does not study at all, still he will get 2.48 marks. This is what it says. In fact, if you look into this line, it says that if the student does not study at all, it says that still the student is likely to get 2.48 marks. 2.48. Are you all understanding? If he doesn't even study, 2.48 to kahin nahi gaya. That's confirmed. That's confirmed. Right. And after that, for every 1 hour of extra study, because the M is 9.68, for every 1 hour of extra study, his score will increase by 9.68. And if that is the case, let's make this as 6. You can see over here, if I take this number and add 9.68, it is the same. So for every 1 hour of extra study, the score is increasing by 9.68. Yes. So that's an interesting observation that we see. Now that you understand this, but come on, that would be crazy if I'm gonna compare it this way. If you remember, we had ideally earlier printed the shape of train and test set. You remember this? So here I already have a test data set of 5 rows. Let me use that for prediction. So my linear regression model is going to predict on X test, and I will call it as Y prediction on the test as I discussed it yesterday. And I can also create the Y prediction on the train, right? By predicting on the training and the testing data set. So that is here. Now let us look at the values. So I want to look at the Y test and Y predicted test. I want to look at them side by side. So I'll be using the zip function of Python. So zip function will be stitching them together. This value, this value, this value, this value, this value, this value, side by side, one below each other. And for you to view the results of the zip, you need to typecast it to list. So actual was 81, predicted as this. Actual was 81, predicted is this. Similarly for the other three, 21, 27. So you see, they are not exactly the same. Why they are not exactly the same? Because it is going to predict on the basis of line of best fit. So if you look into this person, this student studies for these many hours and he gets a score for this. But if you ask this to the machine learning model, what score will he get? The machine learning model will be like, okay, studies for these many hours. It will go on to the line of best fit and this is what it will predict. So essentially, this distance is the error. This is the actual, this is the predicted. So this is the error. But this error overall must be small. You should not introspect it just with respect to one point, but overall it must be small. So how do you quantify the overall error in the model? You have metrics. You have metrics which can help you to quantify what is the overall error in this. How are they called? How are they calculated? We will see that after the break. Right now, I'll directly show you that. So these metrics comes in the evaluation phase of the model. And I am going to evaluate the model using the R2 score. So sklearn has a submodule metrics where I import the R2 score. I calculate the R2 score and see how convenient it is. It says that tell me the actual and the predicted. I'll calculate the R2 on train. Similarly, on the test, tell me the actual and predicted. I'll calculate the R2 on test. 94 on train. And surprisingly, on test data set, it is even more. Ha ha ha. But. Do you remember yesterday we discussed what is a good model? What did I say? What is a good model? The one which on the R2 has minimum what accuracy? A good model should have minimum 80%. And the difference between train and test must be less than equal to 5%. So here, all these conditions are satisfied. It's a very, very simple and obvious use case. I was expecting this to be higher and this to be lower. That's not ideally a good sign, but the reason you're getting that is we are having a very small toy data set. How do you expect it to give awesome results? But still, it has given quite good. And you can see over here, that's the overall pipeline. Train and test. Train and test. And this does not actually end the project. We have just started. This is not the only metric. There are many other metrics, but to start with, yes. For now, yes. That's the metric. And as you know, right, I want you to quickly try this out. I want you to quickly try this out, run it, and tell me if you are also getting the same result, exactly the same. You have to run it directly from the collab only. You ran it, Rahul, so fast. How come you typed it so fast, Rahul? I am actually surprised to hear what's your strategy. I can see same. Very nice. Many people rewarded. I can scroll and check it. I see around 15 reward. What if, what if now I come down? See, what can I change? What can I change? I can maybe try changing the split ratio. Now my data is very small, so I will not change the test size, but I will try changing the random state. Let's say I'll change the random state as 0. You know why am I doing that? Because I don't want my model to give higher, less training accuracy and more testing accuracy. So I'm running all. And yeah, this is awesome. Random state 0 and my problem is solved. You also try putting random state value in your code. You also try going over here and try putting the random state value 0 in your code. Areva. And try it out. We are getting good results. Okay. Is there a better way further? Right? If I say with random state 0, I am trying out the because the data is small. So 90 and 10 ratio, 90 and 10. So the latest results are this. I'll just paste it and let me run on. Am I getting better? 95, 92. No, 90, 10 is not. This is better, no? Okay, so I will try out maybe a ratio of 75, 25. 75, 25 is also not that great. Let me try 70, 30. 70, 30. 94, 95, not that great. So I think the best was this only. 80, 20 with random state 0. Restart, run all. This is the best one so far. But there are some other metrics. What can be the different value of random states? Now, again, if I say something, you will find it offensive, Manu. Just like last time you found it. And over there, you make me only responsible, right? So, because you are not attentive in the class, you held the instructor responsible for these things. That's exactly what you did last time, if you recollect, right? You wrote that all things in the feedback as well to tarnish my image. That's why I was a little upset on you in the previous course. You might have noticed that. Coming to your question, Manu, random state can take any number between 0 to 2 raised to 32 minus 1, although some of the common values are this. Though you have an almost infinite range to try, but if you go to Kaggle or any Google blogs or any YouTube or anywhere, these are the very common values which people try out. But of course, I mean, that doesn't limit our thing, but this should be more than sufficient. 42, 43, 100, 0, 1, 2, very common values. Whatever it is, whatever it is, there are no guidelines around it. The same thing applies for everything. Whatever thing I'm telling you is for the real time things only. I'm not here to talk about how it will happen on an academic project. The only difference over here is the data set is small, but the tips are all for the real time settings only. Cool. Okay. See now, the metric that we use. Hey, wait. Did we study the metrics like mean error, mean absolute error, etc. earlier during our earlier session? All of a sudden I recalled, did we study the metrics like mean error, mean absolute error, root mean square error, and all those things in our earlier class, earlier subject? So let's understand it. Now this will take almost half an hour to understand all the metrics. Now, see, we are going to understand what all are the metrics which are available for solving a regression problem. The first one is R2 score, but I am not discussing it right now. I am starting with the very first one, which is called as the mean error. Mean error is calculated as summation I is equal to 1 to n of y actual minus y I predicted whole upon n. So let's consider a scenario. So if I have, let's say, a line of best fit. Inside that, let's say these are the 4 points. So this is the actual point one, but the prediction will be here. This is the actual point two, but the prediction would be here. That's the actual point three. That will be the prediction. That's the actual point four. And this is the prediction. Let's assume that this is 4. This is 4. Let's say this distance is -4 and this distance is -4. So in this scenario, how do you calculate the total error? So the mean error can be computed as 4 plus 4 plus -4 plus -4, because 4 points are there, which is going to be 0 upon 4, which is 0. Yes, we can actually say that the mean error over here is 0. Let me consider one more example. If I consider one more example, uh, maybe like this. So let's assume that in this case, the actual is over here and the predicted is also over here. In this case, the actual is over here, predicted is also here. The actual is over here, predicted is also here. And the actual is here and the predicted is also here, which means mean error will be actual minus predicted, actual minus predicted, actual minus predicted, actual minus predicted, actual minus predicted. That was total. So here actual minus predicted is 0, 0, 0, 0 upon 4, which is 0 upon 4, which is 0 only. And that's absolutely correct. But something which I don't find very, very convincing in this scenario is on this line, if I say the error is 0, I can accept it positively. On this line, if someone says the error is 0, I am not ready to accept it. I am not ready to accept it. See, if you logically see, is even a single actual point on the predicted, are the actual and predicted same even one time? No. So how can the error be 0? In fact, every time I see a constant error, 4, 4, -4, -4. So this is kind of deceiving us. This is fooling us. Do you agree that this is not the ideal right metric? This is fooling us. And that was the problem with the mean error. So the very first metric which was invented was mean error only. But then slowly researchers realized this as a problem. So to solve this problem, which they see in the mean error, they came up with something which is called as mean absolute error. So the formula for mean error was very simple. I is equal to 1 to n y actual minus y I predicted whole upon n. Now the only difference is you will find the absolute of this. Earlier, you're doing actual subtraction, but now you're finding absolute. So if I consider this first example for mean absolute error, absolute of 4, absolute of 4, absolute of -4, absolute of -4, whole thing divided by 4, which is 16 upon 4, which is 4. That's convincing. And here, does it work or here it fails? Absolute of 0, absolute of 0, absolute of 0, absolute of 0, over upon 4, which is 0 upon 4, which is 0. Now, that's good. So, this is good. So, mean absolute error is definitely better than the mean error. Are you all convinced? Are you all convinced that mean absolute error is better than the mean error? So, that's my example A. That's my example B. I want to take one more example C. So, here, what I do in example C is I want to consider one more line. The actual and the predicted are having a distance of +1 and +7 respectively. And on the negative side, I'm assuming this distance to be -6 and -2 respectively. So therefore, in this case, you can actually say, if I have to calculate the mean absolute error in this scenario, absolute of 7, absolute of 1, absolute of -6, absolute of -2, whole upon 4, 7, 8, 9, 10, 16, which is 4. Now I am not happy with this. Now you might be thinking that now what is the problem? Everything looks good. No, everything is not looking good. I'll tell you why. If you look into the example number B, it is saying that the total error is 4. If you look into example number C, it says that the total error is 4. Now, if you ideally see and observe, the lowest or the highest value over here is +4. The lowest value over here is -4. And if you see over here, the highest value over here is +7 and the lowest value is -6. So if I kind of put this over here, I can actually say, so do you see that the distribution of the error of blue box is higher than the pink box? So it is obvious that the error in the second example should be higher because the spread of the error, the variance is wider. And therefore, the mean absolute error is expected to be higher for the next example, but it is not. Are you all convinced? That is exactly where we see the drawback. Right? Yes. So, what I do over here is fourth one. I propose to you the next one, which is because normal is not working, we absoluted. Because absolute is not working, we are going to go for the mean squared error, which is summation I is equal to 1 to n y actual minus y high predicted whole square upon n, which means if I'm talking with respect to example B, my mean squared error will be 4, 4 minus 4 minus 4. 4 square, 4 square. Take out your calculators. I need your help. Tell me the final answer. But now you'll definitely need calculator. 7, 1 minus 6 minus 2. This is 22.5. Perfect. Now we clearly see that this is also perfect, and we see this is also perfect. But I see one small issue in the MSE. If you look into the example, the lowest value is -4 and the highest value is +4. However, because we are squaring every value, the total error has gone exponentially up to +16. This looks little intimidating and sounds like the model has a very huge error, which ideally is not. Because we squared, the results have gone exponentially higher. The same can be seen for example C. Therefore, now I propose to you the next metric called as root mean squared error. Root mean squared error. And the idea to calculate that is very simple. It is nothing but calculate mean squared error and obviously go for the square root of it. Simple as that. So if I talk about example B and if I talk about example C, example B, RMSE will be square root of 16, which will be 4. Second one, you will tell me, calculator experts, 4.74. Yes, now all these values are quite well in range. That's perfect. So root mean square error is one of the best metric. What is the best value of what is the best value of RMSE that I can get for any machine learning problem? What is the best value? Best value. Guess. Ah, 0, right? 0. Sometimes you try changing your random state, you try changing your train test split, you try changing the machine learning algorithm and many other things. But the value of RMSE that you get, yes, I'm not bluffing, but the value of RMSE that you get is 12,000, 11,232, 10,000 something. Sometimes you get 14,000, sometimes you get 19,873. So now, in such cases, you may have a feel like, oh my God, I'm trying so many things. When Darshan sir showed us an example, he showed us the values come as small as 4.744, but I am getting so big values even after taking the square root. That means I am doing completely wrong, and the answer is not so. You may experience such things as well. So I propose to you the next metric, which is called as R2. I propose to you the next metric, which is called as R2. R2 stands for R2 only, residual square. So let's talk about what is, we can say now, what can we do is, let's say, mm, I'm just looking for some smart solution, and yes, I'll share the link of this video. It's good. Everything is nicely written. Why should I unnecessarily invest a lot of energy in writing? And let me focus on the explanation. So what is R2? R2 tells, listen to me very carefully, then this line will make sense to you. R2 tells How much important is an independent variable for predicting the dependent variable? Like for predicting the sales of ice cream. For predicting the sales of ice cream, do you agree that temperature is very important? 100% you agree to that? Temperature is very important for predicting the sales of ice cream? Yes. Now, what is the usual qualification of the person who sells the ice cream? What is the usual qualification of the person who sells the ice cream on the street? Ice cream le lo, ice cream le lo. With that, right? Maybe not even educated, below graduation, maybe primary school. Yes. Now I tell to that ice cream wala bhaiya, move. I am a PhD, highest qualification. I am the person with the highest qualification. No one is more qualified than me. You move, I will sell the ice cream. So, will you come to me for buying the ice cream because I'm a PhD holder, and you will not go to the person who is just a uh, primary past person or primary fail? Will you consider the, oh, Darshan is PhD holder, let me buy ice cream from him and not from that guy because he's not even educated? Do you take a decision like this while buying your ice cream? No. So can I say that the education level is not a very important independent variable for predicting the sales of ice cream, right? Yes, that's exactly what we have to understand over here. R square, R square, it represents the proportion of variance of the dependent variable that has been explained by the independent variable. How much variance of the dependent variable is explained by the independent variable is R square. In simple words, it is the goodness of it. So it gives a measure of how well unseen samples are likely to be predicted by the model through the proportion of explained variance. The maximum value of R2 is 1 and the minimum value is 0. So if you are getting for some reason R2 of 0, that means the independent variable is just not important for predicting Y. Zero important. And if I am getting the R2 as 0.80, that means that independent variable is responsible for causing 80% variance in the dependent variable or 80% effect in the dependent variable. That's the formula for calculating R2. We will be exploring that also. Right now, you can just have a look at it. It says Y actual minus Y predicted. This is like AI and PI, which I was writing. Actual and predicted. This is again actual, and this is the mean of actual. So let's say there are 10 values in the actual. The average of that is Y bar. It's not Y hat. It's Y bar. Mean. It's the mean of actual. That is what we see in over here. Let's go ahead. Now I say, let's look into the example. So if I say my R2 is 80, that means 80% of the increase in the ice cream sales is due to increase in temperature. So let's add another useless independent variable, which is the education level of the worker. And when I add education level of the worker over here, the R2 increases from 80% to 85%, indicating that if Darshan goes and sells the ice cream, then the ice cream sales will increase even more. then the ice cream sales will increase even more. And that is what is the thing. Now, is that correct? So, that is the drawback of R2. So, what they say is here, this is one limitation that it increases by every independent variable added to the model. That's misleading. Sometimes variables might be useless with minimal significance. So adjusted R2 overcomes this issue by adding a penalty if we make an attempt to add independent variable that does not improve the model. Adjusted R2 overcomes this. Now, how is that formulated? That is formulated again with the help of some statisticians who proved this. We need not get into why, but it is nothing but adjusted version of R2. So if you see the formula, 1 minus R2, which we calculated earlier, n is the number of rows, n minus k minus 1, k is the number of independent variables, number of rows, number of independent variables. That is what we have. Now, the advantage of adjusted R2 is if you are adding useful independent variable, adjusted R2 increases. If you are adding useless independent variable, adjusted R2 decreases. Exactly, yes, Sandeep. That means there is a bias getting added because of the R2, and hence adjusted R2 is what has to be recommended. That's absolutely yes. So now that you understand this, so let us now get into this. So what will I do is copy this link and come over here. Perfect. So that's the link that we have in over here. For some reason, if the link is not clickable, I'm also adding the name of the video. I don't know, in case if if the link is not clickable for some reason, you can actually search it. No, I'll do it here only for you. Let us consider the following things. So extract the values of the table so that I can directly copy paste it into Excel sheet. So now this is what I have. Awesome, right? So ChatGPT is very good in these all scenarios. अरे तुझं बघतोच मला वाटलं काय पाहिजे का तुला? So this is what is the thing. Now I need to calculate the mean error. Now see, this is TB. What is TB? TB is nothing but independent variable 1. This is the independent variable 2. This is the independent variable 3. This is the dependent variable. And this is the Y predicted. This is nothing but the Y predicted. So this is what we have. Now what we have to do, we have to calculate the mean error. How do you calculate the mean error? The way you calculate the mean error is over here by using the formula which I showed you over here, y actual minus y predicted upon n. So how do I calculate n? Well, let me write down over here. What is the value of n? N is nothing but the count of this. 5 values are there, so n is 5. I'm just computing it from a formula, but n is 5. This is n computed. Okay. So y actual minus y predicted. So here I say I want to compute y minus y hat. How do you do that? Equal to 22 minus this. And in this way, we completed all of these values. And what is going to be the mean error? That will be the total of this. So what is the total of this? So total of this will be sum of this F2 to F6. That's correct. And mean error will be is equal to this divided by n. So the mean error in this actual versus predicted is 0.02. Did you all understand? I'm using the same formula which I taught you just a couple of moments back, because we are going to work on this case study as the next problem statement. This is the actual case study consisting of 200 rows where you have not one independent variables but multiple independent variables. Then we have to calculate the mean absolute error. So how, for that, I need to calculate absolute of y minus y hat. So y minus y hat is already computed. I will have to calculate absolute. So use the absolute of this y equal to absolute of this. And then I'm going to take it down. Then here it's going to be is equal to the sum. So sum of these all values. And this is equal to this divided by. So the mean absolute error in this case came out to be 1.4 to 7.1 is the total of the absolute. Divided by 5 is the value of n. Tell me if you understood it or not. It is same thing which I showed you. I have just converted it into the Excel file. Then we have to calculate mean squared error. So for mean squared error, we have to first calculate the square of it. So I say it's going to be this multiplied by this. That's exactly what I want to do in the squaring. So this is going to be is equal to this multiplied by this only. And that's how I am getting all of these values. Here is where I will say I want to find the sum. And here is where I say this phi. And this is what we call over here. So this is the mean error. This is the mean absolute error. This is the mean squared error. And obviously, in the same way, I can calculate the RMSE, which is equal to square root of this. And this is the RMSE. So that's essentially what we understand. So all these metrics are populated so quickly. Are you all with me? Did you understand how all of these metrics are computed right up to MSC? And if I went wrong anywhere in the calculation, do let me know. So the RMSE on this model is 1.68. We know the formulas for it, so that's not a problem. We have to go for formula for R2 score, which is can be easily represented like this. And that's the formula. Now let's get into the calculation of R2. So what all things we need for R2? Let's keep it accessible. I need y actual minus y predicted ka square. So y actual minus y predicted is there. Uska square is also there. So I think numerator is there. Numerator ka total is already there with us. Am I correct? The numerator ka total, which is 2.83. So can I say this numerator is 2.838? This is the same y actual minus y predicted 2.838. Right? Sandesh, that was very fast. Way more faster. Please slow down. Okay, no problem. So now you can take a break by the time I'm done. So this is what we got. And then now it is time for us to compute y actual minus y bar. I need to calculate y bar. Y bar is nothing but the average of this. So my y bar is going to be is equal to average. Oh, sorry, is equal to average of, yeah, that's correct, 18.4. Now what will I have to do? Y actual minus y bar. That's the first thing that I have to do. So is equal to y actual is 22 minus y bar is this. That's correct. But as and when I translate it down, right? So here I got the value. But next time when I scroll this down, this next value it will select is 2010, and after that the next value it select will be blank. So this time it can go wrong. Did it do the referencing properly? No. So my y bar should not change. I have to lock this value. What is this? This is D7. So I will have to put a dollar over here. So lock this value, right? Yes, you know that, right? So every time it is 22 minus 18.4 is this. 10 minus 18.4 is this. 15 minus 18.4 is this. So it's essentially this minus this 3.68. This minus this one. This minus this one. This minus this one. This minus this one. So we have got that. But what we want the square ka total. So I will have to calculate the square of this. So this star this. I have to calculate the square of this. So equal to this multiplied by this. And then I find the square. And what I have to do, I have to find the total of the square. So total of that is going to be sum of these all values. So see, this is my numerator, this is my denominator. I will specifically, let's say, because I want to calculate it over here, I'll put it over here. I don't know why it's not moving. Alright, just ticked or what? No problem. I'll write here only. I can at least scroll it, right? So I have got my numerator. I have got my denominator. What is my numerator? This is the numerator 2.83. So I say is equal to this, just for convenience. What is my denominator? My denominator is this. Then I say my R2, how is that calculated? Is equal to 1 minus numerator upon denominator. Numerator divided by denominator. And it is 0.97 for this model. Did you go behind now? But I think it's correct. Everyone followed this. Everyone followed this, right? Yes. So R2 is also computed. Now we have to compute adjusted R2. That's the last formula. That's the formula. Right click, copy image. And you know, these metrics are not only for linear regression. Any regression algorithm you study, the same metrics are available. That is the reason we are spending so much time on it. Any machine learning algorithm which is of regression type will demand the use of the same thing. Yes. So now to calculate adjusted R2, we need R2 only. So here once again, let us calculate the numerator. And we will also calculate the denominator. So what is numerator? Numerator is equal to 1 minus R2, which is this, multiplied by n minus 1. What is n? N is this 5. N is 5 minus 1. So we got this. So I just applied 1 minus R2, which is this, into n minus 1. N is 5, which we had already saved here. I also have to find P. P is the number of independent variables. So I know there are three independent variables. So I will just count this now. And count of this, oh, it's count has to be only done on numbers, right? So I can say count this three. And yes, let us check it, no problem. 1 minus R2, 1 minus R2 is nothing but L15 into, is that into? Yes, into what? N minus 1. N is 5 minus 1. Looks like correct only. Numerator, okay, here. Numerator is, oh yes, total, not this. That's correct. That's correct. So 0.89 should be the value. That's correct. I selected this by mistake. This is the total. Here we have the same numerator. How do you compute the denominator? N minus P minus 1. So what is N? 5. Minus P is this. Minus 1. N minus P minus 1. And this is what I have. So adjusted R2 is equal to 1 minus numerator divided by denominator, which is 0.5. And I think again there is something wrong which I have done over here. Someone please check or it's correct. You have the access to the sheet. Here I say mean absolute error, mean squared error is what we are trying to look into. So now I say from sklearn dot metrics import mean absolute error, mean squared error. This is exactly like this. From sklearn dot metrics import, from sklearn dot metrics import. These two, here it was R2. So we imported this. Then I am going to say the mean absolute error on train is give the actual and predicted. The mean absolute error on test give the actual and predicted. The mean squared error on train give the actual and predicted. The mean squared error on test give the actual and predicted. Then the root mean square error on train is square root of RMSE of train. Iska square root is this. And this is the one. And then let us print the evaluation metric. This is the one. And then in between, I want to add a separator. Then RMSE, no, mean squared error. And then root mean square error. So you can see over here the mean absolute error, mean squared error, and the root mean square error. You don't have to actually calculate any of these values. I showed you everything in the raw way, but you now know internally what is happening. Can I assume that you have that confidence in how these metrics are coming? Right? It's not magic. There is a math behind it. That's it. And we know among this, the metric that you will finally refer will be only RMSE. You will not go to MAE and all. They have drawbacks. You only refer RMSE. And the R2 or adjusted R2. So now in this, we saw that the R2 is this. This is also what we have studied. I want to evaluate it by calculating adjusted R2. Now we know what is adjusted R2, and this is the formula for calculating it. We have already got that. So the first thing that we need is the number of rows, n, and we also need the number of predictors. So how many number of rows are there in the training data? 25 rows were there. We divided it into 80-20 split. So training data, how many were there in 80-20 split? 20 rows, right? Yes, 20 rows. And testing 5. That's exactly how we divided 20 and 5. So I will be having to calculate adjusted R2 on train and then on test. So for that, my n is going to be x train dot shape of 0, which is the number of rows, and this is the number of columns. And this is how I calculate it. And similarly, after this, now, is that correct? Let me just see. Now, my n is going to be for x test. Of course, my P remains the same, but I will still take it from X test and I apply the same formula. You don't have any direct formula over here. Remember, you don't have any direct formula over here. So ये आपको खुद ही करना पड़ेगा. This is the raw logic that you have to implement. So 95 became 94.88. 94.54 became 92. Still, it is a good model, and we can actually say ending to this. So, as a note, I say in industry, the trusted metrics for evaluating the model are R2 score, adjusted R2 score, and the third one is the root mean square error. So I would still recommend you to go ahead with these three. Try out all. I mean, anyways, R2 is by default calculated. So it is recommended that you try out everything. It is recommended that you try out everything. As simple as that. We are going to get started with a multiple linear regression problem. So, what is good R2 or bad R2? See, we discussed that also, no? If you remember, any metric here, the same rule applies over here, Amitosh. Absolutely same. A good metric, even if you consider for R2, test R2 must be at least 80%, and the train minus tests must be less than 5%. In classification, when you get an accuracy score also, there also the same rule applies. So this is the bare minimum. Sometimes you don't even get this. In banking domain, getting 70, 72 itself is considered as a big achievement. We will discuss all those scenarios, but yes, I mean, on a very higher side, this is what is accepted. We are talking about this data set. So now we have three independent variables, TV, radio, newspaper, and there is one dependent variable, which is the sales of it. So if you want to download this data, I am sharing this link with you. You will just right click on this, save as, and so we have this data. And let me also put in to our day 3 folder. File not found. Surprising thing. I have folded location change. Yeah, it's uploaded to our day 3 folder as well. And now let's get started. So I'm creating a notebook now. Multiple regression using this, and how many are we having? 50 in the class. Okay. Okay, now let's get started with this. So this is going to be the problem statement. So then I'll explain you what all things we have in the data set. So number one is importing the necessary libraries. So I import NumPy, Pandas, then I import Matplotlib, import Seaborn, then I also import warnings, and I say warnings.filter warnings. So this is going to ignore the warnings. Then my data frame is equal to pd.read.csv, and the name of the data set is advertising.csv, and I say loading the data, assuming it is in the same directory, and let's look at the shape of the data set. So I say over here, shape of the data set is df.shape. So I understand that there are 200 rows and 5 columns. And then let's look at the first few rows, and I say df.head. So now, first and foremost thing we see over here, this is what is the data set. You see, there is one additional column which is just not required, right? And basically what has happened is this is 0, 1, 2, 3, which is the default indexes. And basically the data set is such that they had created column number 1, which is serial number, then column number 2 for TV, then the radio, then this newspaper and sales. So this is the serial number column. Now serial number is not useful for predicting the sales, so I am going to ignore it. So how? So I will first of all copy this. See, this name of the column is little odd, right? Don't type in such cases. Always select and copy this. Control C, done. And then I say that the column, this is just an index column and we can drop it. So I say df.columns equal to this. I can drop it. That's one way I can drop it, or I can drop it using the access. So I can say df dot drop, and then I specify the column to be dropped, access equal to 1, in place equal to true. Anything is okay. I will say once again, and let us look at the first few rows of the data set. And this is what we have. Now, well, coming on to the problem statement. So over here, I want to say that the data set contains information about the advertising budgets. So basically, we have data set of 200 companies and how much money have they spent on advertising. That is in $1,000. So let's say company zero, whatsoever be the name of the company, that's not given to us. So this company zero has spent $230,100 for advertising on TV, $37,800 for advertising on radio, and similarly, it has spent $69,200 for advertising on newspaper. And based on that, they were able to get a sales increase of $22,100. Okay. In this way, we have data of total 200 companies. So I say the data set contains information about advertising budgets and their sale. We want to predict the sales based on the advertising budget. So the thing is, after this, uh, if I look at the column description, then you have TV, which is the advertising budget for TV in thousands of dollars. radio is there, newspaper is there, and you also have sales in thousands of units. So how much sales? Now here they are saying it's in thousands of units. You can also consider the sales growth, right? That's correct. So this is what we see in over here. Algorithm. So we are going to use the multiple linear regression algorithm to predict the sales based on the budgets for TV, radio, and newspaper. So obviously, I'm using the scikit-learn algorithm, and in this particular thing, the equation is going to be sales is equal to beta, or I can say C plus, I don't want the M1 into TV plus M2 into radio plus M3 into newspaper, right? This is what is going to be the function. Now, the broad steps to solve our problem are, first, we'll be importing all the necessary libraries. That's obvious. Loading the data set. We will explore the data set. Explore the data set is mainly to see if there are any missing values, outliers, etc. And also to check if there is linear relationship between independent and dependent variable. After that, we do the train test split. Right. So train test split is what we do. But after that, actually, I should say that I will do encoding of the categorical variables, if any. Now you tell me, looking into this data set, do you have any categorical variable like gender, qualification? No. So it will not there. But if it was there, then the step number 4 is that. And you remember the dummification that we learned in the previous course, right? Yes. So that dummification, so that technique gets applied in this scenario. And then after that, so you should always, whatever I'm giving you right now, these steps are valid for any machine learning algorithm. Any means any. Therefore, I'm taking the efforts to write it down. So you might see some people who are not following these steps. So there are so many resources available. Do not follow the steps which they are saying. These are the only steps which will 100% give you the right answer, right? So eyes closed and you can follow the steps. So what some people do, that also I will tell you in this notebook only. But first of all, let me tell you the right approach. And once I'm done with the right approach, I will tell you what other people's do and why you should not do that. Why you should not do that, but not immediately right now. So then after this, you do the train test split, 80-20 split. Then after that, you are going to get into scaling of the features. You remember, we studied min-max scaler, standard scaler, which is mainly for shrinking the values. Yes? Ha. So here you do the scaling of the features. This scaling will happen if there are columns which are numerical in nature. Obviously, numerical columns will be there, and you will have to go for scaling. Here I say you'll go for scaling the features, but I think I need to mention it more properly. Rather than I'm saying just scaling the features, you should say scale the independent variables. Only independent, right? Will not scale the dependent variable. There are some people who scale the dependent variable as well, which is wrong. Why is it wrong? When we come to that step, I will justify, but that's why I'm writing down the perfect approach, because many people do many different ways. So when you see internet, you will see all of this unnecessary noise. So you should always follow the steps which I have given you. Then we say, after that comes the modeling. So you over here apply multiple regression algorithm or any other algorithms of your choice. Then you evaluate the model. And once the evaluation is done, you predict the model, right? So you predict on the test data set. Actually, first you predict and then you do evaluation. I don't know why it's recommended that. First to make predictions and then you evaluate using the metrics as we have. And then you can visualize the result if necessary. That's optional. That's why I said if necessary. You can even save the model locally on your system because usually you will not share this notebook with the client. You will share the model with the client. You remember I had shown you one deployed version. So you do that and then you document the findings and conclusion because with the stakeholders, you will have to share it. And then share the results with the stakeholder if necessary. And then we can go for deploying the model if necessary. So broadly in our course, most of the times we will be going from step number 1 to step number 9 because obviously every project we are not going to deploy. In fact, deployment is not even there, but I will take it. It's not even there, but I will take it. So here, right, so these all are the broader steps that we do it. Then now I think we are good to get started. In fact, today I'll show you the deployment as well. I think ideally it's not the right time to show, but I think you all are smart enough and you will understand it. So I don't think so that's going to be challenge because I have seen, right, you are good enough to pick up the things. It will be optional. It is not there in our syllabus. Which one? Step number 14, it's not there. Step 14, but we will do it. It's like, take it or leave it. If you don't understand, ignore it. But I'm pretty sure you will understand. And it is important, very important. Usually, deployment is something which is taught once the entire machine learning syllabus is over. I'm teaching you at the start only because I'm confident you will understand. And then, any model that we create going forward, you can think of deploying as well. So that's an advantage that you get over here. So our step number 1, 2 is done, right? So I say step 1 and 2 are already done above. Let's get into step 3. The first is we are checking for missing values. I know there are no missing values, but I will just say df dot is null dot sum dot sort values. Don't forget that. And there are no missing values. So the insight over here is there are no missing values in the data set. That's good. Next, I say, let's look at the data types of every column. So I can say df dot d types. Everything is a float data type, so there is no encoding of the categorical variable required. Next, I say, let's look at the information about the data set. So I see there are 200 rows in the data frame, 4 columns. Non-null counts 200, so no missing values. All are of the float data type. Memory usage is this. That's also good. Then I say, let's look at the summary statistics of the data set. So I just say df dot describe. I don't like this print. Now it is better. Now, if you look at this, when you look at this data set, let's say into the average investment, most of the companies prefer to invest heavily for advertising on which medium? and which they think is the least important for advertising? Radio. You remember this. Don't forget this. Huh? You will have to do this analysis step by step for every column. Here there are only three, but in real life there may be 100 as well. So obviously I will not consider a data set which has 100 columns, 200 columns instantly at the start, but you will have to consider this at a larger scale. Always remember this. So even if you look at the minimum investment, do you still observe that the minimum investment is still the highest on TV and least on radio? And the maximum investment is highest on TV and the least on radio? Yes. Let us look into the sales column, right? Yes, sales column, if you see, average sales is 14 and the median is 13. So more or less looks like sales column must be normally distributed. It looks like sales column must be so. Now the next thing is we are now trying to I'll just make a note of this first of all. So dataset contains that I don't want. I see that most of the companies have higher advertisement budget for TV as compared to radio and newspaper. The average sales is this. The lowest advertising budget is for radio. Okay. This is what we understand. Now, after that, now I say, let's look at the relationship between the features. Features are nothing but the independent variables and the dependent variables. So how is TV related to sales, radio to sales, newspaper to sales? So I am going to first of all say features is going to be, I'll just make a note of all this. So I'll say df dot columns are this. So features are these. And I say for feature in features. For feature in features, I'm going to go for SNS dot joint plot. X-axis will be the feature, y-axis will be the sales, and data is going to be the DF, and kind is equal to regression. So it will be plotting a regression plot. I'll be giving it a proper title where I can give the font size as well. And I will also say, let me give the X label, Y label, and I'll also look at grid, and grid I said true, and alpha I'm giving at 0.3, plt.tight layout and plt.show. You can see one below other. So first of all, I can see the relationship between TV and sales. Look at this, TV and sales. So we clearly understand that as the investment on TV increases, the sales increases. Huh? We clearly understand as the investment on TV increases, the sales increases. Okay, then if you look into this, do you see the similar strong relationship between radio and sales as compared to TV and sales? Which is better? TV is better or radio is better if you look at relationship with the sales? TV. Yes. Okay. And if you compare between radio and newspaper, which is better? Radio is better? Hi, I mean, if you look into this, look at the line also, look at the points also. And this looks like a dummy line. Ideally, there is no linear relationship as well. And a radio is better. So I will just make a note of insights from the above plots. There is a positive relationship, or there is a strong positive relationship between TV and newspaper, moderate between radio, and it is very weak in between this. So this indicates that TV is the most significant variable for impacting the sales, followed by radio and newspaper. That we have got this. So I created this very quickly. You can actually, if you want, you can also go for a pair plot. It's your choice. SNS.pair plot, and let it come. So I selected only 3 features over here, but I was planning to do this. I was planning to do this SNS.pair plot of DF. So I'll just open it separately. Yes. Yeah, I was planning to go for this. So if you see carefully, uh, sorry. Yeah, if you see, yeah, this is the figure finally. Little up I'm taking. This is TV versus sales, radio versus sales, newspaper versus sales. We clearly see that now there is one very, very important funda which I want to talk about. Very, very important funda. See, uh, I'm little bit going off the topic, but it is related to the topic only. I'm little bit going off the topic, but it is related to the topic. I'll tell you why. Now I am discussing a concept which is called as multicollinearity. So what is multicollinearity? So I'm still with that topic only. So now multicollinearity basically means that there must be a good amount of correlation between independent and dependent variable, but there must be least amount of correlation between independent and independent variable. I'll explain you what I mean. Let's consider an example. I say a simple layman example. So let's say I have some work in Pune. I stay in Mumbai. Okay. So let me start by saying that I stay in Mumbai and I have some work in Pune. And hence, I will be traveling to Pune. Okay. That's one thing. Now, for travel, I prefer to use my own car. For travel, I prefer to use my own car. But I have 3 cars. Let's say one is my own car. Second is I can also take out my wife's car, and I also have my dad's car. So I have 3 options. And of course, I have the access to any one of this car and I can take out any one of this car. So now let's assume Okay, that all of this, I can take out any one of this car. So what I decide, you tell me whether I'm smart or not. Okay. So what I decide is, decision is, I will take all the cars for my work. That to how? That to how is my car, I will drive it myself. My wife's car, I will hire a driver to drive it. My dad's car, I will hire another driver to drive it. Now, there is a question. Is my decision correct? I have three cars. I have some work in Pune. So I take out all the three cars. I will drive my own car. And other two cars are been driven by driver. We all the three cars go from Mumbai to Pune, do our work, and we come back. So is my decision correct? Just a personal logical question. Imagine you to be my in my scenario, and if you have to take this decision, would you take out all the three cars, or do you think it's not a good idea? No? Why? What is your problem? What is your problem in me taking out all my three cars? These are my cars. What is your problem? Only one car is needed. Only one is enough. Very nice. Right? Only one is enough. Then why to take out the three cars? Why to hire the driver, etc., etc. things? It is uneconomical. Let's say I have a lot of money. What is your problem? But then still I am unnecessarily creating pollution on the road, adding on to the traffic. And the most important thing is, as you all said, it's not needed. If I say I have to take out my entire family with me, then at time one can still adjust that, okay, fine, entire family is coming, so probably it is needed. But in this case, we clearly understand that it is just something which is not needed. So now let's try to map it. So obviously the answer is no. I should have taken one car only, because all the cars are similar and they will take me to the same place. Similarly, in our data set, we have no, and forget about that. So now you consider that I say now let's assume that my Y is nothing but my Mumbai to Pune travel, right? So that's my target. My target is traveling from Mumbai to Pune. And then for traveling from Mumbai to Pune, I have the first independent variable, which is my car. Second independent variable is my wife's car. And third independent variable is this. The relationship in between all these are linear, let's say. But we realize that x1, x2, x3 are highly correlated with each other. And hence we drop, hence we realize they're highly correlated with each other. And this is called multicollinearity. So multicollinearity can lead to the model overfitting, that is, model mugging up the data. So what do we see? In this case, we have to drop, or no, not drop, we will consider any one of the cars and drop the rest. We will consider any one of the car and drop the rest. And that's how we handle multicollinearity. So basically, what does multicollinearity say? That if independent variables are correlated. So what do you mean by independent variables are correlated? The effect which this car will have for achieving Mumbai to Pune travel, the same effect will be by this car, the same effect will be by this car. Now, if I say that I am having a BMW, but my wife is having Honda City and my dad is having a Swift car, then the things are different. Obviously, you will say that no, of course, you will take out your BMW in that scenario. But if all the three cars are same, assume all of them to be Honda City. So that's what we have to assume, right? In this example, don't assume that all the three cars are different. So what I want to say is, whatever effect your X1 is having in Y, whatever effect your X1 is able to produce in Y, the same effect your X2 is producing in Y, and the same effect your X3 is producing in Y. So essentially, we understand that if all of them are producing the same effect, then we can choose any one of it. So, just like if you are going from your home to school, and let's say you usually carry one rough book for writing the things, whatever the teacher is giving you, right? Not subject specific. Then why will you carry three rough books? You carry one rough book or you carry three rough books. It does not have any sense because three rough books will just add on to extra weight. But at a time in a school, you are not going to complete with one rough book and start with second and start with third on the same day. Impossible. So it's not required. Basically, you are unnecessary carrying extra luggage by carrying these two cars because the effect is the same. So they say that why are you unnecessary carrying all the three? Carry any one of it. If you carry all the three, then it is of no use. In fact, it is more uh, uneconomical, as you said, because it's not required. And it's like telling the model that, okay, you want to predict the sales, you use TV also, you radio also, newspaper also, assuming that all of these are having high multicollinearity. So it's like, why? So it's like you're teaching the model same thing again and again. Model wants every time different relationships to learn, and that is what we see over here. So this is multicollinearity, and we have to check whether our data has multicollinearity or not. And for that, we will be plotting the correlation matrix. So this is the correlation matrix. It's nothing but what did we do? df.cor. So entire correlation matrix comes. I printed the correlation matrix and this is what I visualized it here. You can see the values are also the same 0.05, 0.35. You can see the same thing 0.05, 0.35. So heat map. Yes, sorry guys. So I was saying, I'm sure you might have looked into this. So if you see over here, which TV, radio, newspaper are the independent variables, sales is the dependent variable. Similarly, here as well, TV, radio, newspaper are the independent variables. Sales is the dependent variable. Independent should not be having relation. That's what we said, right? Independent should not be having a high amount of correlation. This is essentially what we say in over here. Sorry, yeah, here. Independent should not have any kind of correlations. So then I say So here if you see TV and newspaper, independent and independent, correlation is very less. What is the value of correlation lying between? What is the value of correlation lying between? Yes, -1 to 1. What they say, what they say is if the value of correlation, I'll write it down, right? When do we say multicollinearity exists? If the correlation between two independent variables is greater than 0.7 or lesser than -0.7, then we say multicollinearity exists. This is the best way to identify if the correlation between two independent variables is greater than 0.7 or less than -0.7. So always remember this. So looking into this, TV versus newspaper, very close to zero. Radio versus newspaper, there is a correlation which is positive, but it is not above 0.7. And then this is TV versus radio. You have the newspaper correlation, but it is not above 0.7. So we don't see any multicollinearity. These are repeated values. I hope everyone knows that these are repeated values. Yes or no? Yes. Did I teach you how to mask the upper triangle of the heat map? Did I teach you how to map the upper triangle of the? Yes, very nice. Chalo, then no problem. I'm not masking it, just I wanted to show you once. Very good. So I realize, I say, insights from the correlation matrix, there is a strong correlation between TV and sales. So, yeah, that's what I forgot to tell you. So TV and radio are having a very high value. So there we see multicollinearity. Are you seeing that? TV and radio, we see multicollinearity. Agreed? Thank you for being my blind follower. Multicollinearity is always between two or more independent variables. Yes. Independent, dependent, no. Between X only. In fact, in linear regression, between independent and dependent variable, we want the correlation to be as high as possible. In here, what did we say in this figure? We want this between independent and dependent to be as high as possible. This is little less, we were unhappy. And this is even more less, we were further more unhappy. So correlation between independent variables, if it is high, that is above 0.7 or less than 0.7, then it is multicollinearity. So multicollinearity is always between independent variables. So that is what we say. Node multicollinearity is always between independent variables. Very important. So there is a strong positive correlation between PV and sales, and that is 0.78. Moderate positive between radio and this, and weak positive between this. Then there is no multicollinearity present between TV, radio, and newspaper, as the correlation values are below 0.7, or I would say are between minus zero point 0.7 and plus zero point 0.7. So we don't see that. Okay. But this is what is being done so far. I just add some notes around this, some technical explanation because I explained it in layman terms and whatever I understand. So multicollinearity is a situation in multiple linear regression where two or more independent variables, and not only here, it's in every algorithm, not necessarily here, where the independent variables are highly correlated with each other. This means some predictors carry redundant information about the response. Now, see, this concept applies for every machine learning algorithm. So, don't consider this problem that we are only discussing about linear regression. No, this applies to every ML algorithm. You have to check multicollinearity is considered to be a shrap, a curse in machine learning. Okay. Then, when multicollinearity is present, it is difficult for the regression model to accurately estimate the relationship between predictor and the dependent variable. So, why is it a problem? Because it causes instability in the coefficients. Small changes in the dataset lead to large changes in the estimated coefficients. And it inflates the standard error of the coefficient, making it statistically insignificant. Statistics. It reduces interpretability of the model because you can't really tell which predictor is truly responsible for the changes in the target variable. And the third one is it may also lead to overfitting in some cases. How is it detected? So you have correlation metrics that we use. Number one, and I said preferably values are below plus minus 0.7. Second is variance inflation factor. This is what you will learn in the next case study. It's a very nice metric, variance inflation factor, where we expect the value of the VIF to be less than 5. And VIF is just calculated. How is it calculated is a later part of the story. But VIF, let me tell you that it is simply calculated using your R2. So once you have the R2, VIF is nothing but 1 upon 1 minus R2. We will see that in the next case study. Condition number, which is the ratio of the largest to the smallest value. We will not be looking into that. That's not very important. And eigenvalues is also not important as of now, at least. Let us look at some of the acceptable values. See, everywhere it is 0.7. In marketing for sales prediction, TV, radio, newspaper spend. Drop or combine highly correlated channels. In finance for credit scoring, where you have income, saving, investment amount, you remove or reduce one of the correlated financial indicators. In manufacturing for the production rate forecast, for predicting that, you have machine hours, labor hours, power usage. So you keep only the most significant one and remove the unnecessary one. In the retail for customer spend modeling, based on loyalty points, purchase frequency, and recency, you use PCA. PCA is the unsupervised learning algorithm that we will be studying. I had talked about it earlier. And for logistics, where you are predicting the delivery time prediction based on independent variables like distance, fuel usage, travel time, you expect the value to be less than this. Or I can combine these metrics together. So how are decisions made in practice in a real-time problem? Correlation between predictors, let's say, is less than 0.5, we are good, no problem. But if it's moderate, right? Because every time I said, between minus 0.7 to plus 0.7 is acceptable, but it depends on the use case. Sometimes maybe 0.6 is also not acceptable. So in such cases, you may have to carefully inspect the business rule and take your decision that is 0.55 acceptable, or should I go with what Darshan sir said, 0.7? Well, that rule is a very generic rule. It can be little bit tweaked based on the application. Always remember that. But anything above 0.7, it's definitely high. So over there, you may have to remove that, and PCA is one such algorithm which can help you to remove the multicollinearity. VIF value, as I told you, it must be compulsorily below 5. If it goes above 5, there is a problem. And high collinearity is also not advisable for interpretability. Let's consider an example for marketing spend. If TV spend and radio spend are, let's say, highly correlated, let's say, example, then drop radio and build model using any one of it. In manufacturing, if there is a machine A, runtime and power consumption having a very high correlation, then keep machine runtime and drop this, because it is the runtime that drives the production. This is very important. See, logically, if you have to select for a machine A between two independent variables, runtime and power consumption, I said I will keep runtime because runtime drives the production and not the power consumption. So when I say that I have three cars and I have to choose any one of it, I will choose the one logically. What is important for me? Because this is what will be used for prediction. Just like in retail, customer visits and purchases are correlated, right? How many times a customer visits the website and how many times he purchases something. So how many times am I visiting Amazon.in and how many times am I purchasing from that? The more I visit, the more I purchase. Agreed or not? The more I visit the website, the more I purchase. If I am visiting Flipkart less, then my chances of purchasing from Flipkart are also less. Yes or no, friends? The more you visit a website, the more are your chances of purchasing, right? Yes. So if there is a multicollinearity between the visits and purchases, which one will you keep? They say keep both, as visits and purchases capture separate aspects of the customer behavior. So I am saying do not remove it. I am saying do not remove it. It's a business decision. Remember, it's a business decision. Multicollinearity does not affect the prediction accuracy directly, but it affects the model interpretability and stability. So if your goal is forecasting, you may tolerate some multicollinearity, a very, very important point that we learn out of example number 3. But if your goal is to explain the relationships, then it must be addressed. Very important point which comes out from our discussion. In our data set, we don't have multicollinearity, but if you have it, this is how you will address it. So now that we have done the problem of multicollinearity, I think one thing I forgot in the above. One step I forgot. I just realized it. Split the data into training and testing. No, before that, separate independent variables x and dependent variable to y. You have to divide the data into x and y. This is what the line number 5 teaches us. Divide the data into x and y. So now what will I do is, this is what I have. I will take TV, radio, newspaper into x and sales into y. So I already have this features, but if you want, I'll just keep it once again. When I say my x is going to be df of features, my y is going to be sales. Done. X dot head, Y dot head. Done. After doing that, the next thing is to do train test split. So I say split the data into training and testing. Now tell me, what should I write? From sklearn dot something import trail test split. What is that something? Very good. Yes, it is the model selection. From sklearn dot model selection, we import the train test split. Very nice and very, very important point for all of us. So I say over here that from sklearn.model selection, import train test split, and then I can decide upon the ratio. By default, which ratio do I prefer? In fact, that's exactly what most of them prefer. By default, what ratio do I prefer? 80-20. I will start with that. That is not necessarily the best, but usually one of the good starting points. So I say this will automatically give me four parts: X train, X test, Y train, Y test. Random state I am putting over here as 42. Shuffle is by default true. And then I will just check out the shape of each. So before that, I hope you remember the shape of the data set. We had 200 rows and 5 columns. So if I'm doing 80-20 split, how many rows will go in the train? 160. Correct. 160. Absolutely correct. So I'm doing that. And you can see 160, comma 3, 40, comma 3, 160, comma 40, comma looks like perfect. Then now you know the process, what we are going to do. So now that we have it, the next step is now you focus on xtrain dot head. We have to scale these values. Why scaling is important? See, if you look over here, xtrain dot describe. Now, in the earlier project, we did not scale it. Hours versus score. There also scaling is important. We did not scale it, but we should have scaled it. I purposely did not do that because I wanted to keep it simple. And anyways, it was a toy dataset problem, so it was simple only. Now here, if you look into this, we understood that which is the most important variable for prediction. Sorry, not prediction. Which is the most invested variable by the company? TV. And which is the least one? Radio, right? Now, there is something which I have to say, something which is very important. Just like you understood that TV is the most important one, and radio is the least important one by looking into the minimum, maximum, or maybe even the mean. That's just like you understood this. In the same way, the machine also understands this. Okay, now what is the problem? Just like you said, TV is most important and radio is least important. Machine also tries to infer something like this, which according to me is wrong. I don't want the machine to consider TV is most important and radio is least important. Why? why don't I want the machine to consider that TV is most important and radio is most important is consider. Consider how many students are there in our class. 51 are there, right? So I have a class of 51 students. And in my class, let's say this is the board where I teach. This is where I stand, and this is my first row. This is second row in the class where you all sit. This is the third row of the class, and let's say this is the fourth row of the class. Now, I have seen regularly the following students coming to my class. So I see Preetham is coming, Kamlakar is coming, Shweta is coming, Manu is coming, Ramani is coming, Shanu is coming, Raj is coming, right? And in this way, I see in my class regularly there are total around 48 students who are coming. Regularly, they come regularly, they be attentive in the class. But let's say I see over here that in our class, let's say for example, there is a student called as Rohan and Rekha. They don't come to attend my class. See, whether Rohan and Rekha are intelligent or not, that's a later part of the story. But this Rohan and Rekha are not coming to attend the class. So let's say I conducted total of 20 sessions in the semester. This Rohan and Rekha hardly attended two or maybe maximum four sessions. That's it. And therefore, according to me, Rohan and Rekha are useless students. And Anmol, Kamlakar, Raj, Manu, they are awesome students because they have attended my lecture. And Rohan and Rekha, I don't know, they may be very good in that stuff, but according to me, they are useless. I just hate those guys. I just hate. And I decide in my mind that on the day of Viva, I'm going to take out all my grudge which is there in my heart on them. So even if Rohan and Rekha answer everything nicely, I will ensure that I am giving them the bare minimum marks. And if they don't answer, I will fail them. I will have no mercy on them because they didn't attend my class. Huh? I have that grudge in my mind. And I do the same. And this all things are done just because they have not attended my class. So let's say on the day of the Viva, Rohan and Rekha were very good. Much better than Manu, much better than Kamlakar. But I have that grudge and I give them less marks. Is my decision justified? No, right? My decision is not justified. If as a teacher, I have to reduce marks for Rohan and Rekha, I should reduce them only in the marks allocated for the attendance of the subject. I can give them zero in attendance because they didn't attend. But in Viva, giving zero marks or failing them is not justified. Now consider me to be replaced by the machine learning model. Here, because the investment on TV is the highest and on radio is the lowest average investment, the machine learning model will consider that TV is very important and radio is least important. So while it is understanding the relationship between X-train and Y-train, if it goes on with its biased opinion like that, is that justified? Answer is no, right? It is not justified. And therefore, how to make machine learning model understand that you don't be biased? You remember I explained you min-max scalar. It it converts all the values, whatever be the minimum and whatever be the maximum. Each of this minimum will become zero and each of this maximum will become one. So everything is brought into a standard range 0 to 1. Yes. Do you all remember that? Yes. So we are not changing the values, but we are proportionately squashing everything into a standard range 0 to 1. And that is exactly what we are going to apply over here. That is exactly what we apply. So now I do the scaling of the independent variables. Okay. And only the independent variables. So I say over here, which scaling technique will I apply? Now see, I can apply min-max scalar, I can apply standard scalar, right? So we have standard scalar, min-max scalar versus many others. The question is which one to use when as per the industry standards. The question is also which one are the most popularly used in the industry. The question is also how should I decide which algorithm or which scaling should I use whenever I face a challenge. So let us figure out that. So we already know the scaling techniques. So here we say by default, if you ask me, one of the scaling technique which is recommended is standard scaling. By default, if you ask me, one of the scaling technique which is recommended is standard scaling only because it is one of the best technique to go ahead. Although there are many other techniques as well which are available, I'll just like to put up them. So if you talk about feature scaling, commonly used scalars, standard scalar. A standard scalar will ensure that overall average of every column becomes 0 and standard deviation becomes 1. Affected algorithms, linear regression, logistic regression, SVM, PCA, and it is very popular. I would say the first by default is this only. Min-max is mainly helpful for neural networks. So as far as our machine learning syllabus is concerned, you can kind of ignore it also. But at times you can try it also. If your data is having outliers, then you go for robust scalar. But obviously, if you are removing the outliers, then why will you go for robust scalar? So it has to be used when really needed in financial data sets where outliers are actually ideal values. Removing that is not advisable. In such cases where you cannot remove the outlier because they are genuine values, it is advisable that you keep it as simple as that. So next thing, max absolute scalar. It will scale in the range -1 to 1. It is mainly used in the text processing problem. So you are not going to use it here. Normalizer, again used in text processing problem, is a niche use. And very less common are the quantile and the power transformer. Then decision, which one to use. So you have to analyze the algorithm sensitivity, but you can see over here in most of the cases, standard scalar will fit. So KNN algorithm, K-means algorithm, PCA algorithm, They are highly sensitive to scaling. You can use any one of this. So when you have a choice in between standard and min-max, standard will be the first one that you try. Then in gradient based, where logistic regression and SVM are there, you use standard scaler. For tree-based algorithm, decision tree, random forest, XGBoost, scaling is not required. When we talk about that algorithm, we will discuss it, but scaling is not required. For neural networks, min-max scaler is the first one. And for sparse data, which is mainly text processing problems, over there, max absolute scaler. So looking at the data characteristics, also you can take a decision. So if the data is normally distributed, then standard scalar is good. If it's bounded between some values, then min-max is good. If it contains outlier, robust scalar is good. If it is sparse or normally distributed, max absolute scalar or normalizer is good. And if it is having a non-normal distribution, maybe you can go for this. Also, you need to look into the impact on the business. If you are doing a fraud detection where there are high outliers, robust scalar. Customer segmentation is the problem. Let's say you're implementing it using the PC and K-means, then standard scalar. For neural networks, min-max scalar. For financial time series problems, power transformer. And for IoT sensor anomaly detection, min-max scalar. So which scalars are most popular in the industry? As you can see this table. So whenever you face with any challenge, you should always check the model type. Is the model distance based, tree based, or gradient based? Like linear regression is distance based. Then you should assess the data for outliers. If there are many outliers, then avoid min-max scalar. You check the distribution of the feature. Is it normal distribution? Is it bounded in the range 0 to 100 or 0 to 255? You run quick EDA, box plot, histogram, skewness check. You do that. That's why we said EDA is very important. You start with standard scalar as default. That's exactly what I said, the most important thing. So when to use what? For most general cases, standard scalar. For bounded cases, which you see in the deep learning problems, 0 to 255 is the usual range. You go for min-max scalar. Outliers robust. For text data, you use the max absolute scalar. If Gaussian distribution, you go for this, and for vector normalization, you can go for this. That's essentially what we understand. Then I say from scalar dot preprocessing import standard scalar. Then I say SC is equal to create an instance of standard scalar. Then I say extrail of features. So I say standard scalar, go and fit transform. So I remember I had said fit is nothing but study, and transform is like apply the transformation. First you study and then apply the transformation. So that is what you are doing it on extrails features. And on the X-test, you only apply the same. Why are you only applying the same over here? Why not fit, which is nothing but the study on the test data set? Because it already has studied the training set, and we want to apply the same transformation on the test data set. This will help us to see how the model performs on the unseen data. Now, this is very, very important. I'll tell you what I mean by that. So here I did that. Now I'll show you what I mean by that. I'm showing xtrain dot describe. Alt, I'll also go for xtest dot describe. Now, if you see, is the average 0 for all the independent variables? Is the average 0 for all the independent variables? It is. It is. It is minus 2.9 into 10 raised to minus 16, which means it is 0.0000, 15 times 0 followed by 29. This is 0.15 times 0 followed by 208. They are very, 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 very small numbers. Did you all get it? Amit figured it out. Everyone, did you follow? The average is 0. And the standard deviation is 1. That's exactly what the scaling does. Average is 0 and the standard deviation is 1. Okay, that is what min-max scaler does. That is what standard scaling does. And here also, do you see the average very close to 0 on the unseen data? And standard deviation, if you see over here, standard deviation is close to 1 except for the newspaper variable. Standard deviation is close to 1 except for the newspaper variable. Now, you know what are we trying to figure out over here? The very important thing which I wanted to say. In fact, I'll show you this effect. This effect will be more properly seen uh, by showing you maybe. Yeah. So now if you observe, see what I did apply min-max scaler on this data set. Now, after applying min-max scaler, you can see the minimum value has become 0 and the maximum value has become 1. That's perfect. Minimum 0, maximum 1, and that is perfect. On the test dataset, also the minimum must be 0, na? On the test dataset, also the minimum must be 0. But it is not. But it is not. And the maximum must be 1, but it is not. 0.98. You know why? Because when the model did fit and transform on the TV, radio, newspaper, it got to study the data. And that data, whatever it studied, maybe let's consider the TV column. The TV column over there had the minimum value what? Let's say minimum value was 10, maximum value was 100. Let's say the TV column had minimum value 10 and maximum value 100. So min-max scaler will do what? Min-max scaler will convert 10 to 0 and 100 to 1. This is what it will do. That is with the training data set. In the testing data set, let's say the minimum value in the testing data set for the TV, the minimum value is 9 and the maximum value is 105. Possible, na? It's very much possible that in the test data set, there may be a minimum value which was not there in the train, much lower than that, or maybe sometimes it can be higher than that. Because it went out of the range, what do we understand? We understand that probably this is because of the shuffle. The shuffle that we got could be a bad shuffle, that it is not covering the test data set, and therefore to avoid that kind of bias, we have to see that ultimately after doing the scaling as well, is the train which is between 0 to 1, is the test also almost close to 0? It is. And is the max also almost close to 1? It is not. Because 98 is okay, 99 is okay, but this 1.13 is like almost 13 units above 1, which is not recommended. So what you can do is you can try changing the shuffle. So I go up, and instead of random state as 42, let's say if I'm trying out random state as 0. When I try random state as 0, my x10 is still 0, and this is also 1. Look at this. This is almost 0, and this is 9799.13. So it is still 0.1.13. So I'll go up. Let me say random state as 1. Now if you see, minimum is as good as 0 and maximum is still unchanged. Let me say try out random state as 43. Minimum is 0. Oh, do you see minimum is 0? Maximum is this is good, this is good. Newspaper is 0.63, much out. So this value must be close to 1. I say, let me try out 100. See, minimum is 0. Maximum is bad, more bad. Bad shuffle. So you keep on trying out this shuffling till you get a good shuffle. So let me try out random state as 99. More bad. So in this way, you keep on trying till you get the value. So I guess the one that we tried in earlier was the best so far. Now I do one thing. Yes, so this is what we see. Minimum, mean. Mean is 0 and the standard deviation is as good as 1. So let's say I'm going ahead with this, and the scaling technique which I'm finalizing is standard scalar only. Now, once the standard scalar is applied, now we are good to get into the modeling part. So see, essentially what I wanted to tell you is you always study and transform on the training data, and you only and only transform on the testing data, so that you are able to see that if the intelligence is captured in the object SC, how is it performing on the unseen data also? We would get into the modeling part, and I'm going to apply multiple linear regression model over here. And here I say from sklearn.linear model, import linear regression. Then you create an instance of this model. So as you can see, we are creating an instance by the name LR. You can give any name to it as you already know it. And then I will ask the algorithm to go and study over X-train, Y-train. Once it has done its study, I will ask it to make prediction on the training data set and the testing data set. So I say Y prediction on the train is linear regression. Please go and predict on this, and Y prediction on the test is this. Then I will evaluate the performance using the metrics. So let's first calculate the R2 score. So mean absolute error, mean R2, mean squared error, R2 score is what I am doing over here. Fan law, the mean absolute error between Y train and Y predicted trend. Mean squared error between Y train and Y predicted trend. Root mean square error between Y train and Y predicted trend. R2 error in between the two. And for calculating adjusted R2, right? So for calculating adjusted R2, I need the formula. You remember, we have already seen that, right? So I will calculate the number of rows in number of columns in that, and then I will calculate the numerator of the train. Formula is this, no? Numerator of the train is 1 minus R2 train into N train minus 1. Denominator of the train is N minus P minus 1. Okay. And that's the adjusted R2. Similarly, on the test data set, we do the same thing. We have already studied this, huh? So I'm not explaining it once again. It is just application of this formula. And I'm printing the training metrics. I'll print the train and test set evaluation. So MAE for train and train set MAE, testing set MAE. Similarly, MSE, RMSE, R2 and adjusted R2. We got all. And we have computed it. This image will get lost in the Google Colab. So this image URL is what I have pasted over here. And we can see over here, MAE is this, RMSE is this. On the train, it is less. On the test, it is little bigger. R2, it's 0.9 and 0.9. And adjusted R2 is little less, 0.89 and 0.89. And now that we have this, we will also be printing the coefficients of the model. So the coefficients of the model is feature-wise coefficients. So zipping together. And I'll also be printing the intercept of the model. And then I'll also be printing the equation of the model, y is equal to this plus this into this. Let's understand this. Before that, I would just like to know, after this coefficients of the model, I want a new line. And in this equation of the line also, I want a new line to be added in between. So if you see, TV is 3.76, radio is this, newspaper is this, intercept is this. So the equation of the line is M1x1 plus M2x2 plus M3x3 plus C. What do we understand? So we understand that for every 1 unit increase in TV, 1 unit increase in TV, that means 1,000 additional dollar investment, the sales increases by 3.76 units. For 1 unit increase in radio, the sales increase by 2.79 units. And newspaper, oh my God, for every $1,000 additionally invested, the sales of the newspaper is increasing by only and only this much. Little bit put a stress on your memory and try to recall which was the most important variable for prediction as per us when we looked at the scatter plot TV. And that can be seen over here. And what was the least important? Radio. But looking at this, which is the ideal, real, least important? Newspaper. It says that if you invest 1,000 additional dollars on newspaper, you only get a sales increase of approximately 6 units or 6%, which when compared to TV and radio is marginal. If I have to create a model once again, which feature will I prefer to drop? Newspaper, right? Absolutely. So now, if that is the case, I say, since the coefficients of TV and radio are higher as compared to newspaper, we conclude that TV and radio have much impact on the prediction as compared to newspaper. Let's visualize the prediction. Let it come, then I'll talk about it. Now, if you see over here, what have I plotted? These are the actual sales and these are the predicted sales. And these are the actual sales and these are the predicted sales. So actual versus predicted is what we have plotted. So the thing over here is, what do we understand from this? Right? So looking into the actual and predicted cells. So what we did is Y train, which is the actual, and Y predicted train is the predicted. I just plotted them in blue color. Alpha is 0.5, and rest all things are decoration. And another one, Y test versus Y predicted test. Rest all is decoration. Now looking at this, what do we conclude? See now here, if you carefully observe, when you look at the left plot, which is about the blue dots, most of the points lie on the diagonal. As imagine from left to the top right, bottom left to the top right, which clearly indicates that on the training data, our model is fitting well because the predicted sales are closely matching the actual sales for most of the records, because this is how it is. So this is what we see, because I said color is equal to blue. A few data points deviate, which show minor error, but the coverage is still strong. Also, because our R2 is high, uh, this is because of that as well. And on the right side, if you see, it will still follow the diagonal with a slight more towards the training data. Right. So here we understand that the model is performed reasonably well on the unseen data. That means it is able to generalize, but with few cases where there are less accurate. And this spread is normal, indicating that there is a balance in between overfitting and an underfitting model. So we see there is a slightly lower R2 over here, indicating that there is a high error metric. Then overall, we can understand that if the coefficients, right, since the coefficients of TV and radio are significantly higher than newspaper, we can conclude that TV, radio are important and newspaper is less important. So newspaper hardly contributes anything. So in business terms, I can also say that the marketing managers may want to reallocate the budget from newspaper advertisements to TV and radio for better ROI. What we understand, this is what we overall understand. So now, what am I planning to do is I am planning to actually, uh, I'm planning to actually remove newspaper and see if my thing is useful, right? So I just added explanation about this for your better understanding. But I explained the same thing. So we will now try to remove the newspaper. So I say that let's remove the newspaper from the data set and see how it performs. So what will I do is I will say features is equal to only this, my X and Y separated. Then after X and Y separated, again I have to go for train test split. I did that. After train test split, I'm not interested in looking at the shapes. I'm looking for scaling. So I create an instance of standard scalar and I fit and transform over it. Now I don't need the comments as well. That was, it was good for the first time. Now I don't need it. Okay. Then I go to modeling. I create linear regression model. I fit over it, and after fitting, I'll copy the code. After fitting, till the end, everything I'm copying. You can see over here, after fitting, prediction, error metric calculation. This is good so far. Everything remains the same. And this, but of course, the equation of the line will change. Now, if you see, let us look at the older results first. I'll have to copy that for our better understanding. We see that over here. So training set having MA 1.2, testing set 1.44. Mean square error 2.71, 3.14. Let's compare with the older one. Earlier it was 1.2, then it is 1.2 only. After dropping newspaper, no impact. But MA, which was 1.44, actually it increased. It should have reduced, but it increased. But let us look at the most significant metric as per us. R square is 90, 90. Latest one. And the earlier one was 90 and 90. No impact. Adjusted R square 89, 90. It is 89, 90 only. And you see that. Now I'll do one thing. You know what? The reason I'm getting the same thing is because I'm looking at only the 0.2 precision. I will prefer to go for entire result everywhere. Here also, here, and here also I'd like to go for the entire result. That 0.2 is actually not showing us properly. So now maybe we get a good idea. So earlier it was 0.893695 from 8942. See, adjusted R to increase a little bit. On the test, it was 89105. Now it is 8950. See, there is an improvement, which means that dropping the newspaper was little, but it was definitely helpful. And these are the new coefficients. This is what we understand so far from this. How is radio actually helpful is what we understand in over here. So dropping of that was a good idea is overall what we can conclude from this. So we see over here that the equation of the line for features TV, radio, and newspaper was this. And here is this. So we can see that the coefficients of TV and radio have changed slightly, but the overall performance of the model is still good. So conclusion is we can conclude that these have higher newspaper are minimal. So dropping newspaper did not affect the performance of the model. So better selection can improve the performance. Dropping newspaper did do that. Okay. And that's it. Model can be further improved, but right now I'll not get into that. And this is what we have. Everything is done so far. And now after this, we say that let us visualize the predictions. Same code. Same code like before, nothing new. So not really a great achievement, but definitely if it has improved even this much, see, I need not invest on newspaper. I'm getting anyways the returns from other factors. Why will I invest on that? And that is what is the conclusion so far. That is what is the conclusion so far. Now, number one, see, something which I didn't explain you in the code is what I am going to explain you right now. The first one is, we are talking about assumptions of linear regression model. Our case study is done, but we are talking about assumptions of linear regression model. So I'll just talk about it. So that's the topic, assumptions of linear regression model. The first assumption of linear regression model is linearity. So linearity is what we have already checked. So we have already checked what is linearity. So linearity says that between independent and dependent variables, there must be linear relationship. And this is what we have checked. If this assumption is violated, then linear regression is not the right choice of the algorithm. And the way we check it is visualize predicted versus actual. We did that just some time back. We have done that above, right? This is the same. But still, I will like to do it over here. So I am simply plotting the visualization. So what am I saying? It says that when you do y train minus y predicted train, there must be linearity. When you do y train minus y predicted train, there must be linearity. So I'm just finding out the difference. I get this histogram. And on the scatter plot, I am plotting y predicted train versus the residuals. Right? So prediction versus the residuals, and there must be linearity over here. Right? So here we say that the residuals should not show a pattern when plotted. I say the residuals should not show a pattern when plotted. So what do we understand by looking into this figure? Right, so on the x-axis we are having the predictions, and on the y-axis you are having the residuals. Then you can see over here that I'll just put it here only. The red dashed line is showing the zero residual line. So here, for a perfect linear model, the residuals would be scattered randomly around this line. So the thing is, in case of an ideal plot, if the linearity holds, and in case of an ideal plot, then you will see this relationship something like this. The residual spread, it must be randomly scattered with no clear pattern. Centering should be roughly around the zero line. There must be no curvature or funnel shapes, and there must be no clustering. Then I say, in our plot, our findings are this. Findings are like, you see a moderate clustering of the residuals around zero for lower cells. And the interpretation is, there is a possible slight under prediction at lower cells. There is a slight spread funneling at higher predicted sales. It may indicate there is a mild heteroscedasticity, but not severe. What is heteroscedasticity? We are going to understand in the next one. That is the next assumption. There is no clear curvature that indicates it's good, and residuals are roughly balanced around the zero line. So we can say that your model that you have over here, your model captures the linear relationship between the predictors, TV and radio quite well. Residual plot does not imply any strong nonlinear pattern, and small deviations at extreme values are normal in business problem. Now, the next assumption after this is independence of the error. The next assumption is the independence of the error. What they mean is the residuals must be independent. In time series, this data is tested using a test called as Durbin-Watson test. Here, obviously, we are not dealing with time series, so it is non-sequential data. So independence is assumed if the data collected is independent. So here, if I'm thinking of the test, Durbin-Watson test, it's just a hypothesis test. It is giving me the value of 2.16. It says that a Durbin-Watson test, when you see the result close to 2.0, then it suggests that there is autocorrelation, and less than 1.5 or greater than 2.5 suggests that there is no problem. In our case, see, let me also tell you that we are not using a time series, so we can assume the independence of error. When we see time series, at that time, this will be relevant. So for now, you can just assume this is some metric that you can ignore it for now. Now I will go on to the third one, which is called as homoscedasticity. They ask all these things in the interviews. What all are the assumptions of linear regression? They ask it. So homoscedasticity. I'll show you what it means. It basically means, look into this plot. If we see over here, the errors, they are distributed around the line equally. But if you see in the next plot, the error is increasing, going away from the line. These dots are also going away from the line. Such a scenario is called as heteroscedasticity, which is the unequal scatter of the residuals around the measured values. So I have pasted the link for this image here. And then this is the explanation of this. The residuals should be constant at all the levels of the predictions. If the variance is fan shaped or funnel shaped like this, fan shape, then the assumption is violated and we say there is a heteroscedasticity. Let us plot it. So scatter a plot of y predicted train versus the residuals. That's what we did, right? Errors. And that's what we see over here. So this is the same plot. Okay. Then I say in this particular scenario, now you see over here, we see a red line and we are checking for this. So in this plot, we clearly see that I have the predicted sales on the x-axis, residuals on the y-axis, and the red dash line 0. So let me tell you, what is the ideal behavior in case of homoscedasticity? So in case of homoscedasticity, if it holds, then the residuals should have a random even spread. There must be no increase or decrease in the variance, and there must be no clustering. So we say in our plot, we see the following things. So we clearly see that there is a fairly consistent spread of residuals across this one. You can see that over here. Plus, you also see, because of that, we see that homoscedasticity seems to hold reasonably well. You also see that there is a slightly wider spread at the higher end of the predicted sales. So minor indication of heteroscedasticity, but it looks like in the acceptable range. There is no strong funnel shaped or curvature, so there is no heteroscedasticity pattern, and the residuals will still be around the line. Okay. In fact, you can actually confirm this thing by doing a small test also. There is a test in statistics which allows you to do that. So if you don't want to get into this plot and understanding, straight away go for this test, which is popularly known as the BP test, Brush-Pagan test. So I'm just adding a constant to x-train and I apply that test. And you can see I'm getting the p-value over here. Right, so you can see over here that I am getting the p-value as 0.14. Now, looking at this value, which is 0.14, here I can see the output as 0.14. So coming on to the interpretation, we can, how do we interpret over here? The idea is if the p-value is greater than 0.05, you fail to reject H naught, else you else you reject H naught. Now, in our case, we can see that the p-value is this. So we fail to reject the null hypothesis, saying that there is no statistical significant evidence of heteroscedasticity in our model. So, see, I would also like to tell you that why are we doing this? In real time, it is also important for us to understand the business interpretation. And that's exactly what this is giving us. So, if the variance of errors is constant across all the sales levels, that means the model can be statistically stable for all the sales ranges. That is for extrapolation as well. And there is no special action required, and I can trust the prediction of the model across all the ranges. This is what you have to memorize and take it ahead. But yeah, this is essentially what it means. Right? So that is the next one. The fourth one, fourth assumption over here is the normality of errors, which says that the residuals must be normally distributed. And this is important for the confidence intervals and hypothesis testing of the coefficients. So I say, let us see if the residuals are normally distributed. So I am simply creating a histogram of the residuals and it must show a normal distribution pattern. And after that, I'm also up. QQ plot is not very important, unnecessary confusion. Yes. So you can see over here that this is how we see the results of this. So what do we essentially figure out when we look at such kind of results? Let's try to figure out that thing over here. So see, number one, I said that there must be normality of the distribution. So what do we figure it out? Number one, we see that the residuals are roughly centered around zero. Yes, I see there is a skewness over here, but roughly they are centered around zero. Plus, I also see that it is left skewed, meaning there are more negative residuals than the positive one, which also means that the curve is not perfectly bell-shaped. There is a long left tail, which makes me conclude the following. Centered at zero means the model residuals are balanced on an average. If it's skewed towards the left, it means there are some under predictions which occur more often with the larger errors. If it's not perfectly Gaussian, it means that the model is not perfectly normal. Residuals are not perfectly normal, but it is very common in real business data sets. Then if you look at the QQ plot, which is nothing but called as the quantile plot. Now, what is basically a QQ plot? Right, so first we need to understand what is a QQ plot. Now, ideally, throughout the machine learning, there are many instances where I don't even talk about it, but let us quickly understand what is QQ plot first of all. So QQ plot is nothing but a quantile plot. It is a diagnostic tool to compare the distribution of your data to the theoretical distribution, most commonly the normal distribution. So the way it helps us is helps us to answer the questions like, does my data follow the expected distribution? Because it is plotting the quantiles of your sample data against the quantiles of the theoretical data, which are usually expected to be normal. So if it matches the theoretical distribution, the points will lie on a straight 45-degree line. You see over here, it should lie on this line over here. Now, in our case, what is it showing? It's not perfectly lying on the line. You can see initially it's not there, later on it's not there. Rest of the time it is there. So we say, in our case, the points falling on the straight line, data matches the theoretical distribution. Deviations from the line deviates from it. The curved line upwards and the curved line downwards indicate that there is a right skewness on the long tail and the left skewness as well. And S-shape means the data has heavier tails than the normal distribution. If you see that. So Why are we using that in regression? The reason we use it in regression is it will help us to figure out. So as I told you, in QQ plot, we expect the residuals to be normally distributed. It helps us to inspect whether it is normal distributed or not, and it can help me in detecting the skewness, kurtosis, etc., etc., etc. So now, coming on to our explanation of QQ plot. In our QQ plot, what do we actually see? So we see clearly the points are initially off the track, later on off the track, in between they are on the track. So we see that the points must follow the red line. And they mostly follow that, but somewhere in the middle. At the lower quartiles, they go below. And this confirms that there is a skewness in the histogram. Therefore, I say the middle part follows the line. Most residuals follow normal distribution. The left tail deviates from the line, and the right tail is fairly aligned. So, my final conclusion on this data, we can say over here that if you look into this, there is a normality seen in most of the data. Yes, most of the times it is normal, except this and this. So we can say it's mostly normal. Slight issue is there, but not critical. And practical business impact, we say it is negligible. So again, I say, don't forget these points. I would again reiterate over here to say that if your goal is prediction, like forecasting, then the level of deviation is acceptable. If your goal is to generate precise p-values, then you might need to apply transformation to the log data. And that's how they are helpful. So we say in our case, we can see that normality of the residuals is reasonably satisfied for predictive modeling. Slight left skewness is typical in the sales data and does not invalidate the regression metrics. Oh, backache. Sorry. Okay, that was the thing that we observed. And the last assumption is no multicollinearity. We have already checked that, but I'm just putting it officially over here. So we all know that multicollinearity must not be there. And the way to measure multicollinearity is by calculating variance inflation factor. So we just want to see that these two things are not highly correlated with each other, and we directly have the VIF calculation. So you import the variance inflation factor from the stats model, and then I create an empty data frame. And in that empty data frame, TV and radio, which are there in the X train, I am saying that these will be the two columns of the data frame. One is TV, one is radio. And I need to put in values into that. So how am I putting? I say that for I in the range of X train dot shape one. Shape one is nothing but the number of columns. So it will go on through each and every column. And for every column, it will be calculating the VIF. So you can see over here, or I can actually look at this. So you can see over here, feature is TV. VIF is this. Radio, VIF is this. So we can clearly see over here what is the VIF. In this case, all of these are expected to be below this. So this is what we understand. So overall, we conclude that for every additional unit, the sales increase by this. For TV, this one is this, and radio can be removed, is what we understand. After this, uh, these were the broad steps that we set. So if you see over here, till this point of time, prediction is done, evaluation is done, visualization of the results is done. Now we get into the saving of the models. So for saving of the model, machine learning model uses a special format for saving the model, and that format is called as the pickle format. That format is called as the pickle format. Now our model is called as LR, and so we will have to save the LR model, and we will also have to save the standard scalar which we had chosen by the name SC. So here obviously I want to do that. So for saving the model, I will have to import a package which is called as joblib. So so joblib is basically a package used to save the model. Now you know what? All machine learning models work on one simple funda: garbage in, garbage out. If you recall, what all are the steps that we applied? We load the data, explore the data, encoding, we separate the independent dependent, then we split the data. Then after splitting, we scale the data. Now, then we apply the modeling part. So line number 7, we scale the data, then you apply model, then you make predictions. And while making predictions, you remember you have also scaled the dependent variable. In real life, when you're actually productionizing something, the user will not enter the data in the scaled format. If I say a company has to type in how much amount it invested in TV and how much it invested in radio, so he or she will just type in. He will not apply standard scalar and then type in. That means as an end user on unseen data, you will have to apply standard scalar before the inferencing. Am I correct? User will type in the normal values. You will have to do this thing, else garbage in, garbage out. Therefore, the standard scalar object also needs to be saved. So I say we need to save the standard scalar object as well. So the first thing is, let us save the linear regression model, which we called as LR. So I say joblib.dump. It will actually dump the model. You'll see it here. And I will also save this, saying this. I'll just print over here. This saved successfully just for our satisfaction. It printed, and you can see these two things are here. They are being done successfully, they are being saved successfully. Even if you try to open it, take a moment. That will give me also some break. Take a moment, and I'm sharing with you the models. Just try to open the standard scalar and the linear regression model, which I shared with you in the chat box, and try to open it with any application. I think Notepad will be the best for opening it. Try opening with Notepad and see what is coming inside that. Try opening it with Notepad. Binary format. I think what you can see over there is binary format. So you can see all these things. Basically, even if I share this with anyone else, he or she will not be able to understand. Like for example, we boot the Windows operating system because maybe it has errors or it is corrupt due to viruses or anything. We do that. So when we actually do that, what does the Microsoft share with us? Do they share with us the source code for their operating system, or they share with us the .exe file? Are they sharing the source code, or are they sharing the exe file? Do they share the source code or they share the exe file? Yes, they share absolutely the exe file. That's absolutely correct. And that is the advantage, right? So you cannot copy paste and create your own operating system. And the same is the case with this pickle files, which you see over here, linear regression and standard scalar. No one can copy paste my code. No one will know my code. They can use it for inferencing, but they will not be able to understand how I coded. That's a way of securely saving your thing. Now it is time for me to actually deploy it. So I'm going to create a new file, app.py, and I'm trying to run it first. So first I'll try to run it. Then I'll show you the process, what I did, etc., etc. Now let's observe. I created a nice application. Code part we will study later, but it is asking us that, hey, enter the spend on TV. So let's say I invested around $12,000 for investing on TV. Or let's say I invested around $39,000 for advertising on TV. And on the radio, I have invested $9,000 and I click on predict sales. My sales will increase by 6.49. Let's say if I invest 9 over here and if I invest more on radio, see, it didn't impact. 9 and 39 is giving me 10.78. But 39 and 9 is giving me 9.17. 99 and 9. That was sorry. 39 and 9 is giving me this. If I'm spending, let's say, $200 for advertising over here and 200 over here, my sales is 50. But if I spend instead of 200 just 100, it is 31. And if I spend 100 over here and more on a radio, it is 45. So this is what we see. Now let us look into the code over here and try to understand what have we done. First of all, you need to install the library Streamlit. It is used for creating this nice user interface. Then you can see I have written sales prediction app. Import job lib and numpy. Job lib is for say, loading the model. Then I say at st.cache resources because Streamlit is imported as st. Now I say cache the model to avoid reloading on every interaction. So every time I am going to run this, every time I'm going to infer, I don't want the entire code to run, so I can cache the resource. So I say joblib.load. Earlier I used the joblib.dump method for dumping. Now I'm using the load method for loading. It is going to load it. Similarly, the standard scalar is also loaded and it is going to return that. And when I give a call to load this, it will be loading and the model and the scalars are available here. Then I say Streamlit title, sales prediction app. You see that? Then enter advertisement and this. So sc.write, enter the advertisement below to predict the sales. This is what we see. Then I will accept from the number box TV advertising spend. So you see over here TV advertising spend, there is a number box with minus and plus. So I say minimum value is 0 and the maximum value I didn't give, I can give maximum value. So I didn't give, but I can write max value. And every time it will increment by 0.1. That is if I plus, it is 100, 100.10, 20, 30, 40. Similarly for radio also I created a number input. Everything gets created one below other. Then I say if st.button, that is if the user has clicked the button, right? Then I say over here, I am going to capture the values from the above. Above means see TV spend and radio spend. These all variables are captured, converted to numpy as user input. Obviously, the user has given the values in the non-scaled format, so I will transform it. That's why that scalar was required because the model cannot predict on the values 100 and 200 because we scaled it. So the same thing applies over here. So I say scale input and then the linear regression model predicts on that scaled input, saves it over here. And that is what is predicted. And you see that thing over here. And then for running it, you say streamlit run app.py. Then now what I do is I uh, want to, I'll just kill this. I want to get the requirements.txt file. So I get it using pip freeze requirements.txt. So I come over here. I'll tell you why am I doing it. Pip freeze requirements.txt. I get a file created. These are all the packages which are used in my project. Whichever are available, all of these packages are available. Now, all of this are available. So basically, it is taking a lot of packages, something which is not required as well. I will only take the packages of my interest for this project. So mm, I don't want to filter it. I'm just trying to see exclamation pip freeze requirements.txt and this is updated. Now see, coming on to the deployment or any article, I can't suggest you any article as such for deployment on AWS. The reason being very simple is that their steps mainly remain the same, but they keep on updating small things in the UI for making it more and more better. And that is exactly where it goes a little bit uh, changed. So the best way, if you really have to learn, I can recommend you that you go to YouTube and we can say machine learning model deployment, AWS, and in the filter, you sort by upload date so that you get one thing. So real-time prediction demo using SageMaker is there, and AWS GCP 4 minutes ago. We can go through it, and then sorry, the chat box is open. Okay, anyways, I can show you the rough process and then we can look for some other code. So if you see over here, he has taken the iris data set and model is fine. Model.pickle is ready. Inference.py is what? Not actually, it's a little confusing. He explained the architecture, that's fine. Not a good video. But there are many available. Many are available. In fact, this is what I would recommend you to go through a latest video or maybe a latest Medium blog is what I can recommend you. And it's very simple. Ultimately, it's not difficult or as it's straightforward only to be very honest. In fact, even if you get into, you will have it's yes here. I'm just waiting for this only. They have their own link also, which is updated. Which kind of model you want to deploy, you will be having those all things, the SageMaker AI, and you have the entire step-by-step process as well on their own website to learn about it. So you can refer this as well. See, audio transcript, video transcript, no, AWS free tier is fine. You have proper steps where they have mentioned as well. I would recommend you look for the latest video in this scenario. And so basically, see in AWS, you have to code on AWS SageMaker. So this AWS SageMaker is where it's nothing but the Jupyter notebook only. AWS SageMaker is nothing but Jupyter notebook. So if you actually check in over here, you have to create a role and all those things. Very standard steps, right? They have mentioned everything, how to do that, how to launch that. And then when you start inside this, oh, sorry. If you start inside this, so you have to create a notebook inside the AWS and see here. Then you get an option in AWS where you say open Jupyter Lab after choosing all the spaces and all. And that's it. It will create a Jupyter Lab and whatever you code over here will be saved over there. And that same thing will be used for deployment. So many videos are available like this. Just check out for the right one and the latest one. If you go on for a very older one, maybe the steps might have changed. Cool. And coming on to Shweta, she also had a question. Main file path. That is wrong, no? Shweta Rakesh Kumar slash first model, that's fine. Main file path is app.py. app.py, not the pickle one, no? Not the pickle one. Your main file path would be app.py. Basically, whatever is the name of this file, that will be the main file path. Try this, Shweta. I think so. Some issues. No problem. See here. So how did we do the deployment? Now you know that importing that is fine. So every time I do the inferencing, like if I go here every time. Oh yes, okay. I just saw. I think the chat box was hidden. So I was saying every time you do the deployment. So every time you click on predict cells, every time you are clicking on the predict cells, in the backend, it is giving a call. So I don't want the model to be loading again and again. Therefore, we write at st.cache resource. I'm loading the model and scalar. st.title, we know that I'm giving title and right. So you can see this is the title, which is big and bold. And st.right is this. Then I say st.number input, which is for accepting the inputs, TV advertising budget. You can see st.number input, TV advertising budget. Similarly, for radio, there will be one more and then predict button. So similarly for radio, you can see I have added one more. Then you have button. If button is clicked, then I say np.array on these two, scalar.transform, and then we have this lr model.predict. Save over here, and then I said in st.success. Now success will get it in a green box. If I say st.markdown, it will come in a normal text format. So there are various ways in which one can print. So here, what are you saying? Also, okay, I think okay, I messed out something. To independent. Okay, let me see what have you said. There is no multiple as a correlation value. That's correct. Sandeep, you want to, I think, just a moment. Little confusion. Better speak, Sandeep. Yeah, I gave you the unmute access. Yes, but I can't hear you. Is your mic connected? No, we can't hear you, Sandeep. If I don't know, we can't hear you. Can anyone hear Sandeep? No. Okay, I'll take your point, what you said in the image. I think there is no multicollinearity between independent variable as the correlation value is between this. Yes. So, see, when there is a multicollinearity, if the value goes above 0.7 or below minus 0.7. So, in our case, what we saw above, the point number 1, 2, 3 in the image that you shared, TV and sales, radio and sales, and newspaper and sales, they are between independent and dependent variable. The fourth point is about multicollinearity between independent and independent variable. That is TV, radio, what is the correlation? TV, newspaper, what is the correlation? Radio, newspaper, what is the correlation? Is any one of the relation between X versus X greater than 0.7 or less than minus 0.7, then only multicollinearity is there. So in our case, we didn't find any of these correlations above that or below that, and hence we say multicollinearity is not there. So it must X versus X. That value must be between minus 0.7 to plus 0.7. If that is the case, we say no multicollinearity is present. This is the Guru mantra. Between X versus X, the value must be between minus 0.7 to plus 0.7. In fact, our today's notebook is talking a lot about that thing only. Take you through this. And let's get started with our today's data set. This is what our data set is. You can see the columns of the data set are there in the very first column. But let me show you the data dictionary first. These are the columns of the data set and the meaning of each and every column in the data set. One moment, I'll just open up the drive. I think it's not open on my system. This day 4. Now it's put. And uploading. Yeah, done. Okay. Let me create a notebook. So you can see these are the names of the columns. The target variable is the price. Read the last few names also. And then let me create a notebook over here. Linear regression using OLS. Now see, this is linear regression using OLS. Now, ideally, this one is not there in your syllabus, but indirectly it is there. So what I want to tell you is, you remember in your syllabus, you have RFE, you have VIF, all these things I said. So in the same way, this particular thing is not there in your syllabus, but for understanding RFE and VIF, which are algorithms for feature selection. So when you have too many features, how do you reduce on the number of features? That is where these things are important. So we had ideally discussed around all these things in our very first session. Let me give you a heads up on what I am saying. Yes. So if you look in over here, right? So this is our day 1, 28th June. Now here, if you observe carefully, I said in supervised learning, you have regression and classification. We completed one regression algorithm. We also deployed it using Streamlit and Streamlit Cloud. Now, ideally, I should go on to classification algorithm, but I'm taking one more regression algorithm example, that is linear regression only, but this is not the linear regression from the sklearn. So till this point of time, we were saying from sklearn.linear model import linear regression. But right now, I'm talking about linear regression using the ordinary least square method. So linear regression module is also developed by statisticians, and they have saved it using in a module, not sklearn, but that module is called as stats model, right? It is called as the stats model, and that is what we are going to understand. And it is very, very relevant, very, very relevant. You will understand why this is important. It's going to be a big case study, and it's going to be a very nice learning experience. You'll get a lot of knowledge over here. And over here, if you see feature selection, we are also going to study this RFE and VIF, which comes in the unsupervised learning. So we will be studying this as well. So linear regression is the algorithm to be studied not from the scikit-learn, but from the stats model. And that is what we are learning. And over there, when we have too many number of columns, for reducing the number of columns, I am using RFE. And for checking if multicollinearity is there, we are going to use VIF. Now you'll be like, but Darshan sir, you only just said, you said it right now to Sandeep also, that if the value is between minus 0.7 and plus 0.7, we say it is multicollinearity. Agreed. Agreed. But imagine you have 100 independent variables. So in that case, when you plot a correlation matrix, it is going to be 100 cross 100. Do you think practically it will be possible for you to analyze a 100 cross 100 size correlation matrix? No, right? Impossible. So that is the place where your VIF is going to help you out. How? Well, for that we need at least 1.5 hours from now, but because first we have to build the model. But remember, I'm just setting the context. RFE is for feature selection. So out of 100, I say, hey, can you extract the top 10 features? Out of 100, can you extract the top 10 features? That is RFE. And VIF is, hey, is there any multicollinearity between the features? So we have to check both of this. And that is what our work gets started over here. So car price prediction. Let me ask you, I'm sure you might have heard about Maruti Suzuki, the car manufacturing company. And if you have heard about Maruti Suzuki, then I'm assuming you might have also heard about Geely Automobiles. How many of you know Geely Automobiles? Yes or no? Okay. It is very famous, as famous as the Maruti cars in India. But this is in China. Yes, this is in China. That's the difference over here. Right? It is in China. That's the only thing. Now let us read the problem statement. So the Chinese automobile company called as Geely Automobiles, now they want to enter the US market and they want to set up the unit over there and sell their cars to the US people. But the thing is, the requirements of the US people can be different. See, I'll give you a proper example. Companies like Chevrolet, companies like Ford, and even to some extent, Skoda, Volkswagen, Nissan, Renault, they are in India for so long, so many years. Some of them have even left like Chevrolet and Ford. They are not able to sustain in the Indian market. Now, there is no doubt about the cars. If you look for Ford cars, Chevrolet cars, Volkswagen cars, they are far better. Over-engineered cars, I would say, over-engineered cars as compared to Maruti Suzuki, which is just worst. But still, people buy Maruti Suzuki. One reason is the service, and the second reason they say is the parts and all which are available everywhere. But forget about that. If you look at the overall quality, reliability, everything, this Ford and everything are much better. हाँ mileage कितना देती है? But no one is concerned about the safety, right? People are just looking at the mileage and buying it. So Maruti Suzuki people know exactly what the poor people in India want, and they exactly target that. Now, today, the next thing which people want in a car is what? So if you look carefully, right, if you look for the company like Ford, they were not able to survive. They had to leave. Skoda, they are working on it. But if you look at the companies which came much later, they are able to survive. Like, for example, you talk about Kia, you talk about MG, they are able to survive because they actually understood what is required in the Indian market conditions. What are people required for? Are these cars offering safety? No, neither of these are offering safety. They are offering you features. They are offering you only and only features. And that is what is the most important thing. So they actually understood what is needed and what is not needed, and that's what we see in over here. So it is very important to analyze what is the requirement of the client when you talk about all these things. And that's exactly what Geely automobiles are also doing. Just like here in India, people are not more interested in the safety part of it, but they are mainly interested in features. Is the car having a sunroof? Is it having a moonroof? Is there a 360-degree camera? Huh? Is there this function? Is there that function? But the car is having only three-star safety. So is that really reliable? People are not concerned with that. They are concerned with the features. And that is the harsh reality. But these people or these companies like Kia, MG understood it really well, and they are able to establish a good hold in the Indian market. And companies like Ford, Skoda, they are not able to do that in spite of their cars being better. Moral of the story. It is important that these things are known properly. So, therefore, this Chinese company, Geely Automobile, they contracted a automobile consulting company in US to help them understand that what are the factors which are affecting the price of the car in the US market. So they want to understand the factors which are affecting the price of the car, because the Chinese market requirements might be different from the US market requirements. So company wants to know which variables are significant in predicting the price of the car and how well these variables describe the price of the car. And based on the market survey, they will be taking a decision. So what they have done is this consulting firm has gathered large data sets of different types of car across the American market. And therefore, the business goal over here is you are required to model the price of the cars with the available independent variables. And that will be used by the management to understand how exactly the prices vary with the independent variable. And they can accordingly manipulate the design of the car, the business strategy in order to meet certain price levels. Further, the model will be a good way for the management to understand the pricing dynamics. So that's one thing. So let us get started with our work. Number one, we do all the necessary imports, and you know that very well. I don't think so. I need to justify anything more over here. Next, after that, I say now we are going to get started with the data understanding part. So reading of the data and the understanding of the data. So importing the data from the pandas library and understanding the structure of the data is what is the next thing that we have to do. So the first thing which I do is I say read this data which is available, and then I can look into the first few rows. And you can see there are 26 columns and it is not able to show all the columns. Dot 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 is there. So I want to display all the columns. So again, I will go for the set option function of the pandas. And that's what I do over here. Yes, that's perfect, Shivam. So I go for the set option and now every column is visible. So now we have this column names over here. If I get started with that, every car in the data set has a ID. Symboling is the insurance risk rating. So if it is +3 means car is very risky, like Maruti Suzuki car. If it is -3, then it is very safe, like Tata Mahindra cars. So symbolic rating, which goes between -3 to +3. -3 is safe, +3 is risky. Name of the car. So you can see Alfa Romeo, etc., Audi. Fuel type, petrol or diesel. Aspiration, standard turbo. Number of doors in the car body, convertible, hatchback, etc. Drive wheel, rail wheel drive, front wheel drive, four-wheel drive. Engine location, front or back, like Ferrari has engine in the back. Engine location, wheelbase. Wheelbase is what? Wheelbase is the distance in between the front and the back wheel. So in simple words, if I have to tell you, wheelbase, yeah, this is the distance between the front and the back wheel. So exactly between this and this, whatever is the distance, the longer the wheelbase, the more comfortable is the car. The jerks and all don't come more inside. So that is the wheelbase. Car length, car width, car height, curb weight. Curb weight is basically the weight of the car. That's it. Without anything in the trunk and no passenger sitting. No luggage, no passenger. What is the weight of the car? So then engine type DOHC, MPFI, TDCI, OHCV, etc. How many cylinders are there in the car? Nowadays, most of the car manufacturers are, at least the budget cars are coming in 3 cylinders. They are saving on the cost. Engine size, fuel system, MPFI or what? Bore ratio. We already read about it, right? Stroke, 2 stroke, 3 stroke, 4 stroke, compression ratio, horsepower, the peak RPM, maximum revolutions per minute. What is the mileage of the car in the city? And what is the mileage of the car on the highway? And then the dependent variable, which is the price of the car. The dependent variable, which is the price of the car. So this is what we are having over here. Now, after that, let us check the shape of the data set where I say cars dot shape. So you can see we have only 200 cars data, not more. That is also one more drawback. We are having less data. Okay. Now, let us describe the data set. Now here, there are lot of insights that you can get by looking into the describe as to what is the average wheelbase, average car length, minimum and the maximum car length, car width, car height, curb weight, engine size. I'll mainly focus on the price column right now. Okay. So if you look into the price of the car, the average price of the car is $13,000. Remember this, huh? The average price of the car is $13,000. But if you look into the median, if you look into the median, it is 10,000. That means looks like there is a skewness in the data. The average is 13,000 and the median is 10,000. So there is a difference of $3,000 in the price. In fact, 50% of the cars are 10,000 or below that. 75% of the cars are 16,000 or below that. And between 75 to 100, you see, it is going from 16,000 to 45,000. It looks like a highly skewed variable. It looks like a highly skewed variable, which we will be analyzing it. After some time, we will be analyzing it, but I just wanted you all to make a note of this. So I say now the next thing is, let us check the information about the data set. So 205 are there and I don't see any missing values. This is what we understand. Then we say cars.head. Now, because we have very less number of cars, uh, if you see carefully, right, I would like to see how many unique car names am I having. And this is what I see. So if you see, even if I look at the repetition of the cars, there are 6 cars. Toyota Corolla. Toyota Corolla are 6 cars. Peugeot 6 cars are there. Mitsubishi 3 are there. And then most of the cars are 11111. So there is hardly any variety with respect to the car. There is hardly any variety with respect to the car names over here. So what am I planning? See, this is the car name and brand, right? Toyota Corona, Toyota Innova, uh, Tata Nexon, you have Tata Harrier, you have this, you have that, and so on. So I am planning that, because I'm not having a lot of variety, let me let me actually only extract the brand names of the car rather than the car names. So I'm planning to do that. So what I do is, see, from this Toyota Corona, let's say Alfa Romeo Giulia, if I'm copying this, this is what I have. I will say I want to extract the name of the car. What is the name of the car? The name of the car is brand name. Brand name is Alfa Romeo. So I say this is to be split on space. And then I extract the value at index location 0. Yeah, you can clearly see Alfa Romeo is being extracted, which means that if I'm trying it out with Volvo, it should be extracting Volvo, which also means that if I'm trying it with Mitsubishi Mirage G4, it must be extracting Mitsubishi. So I was able to do that, and that's exactly what I am now planning to do. So with this knowledge, I decide to do this thing. So I get into the step 2, which is the data preparation and cleaning. So I'm going to do that with the help of a lambda function over here. So we say pay attention. I say on the car name column, if you want, I can show you the right. So on the car name column, I want to apply a lambda function. So every name of the car, let's say Alfa Romeo Giulia, is sent into X, and we are going to split over space and extract 0, which is Alfa Romeo. From here also Alfa Romeo, from here Alfa Romeo, from here Audi, from here Audi. And once it is extracted, I'm saving it in a variable name, which is called as company name, just a variable. And then that variable, which is the company name, I am inserting in the data frame at index location 3. So this insert function has the following syntax: location, column, and value. So I want to insert at what index location? 3. 3 means, see, this is 0th column, this is first column, this is second column, this is third column. So here I want it. So basically here means right from fuel type onwards till the end, these all things will be shifted to the right, and in between column number 3 will get inserted, which is nothing but a column by the name company name. So this column will be inserted, and what will be the content of that column which will be inserted? The content will be this that we populated. So I'm inserting it not at the end but at a specific location, and then I'm looking at the head. And we can see 0, 1, 2, 3. And fuel type onwards 4, 5, 6. This is what we get. And then after that, now if I'll just get rid of this car name column because it didn't had a lot of variety. Brands will have a variety. So I'm just dropping the car name, and I have this. Now let me try to introspect how many unique car names are there. Car name, company name, that this. So company names are this. And this gives me much more information because I see that there are many unique company names. And if I look at the length of this, there are 28 company names. Wow, that's very nice. My question, are all the company names proper? What all are the issues that you see? Which company names are having the issue as per you? And why in very short? Volkswagen, Volkswagen, Volkswagen. Okay, got it. That makes sense. Volkswagen is a problem. Toyota has a typing error. Yes, that's very nicely figured out. Porsche has two variants, which is again an issue. Nissan, yes, Nissan is available with N capital and N small. And Mazda, yes, Mazda is written as Maxda. That's correct. So that is what we see as the issue in the data set. So I guess all of you are referring to the same thing. Am I correct? Just read through this and confirm. Yes. So if you don't do that, and if you directly go for modeling, then that's going to be a disaster. So let me try to help you on this step by step. First, I will try to do the easiest of it. The easiest of it is Nissan. Nissan is available in capital and small. So let's cover that Nissan wala issue. I'll convert every car name to the lowercase. I will cover, I'll convert every car name to the lowercase. So now that Nissan issue is gone. So there were 28 unique brand names, but now there are 27. So Nissan wala issue is gone. And then for all others, I just have to make the spelling mistakes correct. Mazda, Mazda, Porsche, Porsche, Toyota, Toyota, Volkswagen by this. So I will use the replace function. and apply that. So if you see now, this replace function is going to take the old name and the new name. So here when I give a call to the replace function, I say old name is Maxta, new name is Mazda. So Maxta and Mazda are here. I say cars dot company name dot replace Mazda by Mazda in place equal to true. In the same way I'm doing for all, and I'm done. You can take a moment to understand the code. I'm sure you are today at this level that you can understand this code conveniently. Once you understand, just reply with a yes in the chat. Right? Very nice. Perfect. So now the number of brands which were 28 became 27 and now it became 22. And when I apply the value count, see now I get a variety. There are 32 cars of Toyota brand, 10 of this. So this is what helps the machine learning model. One single record will not help it to understand. So it's like, if I say that, hey, this is the price of one of the car, and based on that you predict for unseen data, you're not giving it enough data to study. Now I am giving 32 cars of Toyota to study, 18 cars of Nissan to study. So the model has a variety, except for these cars. Well, in all other cases, there are at least 4 to 5 examples. So that will help the model understand the relationship with the price properly. Then, are there any duplicates in our data set? I need not explain the code. It's just a single line code. I'm just trying to figure out, are there any duplicates? And you know this code. Or you can also say cars.duplicated.sum. Both of them are exactly the same code. It's essentially one and the same. Now, for now, these are the names of the columns that you have. Now, friends, what we have to do is get into the exploratory data analysis. What we have to do now is we have to get into the exploratory data analysis. If you remember, I told you earlier as well that any project will be going through the following stages: business understanding, data preparation, which takes 75% of the time. And the modeling part only takes 10 to 15% of the time. Modeling and evaluation and deployment takes 10 to 15% of the time. And we have some idea about why we said so. So now let's get started with the step number 3, which is visualizing the data. Now, in this process of visualizing the data, I would say you expect relatively less support from my side, because we have spent a good amount of time in understanding the data. So now, analyze this visual first. Rather than focusing on the code, let's first look into the output. Take a moment to analyze this. So if you see over here, look into price. This is the mean and median price. Average price is this. around 10,000. Median price is around 16,000, which clearly indicates that 50% of the cars are below 16,000. 50% of the cars are below 16,000, and the 50% cars are here. So which really tells us that the data is highly right skewed. Most of the cars are below 16,000. In fact, if you look into this plot, which is the box plot, you can see the lowest car price is 5,000, highest is around 46,000. We see 50% of the cars are below 10,000, and 75% of the cars are below 16,000. That means 75% cars. 16,000 is this somewhere here, right? So somewhere here. So 75% of the cars are below this. So most of the cars are budget cars. That is what we understand. And right from here onwards, these are some luxury cars, but they are very, very less in number as expected. And you can see over here, this is Q3 plus 1.5 IQR, and these are the outliers, luxury cars. Did you understand this visual? Is this figure clear? Very good. Perfect. Now let us look into the code. I say, I want to get a subplot of one row, two columns, panel one, another subplot of one row, two column, panel two. That's why you have this panel one and panel two side by side, one row and two columns. Till I say, in the first plot, the title will be car price distribution plot. The plot will be a histogram of the car price. That's exactly what you see over here. You see a histogram. Then on the vertical axis, I want mean and median in red and blue color respectively. Legend also I have specified mean are the mean price of the car and the median price of the car. So we have this legend, X label, Y label, which is price and density. Similarly, in the second plot, I'm saying I want a title, which you see over here. And then I want a box plot, which is this of the price column. Y label, as you see over here, price. Tight layout will ensure that all of these are properly, this name and all doesn't go out. And plt dot show. That's not possible. That's not possible. What are you saying? We'll confirm it. Machine will not go wrong. I am 100% sure about it. Let's check it out. So mean is 13,000 and median is 10,000. Mean is 13, median is 10. So it's correct. Mean is 13, median is 10. Confirm it. Mean 13, median 10. बराबर है ना? No? Okay. Uh, okay. Let me check it out. I was very confident it will be correct only. I went wrong. Uh, plt dot access vertical line and mean and median. Legend is the problem, no? Mean color is red. See, mean is bigger value, median is smaller. So mean is here, median is here. That's fine. I think the problem is in the legend. I'll just add a legend. It was suggested automatically, na? PLT.legend is fine, but the legend is not coming. No art is found in the legend. The legend is called with no argument. Yes. So basically, in it suggested me last time, Copilot. So even I didn't noted it. Perfect. Yeah, good observation. And yes, we understand the code, then I think we are good with it. So I say, and this can be easily confirmed by looking into the describe where I can see the minimum mean is 13 and the median is 10,000. In fact, I can look into the greater details of it by actually looking into not only 25, 50 percentile, but I look into 25 percentile, 50 percentile, 75, 85, 90, and 1. So in the describe, I'm saying I want you to show me these all percentages. Now, if you see carefully, 90% of the cars in the data set are below 22,500. So that means there are only 10% cars which go from 22,000 till 45,000. Only 10% of the car. And that's what is written down in the insight as well. I'll try to plot it once again. So I plotted the same thing, but here in the distribution plot, I looked at the quantile 90% and the 10%. See over here, only 10% cars are here. 90% cars are below this line. So I put forward the following points, which I want you to study once. Read it. Okay. I'm sure you might have read it and you might have understood it as well. I will go ahead now. Now I'm going to visualize all the categorical variables, and by categorical variables, I mean to say this. Now, I want to tell you all one very important thing, that I am not going to spend a lot of time in visualization in this case study, because the visualization is too much in this case study, too much. So basically, I will spend time in analyzing the visuals, but I will not spend time in discussing the code of the visual, because I think we have spent enough good amount of time in Matplotlib and Seaborn, and you should be able to figure it out yourself. First, I did value counts on the company name, where we realized most of the cars are Toyota, Nissan, Mazda, Mitsubishi, etc. And the least cars are Mercury, Renault, Alfa Romeo, Chevrolet, Jaguar, Isuzu. That's exactly what I'm planning to plot. So I say, I got a very nice visual. First, let's look into the visual and then we will look into the code for that. The first is, you see a histogram. Yeah, and it can be properly seen. Yeah. We can see as per the car company name, most of the cars frequency is there on this Toyota, Nissan, Mazda, Mitsubishi, as we said at the least star. Mercury, Renault, Alfa Romeo, and the Chevrolet. To the right side, it's a subplot, right? Of one row, three columns. Here I have the fuel type versus the frequency, which clearly indicates that in the US, most of the people prefer the petrol cars as compared to the diesel cars, unlike in India where people prefer diesel cars, CNG cars. And the next one is the third one where you look at the car type versus frequency. In US, most of the people prefer sedan and hatchback. In India nowadays, most of the people prefer SUVs. And the least popular are the convertibles and the hard tops. Probably they are costlier. And now this is the code for it. Creating a figure of this size. Subtitle is the subtitle for the figure, which is histogram of company names. You see that subplot of 1 comma 3 comma 1 132 133. The first one is going to be the value count on the company name, plotting it as a bar, which you see here. Then title and X label. Similarly, the next one is fuel type value counts, title and X label. The third is car body value counts, title and X label. You can go through the code once. So in this way, there are multiple codes which I will not be discussing going forward, but I'll be giving you time to self-understand it. Look into this. I have the symbolic rating for the car. I see there is no car of the safety rating -3 which is considered the best. But -2 are there, -1 are there. But most of the car which are sold in US are of the safety rating 0 and 1. And here I see its symbolic associated with its price. So looking like this, you can see, let's look at the median price. The cars of high safety come at a price of on an average or median of $15,000. -1 is also more or less the same, but these are more popular. 0 is also more popular. You can see the price goes very high as well in some cases. And look at these unsafe cars, right? Which are of 2 and 3. They are relatively cheaper. People don't buy it. That's also one thing. This one. But these are the most popular. So we create nothing but a histogram. And that is the box plot versus price. So you look into the code now. Figure and subtitle, we understand. Subplot 1, comma 2, comma 1, 1, comma 2, comma 2. First one, count plot of category. That's what you see. Palette is cube helix. And you can change the palette. Box plot of x-axis symbolic, y-axis price. And that is what we see. After that, I am looking into the D type of engine. So engine is of object type, it's categorical in nature. And I'm looking at the value count. So most of the engines are OHC, OHCF, OHCV, etc. And the same is the thing which I visualize over here. So engine type is OHC are the most common. That's what we just saw. And engine type versus price, you can see the OHC engines are relatively cheaper as well if you look into the price. Median price is what you should compare. OHCV are very costly. DHCV are very limited, but they are very costly, and so on. So this box plot which you see on the right hand side, I can also quickly analyze it with the code here. I say that, okay, engine type wise, tell me what is the average price. Engine type was average price. That is what we did over here. So average price wise, we can see the DOHCV engines are the costliest, $31,400. That's exactly what this says. And I can also plot it in the form of a histogram. Car's body of engine type dot mean numeric equal to true. Look into the price and sort it in the descending order. So same thing plotted, but in the descending order, so that I need not search for it. So I can first of all find out the value counts of it. So I say engine type dot value counts. So OHC cars are the most popular. This is what we understand. And then what am I doing? I'm taking the same thing. I say create a data frame of grouping of this engine type by price, which you have just seen over here, and plot a bar plot out of it. And we see the same thing basically. See, basically, whatever I got over here, right? DOHCV is the highest and OHC is the cheapest. We plotted the same thing. Now, this plotting is optional, but because we are doing visualization of the data, we have it, which makes us to conclude that OHC engine seems to be the most favored, and OHCV has the highest price range. DOHCV has only one row. Go through it. Laptop battery needs charge. Okay. Are you all able to understand the code as well? Everyone with me so far? Code is easy and I need not discuss each and every line step by step, right? You should be able to follow the code, right? Yes. And I, even if you say you discuss it step by step, I won't be discussing it because we have to climb ladder after every level. While doing this modeling, that to advanced modeling, if you say I am not comfortable with EDA, that means there is a need for practice, right? We have spent very good amount of time on visualization, so I expect every participant to be aware of this because visualization is going to be a part of everything that we do in ML project every time as well, right? So I expect you all to be aware of this. Perfect, that's good. So this is what we have. Is it because of the count of the rotor and the OHC is low? We are not considering them in the inference. No, no, these are just inferences which I found. You can write your own inferences, which can be more detailed as well. Right. This is just my inferences. If you are a mechanical engineer by any chance, don't try to demean me. I am not a mechanical engineer. But yes, domain knowledge is certainly something which is very important for doing the inferencing. So what you see on the screen are the best inferences which I could come up with from my domain knowledge. Maybe you have a little bit more knowledge about it. Feel free to put up that Anivesh. I hope that's clear. Perfect. So I want to find out the mean price of the car for each company. So what is the average price of Toyota cars? What is the average price of uh, this Mitsubishi cars, etc. So if you look at the average for a price of the car, Jaguar cars are the costliest. Jaguar, Big, Porsche, BMW, Volvo, Audi. And the cheaper ones are the Chevrolet, Dodge, Plymouth, Honda, Subaru, Isuzu, etc. This is what we understand when we look at the average price of the car. I will like to plot the same. So it's just that you get the same code and ahead of that you write dot plot, convert it to the data frame, and I say dot plot dot bar. Finish. Same thing plotted. In the same way, I'm also looking for plotting the average price for each company. So grouping by the fuel type, and looking at the average price as per fuel type. So diesel cars on an average are costing higher as compared to the petrol cars is what we see. And you can look into the code as well. This is the place where I'm finding out what is the average price as per the body type. So we know sedan, SUV, hatchback, these all are the ones. So average price as per the body type, where I understand hardtop car and the convertible car are the costliest. Sedan, wagon are medium and hatchback is the cheapest. Look into the code. I get into the door number analysis. So you can see on the x-axis, I have door number. On the y-axis, I have frequency, which clearly tells us in the left side plot that four-door cars are more in count as compared to two-door cars. And on the right-hand side, you can look at the price. Price of both the cars are more or less the same, although there are some two-door cars which are extremely high. But more or less, I don't see anything significant. And the code is what you have to understand by yourself. Now it is visible over here. Essentially, it's a count plot between the door number, and another one is the box plot between door number and price. That these are the only two important lines, line number 7 and 16. Rest all is decoration, but you can just spend a moment in analyzing it. If you don't understand, you ask me. Then I'm assuming you got this, and now I'm doing the same thing as per aspiration. If you see aspiration wise, standard aspiration cars are more sold, frequency is higher as compared to the turbo. Also, if you look into the aspiration, price wise, turbo aspiration car, the median price of the turbo aspiration car is higher as compared to the standard aspiration. And this is what I wanted to now analyze. See, this is the count plot of aspiration, line number 5, and then the line number 11, which is about aspiration versus price box plot. The rest of the code you understand. Look at the next plot. So if you see carefully, this is how the plots have come. Four plots, four rows and two columns. I said we have four rows and two columns in the inference over here. This is what I think anyone can clearly see. Let us analyze each of this. See here, if you see the first one is the engine location. So engine location wise, front engine location cars are more popular. Price wise, they are cheaper, right? Location versus price. Next, cylinder number, four-cylinder cars are more popular. Price wise, they are cheaper. Eight-cylinder cars are costlier. Then fuel system wise, MPFI and 2BBL are the most costliest. Price wise, sorry, not costliest, most favored or most uh, preferred. Price-wise, idea is the costliest. In fact, there are some MPFI cars also which are very costly. Drive wheel wise, most of the people prefer front wheel drive. Price is also cheaper. Rear wheel drive cars are costlier. So you can see we have created 4 rows and 2 columns, and this is the code for it, which I leave it to your best understanding. I'll write down the insights now. This code is understood. That's an assumption. And these are the insights from the code. Let us go on to the next one, where I'm talking about visualizing the numerical data. And if you look over here, I'm trying to check because I want to go for linear regression. trying to check whether every column with the price has a linear relation or not. So here, car length has a linear relationship with price. Similarly, car width also. Car height doesn't have, and curve weight does not have. This is what we see. And that's the code for it. It's nothing but a scatter function called multiple times. Sorry. So you can see, right, 5 rows, 2 columns created, and ultimately, these are the insights which I want you all to note. The pair plot, I just gave the car's data frame and you can see how much time it is taking for it to come. And now, if I say that, okay, use this to understand multicollinearity in your data set, it is just a next level challenge. And this is still, number of columns are still limited. It can go even more bad. Number of columns are still limited. It can go even much, much more bad. This is what we understand. So something which is next level. So to avoid it, I'm going to do the pair plot, but on a limited columns now. And how do I do that is I say pair plot considering this data frame, but only for the columns, these columns on the x-axis versus price. So engine size, bore ratio, and stroke on the x-axis, all versus price. Similarly, next time these 3 columns versus price, next time these 3 columns versus price. So as you can see, engine size, bore ratio, stroke on the x-axis versus price, price, price. Just to understand linear relationship. Similarly, the next one is compression ratio, horsepower versus peak RPM versus price. And the third one. So you can observe where all we have linear relationships and where all we do not have linear relationships. The same code. It's just that instead of pair plot, I have put kind is equal to scatter. Earlier, kind was equal to REG. If you don't remember, let me show you. Earlier, kind was equal to REG, so it was regression, but now I am doing it for a pair plot. So here, pair plot with kind is equal to scatter. That's the only change. Plots are also the same. You can see which of them have relationship linear with the price. In fact, while creating a pair plot as well, you can also say kind is equal to scatter. So it will only and only have pair plot where there are scatter plots. See, everything is scatter plot except the diagonal. Okay. But of course, this is something which is just not understandable to anyone. But some insights which I could quickly find are these. If we try to get into the correlation matrix by saying cars.core, then this is how blendy the correlation matrix is, which is just impossible for anyone to analyze. Now, the next thing which I'm doing is feature engineering. So what can be the feature engineering that I can do? See, with respect to feature engineering, what am I planning to do is I see the features like the mileage of the car in the city and the mileage of the car on the highway. But a car doesn't drive 50% of the time in the city and 50% of the time on the highway. So I am saying that my assumption over here is that 55% of the times the cars are driving in the city in US and 45% of the time it's on highway. Though it depends from user to user, but this is just a general thing which I have taken. We can play around with this. So I say I create a new column called as fuel economy. Then the next thing which I'm doing is I want to target the price column. So if you see the price column is of data type float. Because the price column is of the data type float. Now I'm planning to bin the price column. So basically I know that most of the cars are budget cars. Then there are some moderate or medium cars and there are some luxury cars. So first I'm going to convert the float to integer. So converting that price column from float to integer because it didn't have any float values as such. Then, then I also create a copy of this data set into temp variable. We also created a copy, as you can see. And then I'm just trying to figure out the current status where I say temp.group by companies, finding out the average price. So we know already we have seen that the average price of the Jaguar cars is the highest. It's not new to us. But I'll be using this. I'll be using this. So remember what I did in the code, right? So temp.group by companies to find out the average price. Then I say further, I will reset the index. When I reset the index, this company name will be created as a new column. See here, earlier this company name was in the index, but now it's a new column. Now, further I say, I'll be taking a left join. See what I do is I say, on the temp, I want to merge the resetted index that is this. Basically these two data frames I want to merge on a left join with this. Right, so this is what I have as the thing after merging. Now that you understood the overall operation, now here I do the main stuff. So what I did is I said that this merging operation, I finalize it. And after merging in this data frame, 0 to 10,000 will be called as budget cars, 10,000 to 20,000 medium cars, and 20 to 40 are the high-end cars. So I said, pandas cut this on the basis of price, considering bins and the carbon, as you can see, and it does the needful. And you can see everything is now divided into bins, and I can actually confirm it by applying value counts. See, high-end cars are only 24. That's what we understand. Then, just to see percentage wise, I see 46% of the cars are budget cars. Then I'm doing the last analysis, which is the bivariate analysis. Have a look at this. As the fuel economy increases, the price of the car decreases, be it front wheel, rear wheel, or the four-wheel drive car. Then after that, the next one. You can look into the code now. Scatter plot of this versus this. That's it. And the U is spread as drive wheel. Then, if I look into the value counts of the drive wheel, you can see most of the cars are front wheel drive cars. Just a little bit of inferencing. I'm grouping by fuel system, further by drive wheel, further by car's range, and looking at the average price of the car. This is what I see. Now, obviously, the result is little scattered and there are 72 rows. So on the same code, ahead of that, I apply the unstack function. So I get it more like a pivot table. And I try to plot this because this is analysis is difficult. So I say same code, after this, wherever NNs are there, I said fill that value with 0 and then plot it in the bar plot to analyze the high, medium, and the budget range car with respect to the engine types. Some inferences which I can make from this plot are these. Finally, from all my analysis, whatever I have done so far, these are the list of significant variables after thinking a lot, which I could gather. The most important variables that I could gather thinking of that, I could get these all things. So I will ultimately select these features. So now there are 28 columns, but for my modeling, which is going to start now, I'm only selecting these features which I said. According to me, this is purely based on the domain knowledge and the insights. Whatever we have got so far, based on that, we selected these all features. How many are they? I think 16. Yes, 16 features are there. So now if I try to plot a pair plot for the 16 features, I think that is still reasonable. Though it is almost 3 seconds, it has not come. So it took almost 4.5 seconds for this plot to come. But this is still to some extent understandable, but could be difficult as well. So now, first thing which I would like to do is dummification. Dummification of all the categorical variables. So we will have to dummify all the categorical variables. So I will like to do it only on the data types which are of the object and the categorical types. So I say which all are the ones. So for column in, select all the data types which are either object or category and show me the value count. So as we understand, fuel type, aspiration, car body, we have seen all these things. Let me not discuss it again. Drive wheel, engine type, and many more. I'll only select the categorical columns of my interest. So these all are the categorical columns. And I will do the dummification of this categorical column. So how do I do the dummification? The regular way, pd.get dummies on this data frame, only this columns, drop first is equal to true and d type is equal to integer. Then, now dummification is over. See now, after doing the dummification, the length of the columns is now 31. Okay. So this is the thing that we did. Now we get into the modeling part. So obviously I will have to get into train test split. So I am doing train test split. Now this is a little different one. So if you see, I didn't divide the data into X and Y. First I'm taking the entire data and just dividing it into train and test. Ideally, first I divide X and Y and then I split it. But this is a little different way. I'm showing you. This is also what you can do. It's not mandatory that you have to follow. But this is what I'm doing it. And after that, I'm gonna scale it. So I scale this. Then after that, if I try to look at the heat map of this DF train, enough to get me go mad. Much enough to get me go mad. But still, I was able to find out after going through this by spending some time, you can do it at your convenience. The ones which are important. Then I have the df train.shape. Then I divide the data into X and Y. This is what I do. This is X train and you can see the shape. 200 rows were there. Now this is what is the shape. And enough. Now we get into the modeling part. Now we are going to get into the modeling part finally. So that is going to be something which will be the most important thing. And before we get started with the model building part, no, because it's a little different topic, what we have done so far, let me first confirm from you, have you all understood it? Have you all understood this model building part? Not model building, EDA part, right? Each of these things is very important. because this is what helps us to understand the overall picture. Now we finally get into the stats model. But before that, we'll just go in for a short 2 minute break and then we'll continue. Just 2 minutes, just for a change of context. My eyes are a little paining. Let me just wash it off. And we start exactly in 2 minutes. Okay? Oh, cool. Please stay connected. Thank you. Just 2 minutes. Perfect. We are back. Okay. Now let us get started with the most important thing over here. Of course, everything was important, but this is also important. We are now going to get started with the model building part. So, yeah. So there we are into the model building part. Now, what did I tell you? See, if you recall, I did say over here that here, now we have understood what all are the exploratory data analysis result, which all columns are important, which are less important, etc., etc. Now here, I have how many columns at this point of time? 30 columns. I want to reduce it. Maybe 10 columns. Let's say 30 is very high. You understand the bigger scenario. Maybe you have 150 columns and you want to pick up the top 30 columns, right? Something like that. So here we have 30 columns and let's say I want to pick up the top 30 columns. Recursive feature elimination. And you know what? This is an algorithm, but according to me, there is nothing great. There is no mathematics behind this algorithm. Or rather, I can also say indirectly that you already know the mathematics for it. What is the name of the algorithm? Recursive feature elimination. What does that mean? Well, that means you got to import it. Okay. So you can see I have imported the RFE. It's available inside scikit-learn's feature selection. I have imported linear regression from the scikit only, not the stats model. But I have also imported stats model. And then variance inflation factor, which is used to identify the multicollinearity, for which I was almost scared when I looked at this plot to identify multicollinearity. I have these things over here. Now, how does RFE work? I will explain you the working of RFE in very simple words, and you will be like, yes, sir, we understood it. It's that simple. Because there is no algorithm as such. In fact, RFE tells us that, Darshan, you give me which algorithm you want to try. Yes. It says, Darshan, you give me which algorithm you want me to try. So I will take efforts to explain you this. So how does RFE do? RFE, recursive feature elimination. It is a feature selection method. So out of 30, as I said, let's say I want to select top 10. Just an example. So what will RFE do? RFE will be creating a linear regression model with all the 30 features. So you have the problem, this. So if you are going to create a linear regression model with all the 30 features, then the equation of the line is m1 x1 plus m2 x2 plus m3 x3 plus dot 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 up to m30 x30 plus c. Am I correct over here? That is how the equation of the line is going to be, right? This is how the equation of the line will be. Yes. Now we know that if you remember the TV, radio, newspaper wala example, the most significant independent variable was what in the TV, radio, newspaper advertising data set? TV, because the coefficient of TV, the M value of TV was the highest. Am I correct? The M value of TV was the highest. So here as well, right? Yes, thank you. So here as well, among all of these, there will be some value of M which is the highest, and there will be some value of M which is the lowest. I will find out the lowest ones. Let's say over here in the process of finding the least value of M, let's say M2 is the smallest value. So I will drop X2. Let's say if M2 is the smallest value, we will drop X2. And now after dropping X2, my equation of the line becomes, not equation, my independent and the dependent variable becomes over here x1 plus x3 right up to x30, because you said m2 is the lowest, so x2 is removed, so this is what remains. Independent variable 2 is out. Now you create a model y equal to m1 x1 plus m3 x3 plus m30 x30 plus c dot 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 dot. Find out again the least value of m and remove it. So let us say the least value of m turned out to be m30. If that turned out to be m30, then you remove x30. So that means now it becomes this y x1 x3 right up to x29. And then you create a model once again. So let's say here you have the least value of m to be something, you remove it, and this process is what keeps on repeating till 10 features are left out. Why 10? Because I will be giving in my parameter that I want to select the top 10. So essentially it is applying the same algorithm again and again, again and again, again and again, every time removing the least important feature. That's it. Because it is recursively applying it again and again and doing feature selection, we call this algorithm as recursive feature elimination. Do you understand the working of this? Very easy, right? Very, very easy, as I told you. Let us also understand variance inflation factor. So here it can be any algorithm in RF. It need not be always linear regression. You can apply any algorithm. Here I am explaining with respect to linear regression. RFE can work with any machine learning algorithm. Now, what is VIF? What is VIF used for? For identifying multicollinearity. So let's look into the mathematics of VIF. I remember I had been talking about this and I had shown you the formula for VIF. So VIF is nothing but using the R square. When you do 1 upon 1 minus R square, you get the VIF. When you do 1 upon 1 minus R square, you get the VIF. So here, as you can see in now, yeah, variance inflation factor. It is the measure of how much variance of a regression coefficient is measured due to multicollinearity. We want always remember this thing. Ideally, VIF should be less than 5. Always remember, if it is VIF, we expect the value to be less than 5 always. If it's greater than 5, it indicates that there is multicollinearity. So, how is VIF calculated for every column in the data set? So, here we say, consider our problem y equal to x1, x2, x3. Now, this is unsupervised algorithm. Unsupervised means you only have independent variables, no dependent variable. So, because it is unsupervised, right? So, I say because VIF is only applied on independent variables or the features over here, because VIF is applied only on the independent variables and features. So I say we have to calculate VIF for each column. So right now, the columns in the data set are only this. We are not talking about Y. We are not talking about Y. We are only talking about X1, X2, X3 because we want to find out multicollinearity among the two, among these 30. So what they do, understand this, same linear regression algorithm comes into picture. So it says that I will make X1 as the dependent variable. See, earlier Y was the dependent variable and X1 to X30 were the independent variable. But now I say X1 is the dependent variable and X2, 3, 4, 5 right up to 30 becomes the independent variable. And obviously for this, you'll be having the equation of the line as X1 giving M1 X2 plus M3 X3 plus so on and so forth plus C. So obviously if this is the equation of the line, for this you can easily calculate the R2 score. And from the R2 score, if I substitute in this formula, I can calculate the VIF. I repeat, first of all, you ignore Y, only consider all the X values. Inside that, X1 will become the dependent variable and rest all become the independent variable. As normal as that, create a regression algorithm to study the relationship between X1 versus all others. And then you get the equation of the line like this. Then for this equation of the line, you will be getting the R2 score using the same way. And from that R2 score, I get the VIF. Next time you calculate x2 versus x1, x3 up to x30, get the equation of the line, calculate R2 and VIF. In this way, you consider x1 as dependent, then x2 as dependent, then x3 as dependent, right up to x30 as dependent. That means you will be getting 30 values of VIF. The first is the VIF for x1, second is the VIF for x2, third is the VIF for x3. You keep on doing it till x30 and any value whatever you obtain over here is greater than 5, drop that. Finish. Is that clear with the mathematics of EIF? Ignoring dependent variable, assuming every independent variable to be the dependent variable and creating models and calculating the R squared, then VIF every time. That's it. I'm also sharing with you some additional resources from where you can start. Same thing what I explained you. It's written over here. I like these good blogs. I think long years back, I referred these links. They still exist. They are good. One of the link is by Amitoj. So you definitely go through this and you have others. Okay. So right now, let's get into the process. Extrain dot columns. These all are the columns. Okay, now after this, how many columns are there? Well, if I look into the length of these columns, I have around 30 columns. Let me create a regression model, not using stats model, but using the scikit-learn initially. LM is equal to linear regression. Then after that linear regression, I say go and fit on X train, Y train. This is what we are doing. And then I say fit on this using X train, Y train. And then it's done. So what happened? Oh, I think I might have not executed this. This code cell. Yeah, I didn't execute. See, it's not executed. Let me execute. Yeah, now it is done. You got a tick. Okay. So that's my linear regression model. Ready? So of course, I know over here that if it's a linear regression model, then it is going to have the equation y is equal to m1 x1 plus c. Then after that, I'll come back to you, Sandeep. obviously in this lm dot coefficient to see all the values of m. So these all are the values of m that we have. Now what will I do is I have to apply RFE. I have to apply RFE. There are so many independent variables. Now I say over here that we will use RFE and select the top 10. See, why top 10 features only? Because we want to reduce the number of features. I'm selecting RFE top 10. Now, here I say, of course, you can select any number of features. I am going ahead with top 10 because I have tried my homework before I come for the session. 10 is good in this case, but in real life, it is a hit and trial. So I say RFE is equal to, I say RFE. The first parameter is estimator, and that is equal to the LM model, linear regression model, which we just created above. And there is a parameter number of features to select. So I do that, and then after that, I say RFE is equal to RFE, go and study over X train, Y train. And if you want, you can see the RFE. So RFE has done its job. So what has it done? Well, if I look into extrain dot columns, if I look into extrain dot column, these are all the columns. Among these columns, which column is RFE suggesting us to select? Well, that can be obtained by looking into the support attribute of RFE. Just like in linear regression, when a model is created, you had lm dot coefficient underscore to look at all the coefficients. In the same way, when RFE is created, you have RFE dot support underscore. So if it is false, it's saying that wheelbase is not selected. If it is true, it says curve weight is selected. The last one is true, that means cars range high end is selected. If this is false, false, true, then this is not selected, not selected, but this is selected. So what I want to do is I only want those columns to be selected where it is saying true. Where it is saying true. So I want only the top 10 to be selected. So I say from the extrain, I want all the rows. Using lock, I'm saying I want all the rows, but only those columns where RFE support is true. And these are the ones you can actually cross check if you want. Wheelbase was selected, cars range high end was selected, right? So wherever it is true, those only get selected. So not wheelbase, curve weight was selected and cars range high end was selected. Curve weight is selected, cars range high end is selected. And you can also look into the ranking. So if I say RFE dot support underscore, instead of that, I say RFE dot ranking underscore. Wherever you see one, those are selected. And after that, you will see 2, 3, 4, 5 for the unselected ones as and when in the order of removal. So we are only interested in one. But yes, support shows us that is the ranking. Let me stitch all these things together, column name, support, and the ranking. Column name, support, and ranking together. I'm zipping it out. Okay. Now what I want to do is I finally want to select only the columns of interest. So extrain dot columns, RFE dot support underscore. So these are the final selected columns. How many are they? 10 columns. Correct. It has 10 columns. So we have these 10 columns selected, and now finally I am going to do the model building using the stats model. So I say from the extrain, only select because this was just for showing you. This is the actual selection. So the top 10 columns are selected. You can count, there are exactly 10 columns over here. In fact, I can show you the shape 143 rows and 10 columns. Now, how do you implement the linear regression using the stats model? And how do you check the VIF? That is what we are going to study. We applied RFE to select top 10 columns out of the 30 columns, Amidosh. Out of the 30 columns, we selected or we used RFE to select the top 10 ones. And that was done using the RFE algorithm using linear regression. Just to iterate over it, we had 30 columns. I said RFE, use the linear regression model and only select the top 10. And that's exactly what we do. Would we not apply multicollinearity? You will get that answer in some time. Okay. Then over here, now this is the time where we finally do this. Now see over here, this is the process for building a model. See, earlier model which we built, see, we created a linear regression model using the scikit-learn. We created linear regression model using scikit-learn, and then that model was using all the 30 columns. Then we gave those 30 columns to the RFE and said that RFE, please select the top 10 most important columns. RFE did that. And now after this, I am going to implement linear regression using the OLS method. So here, how do you do that? Well, because I have to create the model again and again, again and again, again and again, I'm not going to write the code again and again. I just dumped that into a function. So if you see over here, I say x is equal to sm.add constant. What is this? By default, the model which is created by the statisticians, you know what equation it uses? The equation that it uses is y is equal to mx. No C, no C. It will not consider intercept. I don't know why they build it like that, but they will not use C. If you want C to be used, then you have to add constant. You like it or you don't like it, right? You will have to do that. Why? Because it's not there. So every time it is mandatory. Basically, it's a very, very standard code, very, very standard code which is used. So even if I, let's say, go to this and I say over here, not in the agent mode, but just in the ask mode, and I'm not giving it visibility to any of this. I just say that uh, stats model, linear regression, code, example. Hmm. Some dummy example created. Do you see over here? It's a very standard code. It's not that I asked it also. This is how it is. You have to, once you have the data frame, first you have to add constant and then sm.ols. See over here, I added a constant which is mandatory to the x, and then I say ols. So there is fit, but you don't say that sm.fit x train comma y train. No, sm.ols you have to give y train and x train. Obviously, that I'll be supplying over here, but it is not x comma y, it is y comma x. You can't change the order, but it's a very standard code. You can see it's matching, and then fit over it, and then the summary is ready. So that's what we do: fit and then summary and return x. and we do that. VIF part, we'll discuss it later. We are anyways not calling it right now, so it's too early to discuss. I'm not talking about the VIF part. So this is what is ready. So now, right now, this is what is the status. Let's get into model building. I'm creating the very first model. How? I say build. Obviously, this is X-train RFE. So X-train RFE and Y-train is what I pass. I say build the model. So it goes over here. X-train RFE and Y-train goes adding a constant, fitting over Y versus X, and then it will print the summary and return X. So what I get as the output, I'm curious to see. When I this, have a close look at this. Have a close look at this and recall our statistics session now. So here, first of all, it says the dependent variable is price. All right. It says that the dependent variable in this scenario is, sorry, yeah, the dependent variable in this scenario is price. Number one, model is ordinary least square. The method is least square. Created on Sunday, 6 July 2025. So this is what all they print. That's awesome, right? Much detailed than scikit-learn. That's why I wanted to show you this. Created at 12:25 p.m. Number of observation, that is rows, is 53. Residuals and the model. So 10 independent features, and you have the number of residuals, which is nothing but the degree of the freedom, which is number of observations minus number of predictors minus 1. 143 minus 10 is 133, minus 1 is 132. Then covariance type, which is nothing but non-robust, right? Then after that, you also see R square is 0.929. So then I say adjusted R square is 0.923. It's good. Now these are the ones which are coming from ANOVA, F statistics, log likelihood. You have the AIC and the BIC, which is indicators of the model quality. So generally, lower values indicate a better fitting. Then you have the log likelihood, which is used in the statistical testing. Higher values in that indicate better fitting. Then you have the coefficients of the table. We get lot of other meaningful information from this. Now, see how much of it do we really need? See, I will give you a detailed understanding. So I have a detailed understanding of everything, but we don't need everything. Detailed understanding of everything is what I'm returning you, but we don't need everything. We'll go through that later. Now, what you have to look into this, the most important, recall your hypothesis testing hands-on notebook. The p-value that I was always telling you was expected to be less than what value? Do you recollect? The p-value was always expected to be less than what value? Very nice. 0.05. Now you have to ignore the constant column because we added it. Ignoring that, now you look into all the available columns and tell me any p-value which is going above 0.05. Which column p-value is going above 0.05? That is the culprit. That is a culprit for now, which has a p-value going above 0.05 except constant. fuel economy, cylinder number 12. Hmm. Yeah, this is the highest if I'm not wrong. The cylinder number 12 seems to be the highest. So obviously, if you get more than one, then you'll always look at the highest one. Only one you'll pick. Don't pick all. The highest one. The highest one is this. So I say over here, I say over here that the p-value of cylinder number 12 seems to be the higher one than 0.05. Hence, we will consider dropping that. So what I do is I will drop only that column, not all, because you'll not drop all because sometimes what happens, after dropping all, I'll build the model once again. You never know the other values which were above 0.05 again start coming below. So do it always one by one. That's a strategy. So I drop that thing. Now these are the columns. After I drop it and these are the columns, I will once again create a model. My model number 2 with these updated features. My model number 2, I'm building once again this, and this is going to call the same function, add the constant and blah blah blah. I hope you understand. I need not explain. Am I correct? Is this code clear to all of you? The same thing? Yes? Okay. So I do that. It gives me the R square. Obviously, you look into these two values for sure. That's good. 92 R square is good. And now you look into the p-values and tell me whose p-value is the highest except the constant whose p-value is the highest. Fuel economy. Ah, yes, that's correct. Very, very high. That's correct. The fuel economy value seems to be very, very high. So, because the fuel economy value is looking very high, now without thinking over it, I say since the fuel economy feature has the highest p value, we will consider dropping it. So I dropped it. Now you don't have fuel economy. So I will go and build my model again. Now you might be thinking, Darshan sir, what about that VIF? We are coming to that. So I built my model again. R square adjusted R square, good. Now tell me whose p value is above 0.05 except the constant. None? Wow, very good, very good, very good. A big round of applause for this. Finally, we got a very good model as of now, at least. So it's time for us that let us now check the variance inflation factor. So I come down and I give a call to check VIF. I will explain the code now only. So now I am giving a call to check VIF and tell me again ignoring the constant which VIF values are. What is the ideal range of VIF value I said? Ideal range? Hmm. Less than 5. So where do you see the values not following the things? How many columns are there where the VIF value is above 5? Tell me the count. Tell me the count. 4. Yes, 4. 4. Because typing that would be difficult for you. And I guess you are talking about these 4, right? Yes. You're talking about this. How did it compute? You know the mathematics. You know the mathematics, how VIF is computed. But let us get into the coding part of VIF. What it does. It creates a empty data frame. As you can see, pd.data frame, it creates an empty data frame where I say VIF features. So it will be just creating a single column, empty column called as features. So, excuse me. I was saying it creates a data frame, and in this data frame, I'm going to create a new column. The name of the column is features, and the content of the column are all the 10 columns that we have. And then I say, so one column is created by the name features. I say create one more column as VIF. That's exactly what you see over here, right? One column is created by the name features. Another column is created by the name VIF. So, yeah, that's what we had. So what I said over here, for I in range x dot shape of 1. Shape of 1 is nothing but the number of rows. So it will go through each and every row. And what it will do? It will calculate the VIF for all the x values for that ith column. So it is calculating what is the VIF for const, what is VIF for curve weight, what is the VIF for this. And it will add it to a new column called as VIF. But if you see, this column is in descending order. So first I did rounding of this to two decimals. You can see 0.90.10. Then on this column, I said sorted by the VIF value in the descending order. That's what it is done. And that is what is written. And therefore you get this output. Are you clear with this code? Check VIF. Why is it giving this output, everyone? Right? Is that clear? Easy enough, right? You can just go through it once. Understood or not? Are you all clear or not with this? Or you have any questions? Everyone? Is this VIF code clear or you need me to explain once again? Please answer in the chat. I mean, this confirmation is important because we are going to give a call to this again and again. At that time, I don't want any confusion. Okay, perfect. So now we have this. So now, of course, which VIF will I drop? I will drop the VIF whose value is the highest. So I'll start with curve bit only rather than going ahead with all the four at once. I'll start only with the curve bit one by one. So we have decided to drop the curve bit. So I say I drop the curve bit, and this is what are the new set of columns that I have. Now after this, what? Will I check the VIF again? No, that would be insane. Don't check the VIF again. Create a model, and after the model, you'll check the VIF. So I am going to give a call to create a model. You can see that's how I created using the same code. And then I say R square is this, adjusted R square is this. P values, are all the P values below 0.05 as of now as well? Yes. If it is not, then there is a reason to worry. Fortunately, everything is in control. So because everything is in control, I will straight away say let's apply check VIF. And now I can see the VIF for the sedan being the highest. So I say sedan bhai sahab, you get out of my house. So dropping the sedan, and this is what we are having. Now will I check the VIF? No, I will create a model first. And I'm going on with the fifth model. You understood the process, right? Repeat telecast of the things. I create a model as you see over here, R square adjusted R square good. everything good with the p values as well. So we can straight away go for checking the VIF. Correct? No. Why not 4 and 3 together? I just answered it a couple of minutes back, Manu. Why not 4 and 3 is because sometimes when you remove 4 and you create a model again, the column 3 automatically has the VIF value below 5. So there is no need to drop. So that is a linear way of removing the features where you try to retain the columns as well. Is that clear? Yes, perfect. Welcome, welcome. Then now I say over here. Next. P-value. P-value has now let us down. So I will have to address the P-values. Of course, yes. So I will have to consider this car body wagon 0.315. Yes. So we will have to drop that. Yes. So I am trying to check the P-value of VIF as well, of course, but I'm not dropping anything. I'm just checking it. So see, VIFs are all in line. But we are still not good because this is the problem. So we will have to address this problem. So I will say Tata bye bye to this car body wagon because the P value is higher. So car body wagon get lost. And these are the set of columns which I have. Keep on repeating this process till your pain goes off. Right? Just like you keep on applying the ointment till you find relief. So now I'm creating a model once again with this latest features. R square is good. P values looks like all of them are below 0.05. So looks like this is good now. Almost I think we have reached the solution. Let us check the VIF as well. Just fingers crossed to see if the VIF values are good. Oh yes, we can see all the P values below 0.05. All the VIF values are below this, which means we have got the best model and the best features so far. Are you all with me? Does that make sense so far to you? That all the selection of the columns is done? Yes. So, so now I say over here, these are the final set of columns that we have to look into. So I can actually now do the residual analysis of the model where I say, let me finally fit on these latest ones and let us look at the summary of this latest ones. You can see over here, adjusted R is good. P values, everything is aligned. If you want, I can look into the predictions and the actuals as well. So Y train and the Y train predictions, just in case if you want to see it. Anyways, that is optional. And so we have around 143 records, right, which are divided. So you can see over here, 143 is the length of that. And it is expected that in linear regression, when you find out the difference between Y train and Y predicted train, when you find out the difference between Y train and Y predicted train, so basically this minus this, store that value. This minus this, store that value. Keep on doing it for all. So they say that when you do Y train minus Y train predicted, you expect it to give a normally distributed plot. And if you get a normally distributed plot, then we say that the model that you have got is good. And we actually got it. So we just did Y train minus Y predicted train and we plotted it. that is one of the assumption of the linear regression. We say that the error seems to be normally distributed, approximately at least. So, assumption of linear regression seems to be true. Now that we have done everything on the train part, now we get into the testing part. So in testing part, you have not yet done scaling. If you remember, min-max scalar, I only did it on the train dataset. It is left on the test dataset yet. So I take the same columns and I fit on those columns. Then after that, I divide the data into X and Y because test also has to be splitted. So test dataset is also splitted into X and Y. Y test, X test ready. And then I have the following set of columns. And then, yes, Sandesh, that's correct. Then I will now fit. I'll drop the constant from the X train and I will only select the interested columns and I will add a constant on the X test as well, which will be used for prediction. So whatever we did on train, I'm doing it on the test and we are just trying to evaluate the model's goodness. So let me compute the R2 score of the model. 81 is the R2 score of the model. Let me also plot the Y test versus the Y predicted. So it is expected that when you print Y test versus Y predicted, they are expected to follow a straight line. And if this is the case, that is another reason to conclude that it is a good model. So we'll get started now. So coming on to the topic of logistic regression. So what is there ideally in the topic of logistic regression? See, first of all, I want to tell you something with respect to the available algorithms, right? So number one, logistic regression is a classification algorithm. It can be used for binary as well as multi-class classification. However, in the industry, it is more popularly used for binary classification. Before we dive into the mathematics, which is relatively simpler, let us look into the available classification algorithms. Logistic regression, that's one thing. Then you have decision tree classifier, random forest classifier, support vector classifier. Then we have uh, naive Bayes classifier. Then you have Adabos classifier, a nearest neighbor classifier. gradient boost classifier, light gradient boost classifier. Then you have extra trace classifier, extreme gradient boost classifier. Now, what is the moral of the story? Why did I write down the names? We had already discussed these names, is because I want you all to observe one very interesting thing. Classifier, 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 classifier. But do you see the odd man out? Regression. So logistic regression is a classification algorithm. And this in itself is the biggest confusion at the moment. So if so all the algorithms are known as classifier, then why is this algorithm known as regressor? That's an important thing that we have to look into. This is one of the very important things that we have to look into over here. So every algorithm known as classification, then why this algorithm is known as regression? And this is exactly what we will be understanding in our session. And let me tell you the rough reason behind it. Logistic regression is taking birth out of linear regression. So little modification to the logistic regression, to the linear regression makes it logistic regression. So over here, now coming back to the point which I have to discuss. What did we discuss in linear regression? Right. What did we discuss in linear regression? Yes, you heard it right. I'm talking about linear regression. So in linear regression, I said scikit-learn wala thing. We had this problem where we said I have the area of the house and I have the price of the house. And then the next thing that we did is we plotted this data. And then after plotting the data, we had this for which we had drawn a line of best fit for this data. And then we also understand that when we actually did this fitting, then we got the line of best fit. And obviously, if it is the line of best fit, every line has an equation. That's what we understood, where we understood that M is nothing but change in Y upon change in X, and C is nothing but the Y-intercept. Slope is the M, and C is nothing but the Y-intercept. Then, once we have that, the next thing that we understood over here is how it fits, and then how using this equation, let's say the equation of the line is 0.5 into x plus 2, how we plug in the value of x and we are able to find out the value of y. This is what all we have understood. This is exactly what we have understood. Then now the problem is I'm gonna change the problem, but to be solved using linear regression only. I'm planning to change the problem, but I'll plan to solve it using linear regression only. So I say the task is predict whether a person is obese or not obese, depending on the weight. We have to predict whether a person is obese or not, depending on weight. So it's a classification task. As you can see, it's a task of binary classification. Predict whether this is the scenario. So now consider that we have a data. Let's say I have a data like this. Now I have weight as an independent variable and class over here as the dependent variable. So let's say a person, they have given, I am not creating it. Let's say it is given to us by the client only. Weight is 10 and we say the person is not obese. Weight is 70. Let's say the data set says the person is obese. We didn't do that. Data set is saying that. We are not concerned how. Let's say this is given to us 20 where it says not obese. In this way, we have got many records. So obviously, if I have to model this scenario, then mm, 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 mm. What we will do, if you have to model this scenario, I will be considering weight on the independent variable and the dependent variable is class. So let's say weight, right? So weight will go from, let's say in our data set, the weights are up to 100. So we will have to write down the weights. So that's 10, 20, 30, 40, 50, 90. Okay. Let's say this is what is given to us. Now, the thing is, think about how this data can be plotted on the XY axis. Think about how this data can be plotted on the XY axis. According to you, do you think there will be any challenge in plotting this data on the XY axis? According to you, will there be any challenge in plotting this data on the XY axis? Tell me. Do you think there is a challenge or I can easily plot it? What do you think? No technical answer. Simple, basic. No, not straight line and all. I just want to plot a scatter plot. See what we did over here, if you remember. Here I had area and price. So area and price written over here, and you plotted a scatter plot. Line of best fit and all is the later part. So here, how can I have that scatter plot? That's exactly my question is. Is it possible for us to draw a scatter plot? Exactly what Raj said. Y is categorical, and that is the problem. That is the problem. Y is categorical in nature. So here someone says that my weight is 10. I know I have to plot it here, but on the y-axis, where will I go? So what I decide is, because y-axis is either obese or not obese, there are only two possible values. So I'm going to model it using the concept of probability that we studied during the statistics. So let's say I am saying that if a person is not obese, let's call it as 0. And if a person is obese, let's call it as 1. And I am planning to represent this as a probability scale. As you can see, so I am planning to represent this as a probability scale. Now, if you see what my thought process is, person with weight 10 is not obese. So 10 wala is not obese, so I will mark it here only. 20 is not obese, I'll mark it here only. 70 is obese, so 70 is obese, zoop, 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 here. Mark it here. In the same way, all the obese people will get marked over here. As per the data set, all the non-obese people will get marked over here. Now, if I have to draw a line of best fit for this data, if you see, half of the data is here and half of the data is here. But line of best fit is always 1. So can I have a line of best fit like this? No, no, no. This is not a line of best fit. Because line of best fit has, this is a line, right? That's exactly what we're going, this is a line, this is a line, this is a line. But whatever is I did draw is not a line. So according to me, the line of best fit in this scenario looks to be this. The possible line of best fit for this data is this. Because this line passes through maximum points, and the ones which it is not able to pass through are as near to the line as possible. See, I cannot draw one line of best fit like this and one line of best fit like this. Best is always one, na? How can there be so many best? There has to be only one best. So the only possible line of best fit, which is the best as of now, looks to be this yellow line. Am I correct on that? As of now, the only possible line of best fit which looks feasible looks like this yellow line, which I have just write down on. Anyone has any other idea? You can let me know, but I don't think so. Anything else is possible. Right? Yes. So now the thing is, here in this scenario, if I say that, is linear regression able to predict? Ideally, if you see, it should be able to help. Let's say, uh, I'll just keep the chat box open. So let's say a patient with weight 40 comes to me and says, Darshan, am I obese? I say, just a moment. You are 40. I'll go to the line of best fit and I'll come over here. Because the probability comes out to be less than 0.5, I say you are not obese. Okay, then let's say someone else comes, says that, hey, my weight is 60. Am I obese? I said, wait a minute, I'll let you know. I say, yes, you are obese. As per your data, you are obese. Someone says, hey, my weight is just 30. Am I obese? I come over here and I say, you are not obese. Someone says, my weight is 70. Am I obese? I say, I am not obese. So this approach can be perfectly working. We are happy with it. There is no need to go for a logistic regression. Linear regression is awesome. And we need not even think of going for logistic regression in this example. But imagine a scenario where a person says that my weight is 20. A person with weight 20 should be marked as not obese. So person with weight 20 comes over here, and this is where it comes. Now, ideally, it is below zero. If you recall probability chapter that we did in statistics, what is the range of probability minimum and maximum? 0 to 1. So this is something which is against that. And let's say my weight is 100. Who am I? So now this time for me, I will have to come over here, and this probability goes above 1, which is again a problem. So essentially what I want to tell you is this logic is working fine. This logic is working fine only and only if the weight of the person is in this range. This range means almost 28 to 82. This is the only range in which this thing is working fine, 28 to 82. And this is taking decision something like this. So if you see, the decision over here, which is the weight over here, is 55. So the logic is if the weight is greater than equal to 55, obese, and less than 55, not obese. That's exactly how this is working, but it is working only in a short range. It is not working completely fine. So what logistic regression did, it used a very, very old concept of physics. What they did in physics, there is a special function, physics and chemistry, there is a very special function which is known as sigmoid. The sigmoid came in the year 1950. It is not today. It is available in one of the research paper. The sigmoid is denoted by the symbol sigma. And the best part about this is it will always come in the range 0 to 1. Always. It will always come in the range 0 to 1. The second thing is this function is always going to have the S-shaped shape. So you'll see this function to be like this, or you'll see this function to be like this. So it will always be S-shaped and the range will be 0 to 1. Here also it is 0 to 1. So basically the boundary always 0 to 1. This is 0, this is 1. Always be 0 to 1. So it is denoted by the formula 1 upon 1 plus e raised to minus y, where y is equal to mx plus c. So basically, this y is nothing but the equation of the line. So This is 1 upon 1 plus e raised to minus of mx plus c. See now, if I am assuming, mm, if I am assuming that, yeah, assume that we have got the equation of the line as 0.5 into x plus 2. That's exactly what I discussed in the linear regression ka example. Let's say this is the line of best fit, this is the equation. So that means my sigmoid becomes 1 upon 1 plus e raised to minus of. Now what we have to do? If x is equal to 1, then sigmoid is equal to what? If x is equal to 7, then sigmoid is equal to what? In this way, I can compute various values. So how many values of x do I have? Any number of values, right? Let's say 1, 2, 3, 4. So many values are there. All the values when I substitute, I will be getting so many probabilities. Do you all understand? When you substitute various values of x, you will be getting various values of sigmoid. And as I asked you to assume that it is always going to be in the range 0 to 1, which means that every value of x will be converted into some number. Like for example, if I go on to Google sigmoid function, right? So it is saying that, okay, tell me the final value of y. So if you recall, if you recall this, it is asking me that you tell me, listen to me very carefully. You tell me this value. So obviously, if someone says x is equal to 1, it is going to be whatever is the result of 0.5 into 1 plus 2. That value you have to substitute. If someone says x is equal to 7, then whatever is the value of 0.5 into 7 plus 2. So if you look into this formula, it is saying that you tell me the value of 1 upon 1 plus e raised to minus 1. They gave x, but they are essentially meaning the same. So now I know that y is what? Y is nothing but 0.5 into x plus 2. So if x is equal to 1, can I compute y? Yes, of course. If x is equal to 9, can I compute y? Of course. So they are saying that you just give me the value of y. Basically, you do this, and whatever is the result, you tell me over here or here. So let me give a value like 7 and I press enter. Oh, I did not even press enter, it gave. So 1 upon 1 plus e raised to minus 7 is 0.99. So you see the range of the result is between 0 to 1. If I say the result I get is 3, y is 3, then it is 0.95. It is in the range 0 to 1. If I say it is 0.64, it becomes 0.64. If I say it is minus 6, it is 0.02. If I say minus 60, it is 0. Minus 12, 0.06. You give any big number, right? You only try I give 645. It's 1. You try giving, forget about me. You yourself try. Try giving any value over here and tell me, are you always getting the result in the range 0 to 1? Yes or no? Please confirm. Try putting any value. Now, I shared the function with you. Try putting any value and guaranteed the result will always come in the range 0 to 1. Yes. Did you all confirm? Others also confirm. Huh? I think Preetham and Raj did it very fast. Others also confirm. It should always be between 0 to 1. Right? Yes. So sigmoid is a tried and tested function which will always give the result in the range 0 to 1. That's the very first thing which I wanted to tell you. Second thing which I wanted to tell you is, if I look into Google by just saying that I want a sigmoid function. Now look at the shape of sigmoid function. This is the next important observation that you can see. It is always S-shaped. It can be like this. It can be like this. Maybe it can take any one of this shape, but guaranteed in the range 0. This is not sigmoid. This is tangent actually. Guaranteed it will be in the range 0 to 1. Guaranteed 0 to 1 only. Confirm hai, confirm. It can take any one of the shape, but it will be in the range 0 to 1 only. All right. Denominator is always greater than 1. Hence, the result is, that's fine. But it is neither going -1 also. It is not going below -1, below 0 also. If you see that, right? Less than 1, that's fine. But it is not going below 0 also. So it is restricted in the range 0 to 1. Plus, the shape is special over here, Shanu. It's always S-shaped. Always S-shaped. So, I say, coming back to the topic. So that means, you know what I want to tell you? What I want to tell you is, imagine over here we had this data set which consisted of 1,000 rows and 2 columns. Then in this particular scenario, if all of these points are converted, if all of these points are converted into the S-shape function, that is sigmoid, if I am finding out all the sigmoid values, that means this function will also be converted in the range 0 to 1. So you can expect this function to have a shape like this. Now the beauty of this is, now you'll come and say, my weight is just 30. No problem, your weight is 30, you're already on the sigmoid, that means you are not obese. Now Darshan comes and says, my weight is 100. No problem, you're already on the sigmoid, you're obese. So that problem is solved. Earlier, where it was failing for any of the values ahead of this and any of the values below this. Now, this was a gray area earlier, and only this was the area where it was working. But now, because of sigmoid, this has also become workable and this has also become workable. That is what is the advantage that you see in over here. Okay. So that is logistic regression. Give me 10 seconds. 0.5, is it obese or not? 0.5. At 0.5. Sorry, I didn't get this. Hi, this is the one. Na? See here. What I said. See, I said if it is greater than equal to, then it is obvious. So here essentially I can modify this, right? So I can say now if the probability is greater than equal to 0.5, you got it right? Yes, it's obvious. And if the probability is less than 0.5, it is not obvious. And another thing, Sandesh, it does not even matter because in real life, when we are doing the prediction, the things happen directly with the help of machine learning algorithm. You don't have to worry as such about all of these things. So that is something which is the best part of it. Now, there are many other things in the logistic regression algorithm other than this as well, but it is not required. We are good enough to now call this much as the sufficient mathematics, and we can focus more on the hands-on. So I am exporting it out and simply learn morning. Let me explain you what I am planning to do, right? So the thing is, I'll explain you the problem statement as well. So logistic regression on the Titanic data set. And let me tell you, the goal over here is to predict the survival of the passengers using the logistic regression. So here, what I do is, I am going to say, EDA part, we will not be doing it. So if you recall, what all things are the steps which I recommend? You get the data, you do describe info, etc. over the data, EDA over the data, missing value handling over the data. Then I said you do one hot encoding, which we did not do in any of the earlier steps, or we did in the OLS part. So then you do one hot encoding, then you divide the data into X and Y, and after dividing the data into X and Y, what is the next thing that we do? So you have this, you have to divide the data into X and Y. And then after dividing into X and Y, we are dividing it into train test split. And after doing that, we used to tell to the model that go and understand the relationship between X train and Y train. No, 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 no. After dividing it into train and test, we used to say that I want you to scale this and this. Fit transform on this and only transform on this. Am I correct? After train test split, scaling was the step which I recommended. It is already there in our notes. Yes. Remember that, that's very important. Scaling of the numerical variables. And after scaling is done, we were fitting on this. And then I asked it to predict on this. And that used to come over here. Then I asked it to predict on this. That used to come over here. Then comparing this, we used to get the train accuracy or train R2 score. Comparing this, we were able to get the test R2 score. This is what we were doing. Today also we are going to do the same thing. The only difference is now, if you recall, we are working on our Titanic data set. So obviously, the target variable in this case is whether the passenger survived or not. So that is dependent on multiple things like what is the class in which he was traveling, what is the sex of the passenger, what is the fare of the passenger, what is the port of embarkment of the passenger, etc., etc., etc. All right. So, etc., etc., etc. This is what we were saying over here. Now, what are we exactly trying to see? Titanic, you will be like, sir, Titanic is already sank in the year 1912. So what are you going to predict now? People died, their bodies are not even existing, fishes have eaten it, everything. Well, understand the simulation of the problem statement. Imagine it is the year 1912. Okay, so today it's not 2025, but imagine it is 1912 when Titanic sank. So over there, once the Titanic sank, let's say as a data scientist, you received the data for Titanic. So you had received the data of total 891 passengers. But in real, in Titanic, let's say there were 1000 passengers who were traveling. But you're sure about this 891, whether that passenger died or survived. This is what you're sure about. Right. So you know that 1000 passengers were traveling on Titanic, but the data that you could collect from their bodies. So obviously the people whose bodies are found, we know that they are dead, and people who are alive, we have the record of them. Others, we are not sure whether they survived or not. Obviously, it is assumed that they died, but just to be sure, we are creating a machine learning model over here. And how are we doing that? The way we are doing that is we are going to take our data of 891 passengers, divide it into train and test. After dividing into train and test, we'll be fitting on this and we will be predicting on this. So that's my prediction. That's my actual. We'll be also predicting on this. That's my prediction. That's my actual. Using this, you calculate train accuracy. Using this, you calculate test accuracy. So let's say I got around, let's say I am getting around 90% accuracy on train. And let's say I'm getting around 88% accuracy on the test. So I say that, okay, what I have got is a good model. Now let's consider, for example, there is one relative of some passenger whose data is not available over here, who comes to me and says that, hey, my husband's name was Mr. Allen. He was a male. He was traveling in second class. He embarked from Southampton and he paid $29 of fare. But I don't know whether he survived or not. I don't know. Please tell me whether my husband exists or not. So this model can help it to predict with around 88% accuracy. That is essentially what is the end goal of our case study. Are you understanding it now? Because obviously this comes as one of the very obvious question from the participants, that how are we doing it today? Assume today it's 1912 and we are using a machine learning model to get this. Did you understand the point? What are we trying to achieve? Because EDA part and everything remains the same, right? Very good. So now, now that you have this, I think we are good enough. Perfect. Thank you all. So I say, let's do the necessary imports. So I say NumPy, pandas, matplotlib, cborn, warnings, done. I am going to go little fast because at least till modeling part, I'm gonna go little fast. Why? Because you already know how to create a model. Am I sorry, not model. We have already done EDA on this. So obviously I'm not going to do exactly the same area what I did over there, and my speed will be relatively faster. And you should be okay with that. So I say over here that I have done the necessary inputs. Now df is equal to pd dot this. This is our data frame's head. That's perfect. Df dot shape. 891 passengers were traveling. We have 12 columns. Now I need not do the explanation of this data or analysis. We know that passenger ID is the ID of the passenger. Survived 1 or 0, whether the passenger survived or not. Passenger class 1, 2, 3. Name of the passenger. Sex of the passenger. Age of the passenger. Sibling and spouse count of the passenger. Then you have the parent and children count of the passenger. Then you have the ticket. Then you have the fare paid. And thereafter, you have the cabin and the port of embarkment of the passenger. So this is what we have in so far. So now we know there are three ports of embarkment, everything. So I'm not going to get into that, and I'll focus on the important stuff. So I'll make a note over here. Our data set was already explored during our EDA class. So by default, it is expected that you explore every project before coming for any conclusion. Since we have already explored and we remember the findings, I will be doing minimal EDA and straight away jumping into modeling. However, for any real life use case, you are strongly recommended to focus more on EDA to extract the relevant features and get the insights from the data before proceeding to modeling, so that there is no confusion. So now df.isInA.sum dot sort values. So we understand over here that cabin column has a lot of missing values. So we will drop it. This is what we had done. And then I check it. Then for embark column, we will replace it by mode. So df dot embark dot value counts. So we understand that since most of the passengers embark from Southampton, we will fill the missing values by Southampton. And I'm once again checking it. That is done. Then for numerical column, I said we will either fill it by the mean or median. So df dot age dot Skew, let us check the skewness in the column. And we got the skewness value as 0.38. So if you remember, we did go over here and I googled for skewness range. I can see I came on to this website and I gave you this insight. So I said over here that if the skewness is between minus 0.5 to plus 0.5, then we say it is almost symmetrical, and it is. So therefore, we decided to fill the missing values by mean. So I say, since skewness is between minus 0.5 to plus 0.5, we say age is almost symmetrical. So let's fill the missing values with the mean of the age. And this is all done. I hope all of you remember that we have already done this, and I'm not appealing to be going very fast, right? We have done this slowly and steadily. We invested almost 5 hours on this EDA, right? Yes. One complete session was gone, and next session also 1 to 1.5 hours. So almost 5 hours we have invested on this EDA. So I think I can be confident about going ahead with this way. Right. Okay. So that's what I have. Huh. So this is done. Now I say we did go for feature engineering. The first feature that we engineered was we found out the total of the sibling spouse plus parent children was nothing but the family size. So family size was this. This is what we engineered. And then from the family size, we also figured out whether a passenger was traveling alone or not. So if someone's family size is 1, that means he is a solo traveler. So next is is alone, where we use this. Just let me know anyway, let's say for some reason you have forgotten something. Let me know, I will explain. It's by default, I'm assuming you all are perfect with it. So we did this. Now, once you have this is alone wala thing, the next thing that we engineered was the gender class. Right, so gender class was another thing that we engineered. So what did we say in the gender class? So I say if age is less than 15, then child, else sex as either male or female. So df of gender class is equal to df dot apply lambda dff. If age is less than 15, we said child, else whatever is the sex. And this is what we got. So now if I say df dot gender class dot value counts, we see that there were 78 children traveling on the Titanic. Then after the gender class, we went ahead with the uh, title column. After the gender class, we went ahead with the title column. So from the name, we are extracting Mr., Mrs., etc. So title. extraction. So, I mean, you remember, right? First we split it on comma, then we extracted index 1, then we split it on dot, then we extracted index 0, and then we stripped it. So that's the same thing, split it on comma 1, then split it on dot, and then we stripped it. So title column extracted, and this. Just let me know in case any one of you is not comfortable or not understanding. Please let me know. By default, we spent a lot of time, so I'm assuming that we all are aligned. Okay. So this is done. Now what we want to do is I want to merge uncommon titles into the following categories. Yeah, that's done. And we understand. We have seen that logic. That logic is also already written, I guess. On this page somewhere we have written down the logic as well, on the basis of which we combine. That's okay. I think we got that using ChatGPT that time. So that was also. We have this. Now, before I go ahead, you have to tell me one thing, that logically, let's say if you have to predict whether a passenger survived or not. Okay, forget about that. Let's say you are working for a company like Walmart, and there are various employees who are working over there. Let's say one of the employee is Preetham. So now we have to decide how much percentage hike is Preetham going to get in his salary. Let's say currently he is drawing around 12 lakhs per annum, and how much percentage hike is Preetham going to get? So his manager is like, okay, Preetham, so all the employees who are having their names starting from anything between A to M will be getting 15% hike. And if your name is starting from N to Z, you will only get 4% hike. What do you think about this logic? Is that logic good for figuring out the increment to be offered to anyone in the organization? It's biased. Does not make sense. In the same way, now I want you to tell me that if we have to predict whether a passenger survived or not, do you think the passenger ID would be a factor for survival? Like the passenger, like let's say the captain saying that, okay, all the passengers who are having even passenger ID will be sitting on the lifeboat. No one else is allowed. Only if your passenger ID is an even number, you are eligible to sit on the lifeboat. Else you are not. You find out your solution by yourself. No. This is where I want to tell you that this is not a useful column for prediction. This is not a useful column for prediction. For predicting whether a passenger survived or not. How about passenger class? Is passenger class important for predicting survival? Ah, yes, we actually saw it that time also. Is name helpful for predicting survival? So it's like, okay, your name is Preetham. Okay, Preetham, come, you will survive. Your name is Darshan. No, I don't like that name. You will not survive. No, it cannot happen like that. So that's out. But before dropping that, I extracted meaningful information from this. This is worth thing that you need to note. I didn't directly drop it. I tried to extract any meaningful information. This is very important because this information will support the model. Is sex important? Is sex important? Yes. But do you see gender class which actually has sex also? Gender class is anyways having sex. So if I keep this as well as I keep this, there will be multicollinearity. Gender class has male, female, and child. That is more informative as compared to only sex, which is male and female. Therefore, I will keep gender class and I'll drop sex. Got it? Yes. Is sibling, spouse, and parent children important? See, using sibling, spouse only, we got family size. So obviously there will be a multicollinearity between these three columns. So multicollinearity means out of these three, we have to choose any one. So better I keep family size because family size is combined information. So again, I'm gonna drop siblings, spouse, and parent children. Ticket is not having any numerical value or categorical value. I will drop them. Fare is important. More, more fare paid, they survive. Embarked is important and rest all things are important. So what am I doing is I want to drop columns that are not needed for the model. So the first one is passenger ID, name, sex, sibling, spouse, parent, children. Yes, is alone can also be dropped. That's a very important point. But see, is alone contains some meaningful information. I understand there will be a multicollinearity, but is alone is having a business sense. If someone's wife comes to inquire or someone's relative comes to inquire, then whether that passenger was traveling alone or not is an important factor for predicting survival as per us. So we are keeping it. We will try going ahead with the model. If it is not performing good, then we will drop it and find a model again. So for now, because I am a little bit skeptical about it, I am going ahead. Later on, I will create one more model without that, and I can compare the performance of the two models and really decide it is good or not. Just see, you have to take that risk, right? I may be wrong, or Sandeep may be wrong, but we have to try it out ultimately. Yes, family size can do. Agreed. So that's what I said. I may be wrong, I may be right. Just because I have that little doubt in my mind that it has a good business sense, I'm not I'm not completely willing to drop it for now. Later on, we'll see. We can try dropping it and seeing it if it is helpful. So, mm, what is the next step that I'll be doing now? Tell me. What's the next step? Next step. EDA done. One hot encoding. Yes. So now I will be doing the one hot encoding or what you call as dummification of columns embarked, then gender, class, and title. Correct. So do the dummification. These are the columns. Drop first is equal to 2 and D type is equal to enter. Don't forget that. And it is done. Then after this, I'll be splitting the data into X and Y. So X and Y ready. X is everything other than survived and Y is only survived. And then I'm going for train test split from sklearn.model selection, import train test split. And we do this. And then I'm printing. When do we do the scaling? Do we do the scaling on this data or yes? After train test split, Amitoj, remember the first step is divide the, the first step is you load the data Then you handle the missing values, EDA. After that, you divide the data into X and Y. No, you can do that. And after that, you do one hot encoding on the categorical variables. Then you do train test split, and there you apply scaling, and then you go for modeling. So after train test split, this will come. These steps are already written in our very first linear regression case study of uh, advertising data. No problem, no problem. Remember it. In our advertising data, we had written down the steps. I think someone else might have also forgotten. I'm pretty sure about it. So, but these are important things. That's why I had written it down. I don't know whether it was in this. Yes, here. This is important. The day 3, 5th July wala resource. Load, explore, one hot encoding, divide into X and Y, train test split, then scale, then model. All right. So essentially, put it over here. No, that will be helpful for you in the long run. It's very important. And yes, what has Anivesh shared? Oh, and Anivesh, share the link for this image from wherever you found it on the internet. So this scaling is done. Now we go for model. So I'm going to come over here and I say from escape from dot linear model import logistic regression. So as you can see, I am going ahead with the logistic regression and I am going to create a model called as logreg, which is logistic regression, and going everything ahead with default. Logistic regression dot fit over extend y train. Same thing, right? Absolutely same. You create a model. Right now, going ahead with the default logistic regression dot fit over extend y train, and then I can ask it to predict on the training and testing set. So I say y prediction on train. So logistic regression will predict on this. Logistic regression will predict on this. And how do I figure out whether the model is doing good or not? By looking into the accuracy. So we have accuracy score and confusion metrics and classification report as three of the metrics over here. We will talk about this. First, I will only do the evaluation. So I say train accuracy. See how easily you find it out. So I asked the logistic regression that first import, then you create an instance, then you fit with that model. After fitting, I'm asking it to predict on X train, predict on X test. And then I say that just like R2 score, just like mean square, I'm just saying accuracy score. That is the only change in the function name. Rest, the code is same, right? Y train, Y predicted train. Y test, Y predicted test. And look at the accuracy. On the training data set, I'm getting less accuracy. And on the testing, I'm getting more. Quite odd. On the training, more accuracy, testing less. So I'll do one thing. Maybe my random state is not good. Let me try random state at 0 and try to rerun the things. 83 and 81. Yeah, that's fine. That's fine because train accuracy must be higher than the test accuracy. Did we get a good model? Yes, we did get a good model. Now, there are a few important things. See, the implementation comes to an end, but there is also one more, which is called as confusion matrix. I want to show you that. So just like I gave accuracy score, Y test, Y predicted test, this accuracy score I'm replacing by confusion matrix. Have a look at this. Now, what do you understand from this? Well, uh, we understand over here 98 people actually died, and the model predicted that they actually died. But 48 people actually survived, and the model predicted that they actually survived. Similarly, 21 people actually survived, but the model predicted that they died. And 12 people, they actually died, but the model predicted that they survived. So I say, I'd like to show you something. The topic is not over. Huh? So maybe if you have any questions, please stay connected. So don't look. Are you looking into the code, Manu, by any chance? I'll come back to it. Let me first explain you the concept, and then I'll give you opportunity to understand that. I will change the random state na here. Here, where did it go? Just a second. It's automatically scrolling down. I don't know why. Just a moment. Here, the random state was 42. I made it as 0. Right. So obviously the shuffle changed, and because the shuffle changed, everything changed. Okay, cool. So got it, right? So now here, first of all, I want you to only observe this image. Consider it is the COVID time. Wait a minute. Why am I investing time? I remember we had statistics class where we had discussed this. Am I correct? We had discussed this example, right? Ah, very nice, very nice. And I also told you it will be very helpful during the machine learning. So today the day has come. I will still go through it once, at least 1 minute refresher. So here I was saying, we see over here that there were, let's say if I'm comparing with respect to the COVID time RT-PCR example, then we understand 100 people actually survived and the test predicted that they survived. True positive. 50 people actually did not survive and the test predicted that they did not survive. True negative. 5 people actually survived but test predicted they did not. And 10 people actually did not survive but the test predicted that they survived. This is what we have got now. Now, this is what we have got with respect to our Titanic data set. So, what do we understand? See, it's quite obvious for anyone to understand what they are trying to say over here. So here, I'll delete this and see. So how do we actually figure out this? So this is the status, same thing written down. So we understand how many true positives, true negatives, false positives, false negatives are there. Now, you know what? How is accuracy computed? So the accuracy which we got, what is the accuracy that we got? We got 81.56% accuracy on the test data set. And this is the confusion matrix for the same. If you see, if I just say confusion matrix, you can, first of all, I just observe how the results come. So the confusion matrix gets printed in the form of a numpy array. Yes, out of 891, that's correct. Confusion matrix gets printed in the form of a numpy array. So I don't understand this. So I printed it in a nice way. How? I said that let this numpy array get converted to a data frame. That's what I did. I saved confusion matrix into this variable and I then printed a data frame. And this data frame ka index will be labeled as this rather than 0 and 1. It is actually that actually survived. Columns are labeled like this: predicted, that predicted, survived, instead of 0 and 1. Right? So you understand. And how did we get the accuracy as 81.56? So you know what is accuracy? Accuracy is 48 plus 98. Look at the 48 plus 98. Total of this diagonal divided by total of all four. 48 plus 98 divided by 48, 98, 12, 21, 81.56. So the model is 81.56% accurate. Now, we also talked about precision and recall, where I said precision is minimization of false positives and recall is minimization of false negatives. So, precision is TP upon TP plus FP, which is 48 upon 48 plus 12, which is 80%, which means when the model predicts that someone will survive, it is correct 80% of the times. When the model predicts that someone will survive, it is correct 80% of the times. On the recall, we have 69.57% accuracy, which means when the model identifies around 69.57 of the actual survivors. Similarly, you have the precision for died and precision for recall. Insights. The model is accurate at predicting deaths than survival, with better recall and precision on the died class. It struggles with false negatives. 21 people who survived but predicted to die in this critical scenarios. As per Python, the true negatives always come first. TP doesn't come. Here TN comes, here TN, then here TP. And then over here FP and FN. Though it can be represented in 4 different ways, but this is the Pythonic style. So where can you find it? If you go to Google and you Google about from sklearn.metrics confusion matrix, on the documentation page, you will find this is the style which they follow. No, collab, forget. Python follows this. Let's figure it out. Okay, let that not be a confusion. If that is confusing you, see here. Forget about collab. Let's look into official documentation. You see this TN, FP, FNTP. So it is always first is TN, then FP, then third is FN, and then it's TP. See here, this is the format. TN, right? This is 0, means no, truly yes, false positive, false negative. This is the format which it follows. Don't get confused. Linear model, import logistic regression, and I created one model of logistic regression. So I created an empty model, but inside the logistic regression class, there are so many hyperparameters available. So many are available. Now, do you practically remember the functioning of each and every parameter? Answer is no, but I would like to definitely add on some things over here. Starting with it. So here, in this hyperparameters. What is penalty? What is dual? What is tolerance? These all things. There was a time when uh, understanding these parameters was very difficult. But now it is really easy because if you now look into logistic regression scalar, these are the parameters. Explanation about that is already written here. What is penalty? It is used in the scenario when the model is overfitting. What is dual? And you don't have any detailed information. This is the official documentation. It only talks about this. It only talks about this. This is the official documentation. So whatever information you get it from here. But today, if you go to ChatGPT and put this hyperparameters and ask it, then explain this hyperparameters to me in a simple way. And what are the commonly used ones in the industry? It quickly helps us understand this. In fact, this is what I have got it using ChatGPT only to make you understand that even without knowing these parameters, you can still make some educated guesses. So how many of the people in the industry actually know it? Honestly speaking, as good as 0%. No one knows these parameters. They know how to play around with that, but no one knows the mathematics behind each and every parameter. Like here, penalty specifies the regularization strength. Now, regularization in itself is another 3-hour topic, but a penalty is specifying the regularization strength. As I told you, it is used to avoid the overfitting. So there are three types of regularization: lasso, ridge, and elastic net. The most common is L2 and the default is also L2. Dual, by default, you set it to false only. You can say commonly used false. Tolerance. Tolerance for the stopping criteria. How many times you want the model to keep on fitting? So here, this is what we have. C is a regularization strength. Most common value is 0.01 to 100. Default is 1. Smaller values mean stronger regularization. And this is the important tuning parameter. Because logistic regression comes out of linear regression, fit intercept is there and it is to be true only. Never make it as false. Class weight, default is none. If the data is not balanced, you can put is equal to balanced as well. Random state can be any number. There are various types of solvers. Linear is good for small data sets. LBFGS is fast and works with most of the cases. And Saga supports L1, L2, and elastic net only. Max iterations is how many number of times you want the algorithm to run before it predicts. Multiclass default is deprecated. Common values are this. So whenever you are doing binary, non-binary problem, you set it to OVR. And then verbose is set to true. Warm start is rarely used. Number of jobs will understand more better in decision trees. So these are the most important hyperparameters and the most common values of these hyperparameters. So now they say that, okay, this is what you can try. So I'm going to play around with the value of C over here. Let's try C as 0.5, 83, 81, not that difference. Let me try increasing C. And you can play around with multiple combinations, but I'm just trying out. Oh, 83 and 81, little increase, little increase. Let me try another set of logistic regression parameter. So I'm trying out C is equal to this penalty solver, rest all things remain same. You see, I got 80.78%, which means, see, one important note, what all can we do to improve the performance of the model? Number one, creating more features. That can be one important thing. Next is hyperparameter tuning. Third is change the train test split ratio. Fourth is change the random state in train test split ratio. Fifth is try different scaling. So now, and the sixth is try different machine learning algorithms. Now, this is what definitely I'm keeping it for later. But what I want you all to do now, what I want you all to do now is I want you all to not work on this problem statement, but let me see if I have anything else. I have it. Just a moment. The reason we didn't do RFE VIF is because we have less columns. RFE is used when you have more than 100 columns. RFE is recursive feature elimination so that we are able to select the columns. Hardly 10, 12 are there. So obviously we don't want to reduce it. Therefore, we didn't use it. I'm going to give you one data set now on which you are going to work. I'll tell you what is the name of that. Right, because the columns are less, right? So we eliminated everything manually. I want you to now work on a problem. I'm actually getting that data from Kaggle only so that you have a sample code as well that you can follow along. We'll go ahead with this. Hard disk prediction. I am doing one thing. Task to do now. So this is the notebook. I'll just confirm if the link works. Yes. So this link works. Now what am I doing? See, listen, all of you. The task to do now is shared with you here. So this is the task to do now, which I have given you. When you click on it, you have the data. You can go into the input. Oh, data set is no longer available. Then you go ahead with this then. Breast cancer. Right, so this is the data that you will be using. You go ahead with the breast cancer data. This notebook is there. This notebook is there. So if you scroll through this, they have prepared the entire notebook. You have to follow my approach and try to see if you are getting more better accuracy than this. Okay, I'll also be very much straightforward and inform you. I don't want to beat around the bush. This is where I am there in the session. I am there in the session as a support, but I am not actually going ahead with teaching anything new today. So maybe we have the session for another half an hour where I would want you to execute this. Execute, not only execute, prepare it from the scratch. This has to be done today itself. I have got some medical emergency right now. I told you, right? Morning only I had the medical emergency, but I didn't disclose that because I'm all okay. My kid is not well, and the doctor, what do you call, on today, he is only available till around 1 o'clock, right? So I have to leave. I will be available in the session. It's not that I'm not available for any kind of support. I'm traveling in a cab, but I will be available over here. So I want you to work. I'll be connected to my internet. I'm carrying my laptop, everything. You have to work, right? Yes. So I want none of you to drop from the session, but I want you to work on this problem. I want you to work. So, and if you have any issues, I'm there as a live support. Ideally, I could have completely hidden that, okay, you continue, do this, do that, but I'm being very frank. So I want you all to do this. Once you are done, we'll definitely end it early, maybe by around 12:15 or so, but I want you all to work on the problem statement. Thank you very much. Thanks a lot, all of you guys. I can see your messages. So, uh, you know what is the problem statement, and this is what I want you to get started with. Now, there are some more metrics which are actually left out for me to be teaching you. So, that is what I want to. So, first, we are doing the necessary imports. Then we read the Titanic data set. You know the target is to predict survive. So then after that, we handle the missing values appropriately. And now the data has no missing values. Then we engineered family size. Then from family size, we engineered is alone. Then I also engineered gender class by this logic. So I figured out there is 78 children who are traveling. Then I engineered title column where we found there are so many titles and we merged them broadly into four because they are having huge numbers. And this is the status. Then, because I wanted to predict survived, passenger ID will not figure out whether a passenger survived or not. And so our name, sex, not relevant because sex is not relevant because we already had gender class. Siblings lost parent children obviously will have multicollinearity with the family size. So we dropped it and ticket number is not categorical, not numerical. We dropped it. Then we did one hot encoding of embark, gender class and title. Now I divided the data into X and Y. This is what we did. Then we did train test split. After doing the train test split, we have this, then we scaled it. So obviously we got a good accuracy, but it can be improvised. You can try changing the scaler. You can try changing the random state. You can try changing the train test split ratio. So we do that. Then I created one model of logistic regression. And understand this, we have already done it multiple times. You imported it, created an instance, fit on it, predict on train and test, and then you have the metrics, right? So accuracy score, confusion metrics, and classification report. So we saw that we calculated the accuracy, and when we got it, we got our model. This result, we see we have got a good output where we got the accuracy to be 83% and this to be 81.56%. So obviously, when I am getting over this, I can actually, where is this? Here. I can actually say that with respect to accuracy score, both of these are above 80, which is a strong baseline performance for the model. There are no signs of overfitting as well because they are very close to each other. And the model is definitely suitable for deployment. Next, I can add more features. I can try playing around with the regularization strength. I can compare with other classifiers like this. Right, so this is what we understand over here. So this is what we overall understand over here. Now, what will I do is see, we also calculated confusion metrics for the test data set and we got these results as the confusion metrics and you understand it very well now. I also explained you some other metrics over here like precision, recall, F1 and this. Then I also want to say is I also want to calculate the classification report. So classification report uh, is also nothing but this. I'll show you in very simple words. How does it look like? So if you see over here, confusion matrix of Y test and Y predicted test. And I say classification report of Y test and Y predicted test. So basically syntax is the same. And you see it's looking very bad. So you can do this, you can put it in print and now it will be perfect. So basically the code is same. Confusion matrix, Y test, Y predicted test, classification report of this. Now, what we want to do is, see what I did over here is I am having more or less, if you see carefully, I am having the same results here also. I'm not having anything different, absolutely same result. If you see over here, I am calculating that, saving it into this. After saving it, I am saying convert it to the data frame and transpose it because I want it to be like this. See, this is also okay. This format is also okay. And this is also okay. Uh, Support is how many examples are there for diet. And wait, na Raj, I'm explaining that before only you are asking questions as if I have left the topic. Wait, have some patience. Did I leave the topic? I said that, okay, let's go ahead. Did I do that? No, no. So I'm explaining that. Here, if you see what is support? Support means how many examples are there for the passengers who died. In our data set, there are 110 examples in the test data for the passengers who died and 69 for the passengers who survived. You know the precision and you know what is recall. So this is the precision for the passengers who died. This is the recall for the passengers who died. So if you see, I'll get a tabular understanding here. So precision is 82.3540, which means 82.35 of the predicted non-survivors were actually survivors. So you said they did not survive, but they survived. Similarly, the precision over here for one is 0.80, which means 80% of predicted survivors were actually survivors. Similarly, recall of 0, which is 89.09, which means model identified 89.09% of actually non-survived correctly. And here recall of 1 is 69, which means it identified 69.5 of actual survivors correctly. Now, F1. Let me show you the F1 score formula. So friends, the ultimate formula for F1 score is this. 2 into precision into recall upon precision plus recall. Right, so this is the F1 score formula. I just pasted the link for it. So F1 is computed. So what is F1? So let me tell you, F1 score is considered as the harmonic mean of precision and recall. Basically, it will give equal importance to precision and recall. So they say F1 score is preferred when the class is imbalanced. So like, see, this is 110 and this is 69. It's not 110, 110, neither it is 69, 69. So whenever little imbalance is there, they say F1 score is also a good metric rather than accuracy. So here we got the F1 score for class 0 as 85%, which means the balance performance for non-survivor prediction is this. Similarly, for 1, it is 74%. And support is this is what we already understand. So if I look into overall evaluation in this, we can say that our accuracy is 81.56%. Now, where is this here? This one accuracy is 81.56%. Overall accuracy is 81. So this one, sorry, 81. Actually, it is the same value pasted everywhere, entire same value, because obviously I can't have different thing. Or if you want, you can also see this also. This is how it gets printed. Only accuracy. So accuracy is this much. Okay, so it is rounded off below. So here it is rounded off because earlier in the later one we returned it as a dictionary. It is not rounded off. So this is what is the accuracy, which means 81.56% of the total predictions are correct. Then you have the macro average. Now that's not really very important, but we will talk about it. Not very important. You can completely ignore it if you want. So macro average, as you can see, is having the precision value 81, recall is 79. So macro average is 80, where we say average F1 treating both the classes equally without any weighing is considered as macro average. And similarly, the weighted average is 81.45 as per this, which says over here that overall precision adjusted for the class size. Now, you can actually ignore the macro average in both the cases. What is more important is to focus ideally, if you're talking about this, focus on accuracy and the precision and the recall for both the classes. We have seen what is the importance of precision and recall with respect to the problem statement. Therefore, the first three rows are the most important. Others are not relevant in most of the scenarios. So that's one thing. Then I want to tell you that after this, I want to do some more. So what am I doing is I'm adding some things over here. So I want to talk about few metrics. Few metrics, which is nothing but the area under the curve. I'll tell you what I exactly mean by that. I'm just looking for a perfect image on the internet. When you have a confusion matrix, the true positive rate is TP upon TP plus Fn, and the false positive rate is this. And if you look into this, right? So TP upon TP plus Fn. What is TP upon TP plus Fn? Sensitivity. See, TP upon TP plus Fn is nothing but sensitivity. And FP upon FE plus Fn, which is FP upon FP plus Fn, which is not in this case, but that is what is called as the false positive rate. So I was saying, when you plot this false positive rate versus true positive rate, you get something which is called as a curve. Now, I'll zoom it, right? So now, listen to this. This curve, if you see it, zoop, zoop, it's perfect like this. Look at my hand movement. If it is right angle like this, then we say This curve is called as the receiver operating characteristic. I'll explain. Don't ask any questions. That curve which is going like this is called as the ROC, ulta L, right? Inverted L. So this is the ROC. You can also get that curve like this, right? You can also get that curve like this. You can also get that curve like this. So what do you understand basically? See, if you get that thing like this, we say the area under curve is 100%. This is another metric, just like precision, recall, accuracy score, F1 score. This is another metric. AUC is 100%. That means it is awesome. Now you'll be like, which to refer when I'm talking to that. First of all, you understand this. First, you understand metric. Don't get lost anywhere else. So area under curve is 100%, which means it's very good. We want this to be above 0.8. If you have a curve like this, it is 75%, which is not good. If you have like this, it means that the model will 50% of the times predict perfectly, 50% imperfectly, which means the model is randomly guessing. It's worst. It's worst. And this is just something which is not possible. Problematic. So now, when I say AUC is 100%, this is how your confusion matrix looks like. You know, this makes you perfectly understand. So I'll do one thing. Have a look at this figure. See, one mountain is for true negative. One mountain is for true positive. When everything gets classified as true positive, true negative, and these mountains don't mix with each other. Remember this, when these mountains don't mix with each other, that means there is absolute perfect separation between TP, TN. So it's like your confusion matrix will have FP and FN ka value as 0. Just like you can consider this example. Here, if you see, these mountains are not intersecting. That means this is TN, this is FP, and FN and FP are 0. But here they are intersecting. And here, though, my God, they are intersecting a lot. And here it's a case of error. So now, if you look into this, we want this intersection to be as minimum as possible. If you remember, I said precision focuses on minimization of false positives. So this is visualization of confusion matrix. Huh? This is visualization of confusion matrix. So I say FP and FN. When I say I want to minimize this, I'm focusing on precision. When I say I want to minimize this, I'm focusing on recall. So this is the status in between the two, and there is absolute no separability. And therefore it is 100% because there is no FP and FN. Here it is 75%. So there little bit overlap is there. And here a lot of overlap, therefore it's 50%. 50% means worst. It is randomly guessing the passenger has survived or not. So you are actually plotting out this. So now look into this. If we have three models where you have plotted the true positive rate versus the false positive rate, then if you get something like this, 100%, perfect classifier, awesome. If it's like this, little bad. This is little more bad. This is little more bad. And this is worse. 0.5. 0.5 is the worst that it can take. 0.5 is the worst value that it can take. So let us actually calculate that, and then I'll explain you the understanding of this in more detail. But first, let me ask you whatever we understood so far, right? So the area under the curve, so this curve is called as receiver operating characteristics curve. This curve, really. All of these curves are called as receiver operating characteristics and the area under them. So this has this much area, right? So if I consider this curve, this entire thing is the area under it. Or let's say here. So the area under this curve is this entire highlighted portion. This is the area under this ROC curve. This is the area under the curve. So that is called as the area under the curve. Are you all clear with this so far? Whatever I said, I'm going to get into details of this now. So now we want to first of all plot it. So plot it. It's simple and so this code is little bit you'll not like it. Even I don't like it, but I can give you one guarantee for sure that this is how we this is how it always looks, right? So I want to calculate and plot AUC ROC curve. So for that, you need to actually import this. After importing, you just like you have all of this, you have this as well. So I get ROC curve calculated and then I'm just let it come and then I'll explain you. See over here. I have got a model where the receiver operating characteristic is having a value 0.85. This is my ROC curve, right? So this is what we understand over here. So what do we basically figure out from this? So the idea over here is we are getting this value as 0.85. Now, with respect to our AUC, I can say because I got it as 0.85, it indicates that there is a 85% chance, very important. It indicates that there is a 85% chance that the model ranks the randomly chosen survivor higher than randomly chosen non-survivor and high true positive rate at low false positive rate, right? High true positive rate at low false positive rate. The model identifies most survivors early on, making FPs less. So general safe is both towards the top left, indicating a good separation in between the classes. So we can kind of conclude over here that our model discrimination is strong. It is able to distinguish survivors from non-survivors. Threshold tuning, I'm going to do it now. And precision recall curve to be more critical, but that I'm not going to do. Threshold tuning, I'll be doing it. I'll tell you what I mean by threshold tuning over here. So this is the one. Now let's look into the code. ROC curve says y test and logreg dot predict proba. Now what is that? See, this is interesting. So if I just say logistic regression dot predict on X test. So it will predict on all the values whether the passenger not survived, not survived. But if I say predict proba, if you recall the mathematics, you remember in mathematics when I was looking at um, weight, weight on the x-axis versus the obese or not obese on the y-axis while I was teaching you. I said that when we are actually hitting on the sigmoid curve, I was very clear over here that when we are actually hitting on the sigmoid curve, we are getting a probability. And if the probability was 50% or higher, we used to say that he is obese. Else we used to say he is not obese. So if you want to see that probability, you can use this. I'll tell you what I mean. See now, this is the probability that the current passenger of prediction, that is the first value in the test data set. This is the probability that he died. This is the probability that he survived. Total of this is 1. Total of this is 1. You can check it out. See now. 9 plus 3 is 1 only. Na? This is into 10 raised to minus 1, 10 raised to minus 2. So, this is a higher probability. So, the chances of death are higher. So, you need not look into both the columns. You can look into, let's say, this column. If this probability value, so listen to me very carefully. You are only looking at this column. So, in this column, if this is the probability of the passenger survived, because this is the probability of passenger died, this is the probability of passenger survived. If this value, if the value in this column is above 0.5, passenger survived. So, in between this, is the value above 0.5? Did not survive. Is the value above 0.5? No, did not survive. Is this above 0.5? No. Is this above 0.5? No. Is this value above 0.5? Tell me, is this value above 0.5? Because this is 9.61 into 10 raised to minus 1. That means it is 0.961. Right? Yes, it is 0.961. Therefore, it said 1. So this is how ideally, internally this happens. But this is what is shown to us. So, coming back, I am saying that logistic regression predict proba and select the first column. All the rows of the first column. Here I say from the prediction, all the rows of the column 1. There are 2 columns. I say choose the first column. First means not the 0th column, choose the first column, index number wise first. This ROC gives you 3 things as the output: FPR, TPR, and threshold. So, FPR is the false positive rate, TPR is the true positive rate, and the threshold is the threshold for the ROC curve. So here, I am getting AUC, which is the area under curve. This will help us to understand the model performance. And then I'm importing matplotlib, and I say I want to plot FPR, TPR, which we have already computed over here. Label it like this, which you see here. I want to plot a line which goes from 0, 0 to 1, 1. So it starts from 0, 0, 0, 0, and this is 1, 1. So dotted line goes from 0, 0 to 1, 1. That's what I said. 0, 0 to 1, 1. In red color, dashed. Label as this. And then these things are obvious. You know that very well. This is based on your experience, or we will choose one by default. No, you can choose any column. See, ultimately, you will still get the same results, Manu. If you are talking with respect to this, if the value is greater than 0.5, you predict passenger died. And if it is less than 0.5, you predict survived. So see, is this value greater than 0.5? Yes or no? No. If it is not greater than 0.5, passenger died. Is it not greater than 0.5? Passenger died. Not greater than 0.5, passenger died. Not greater than 0.5, passenger died. Is it greater than 0.5? You can see the passenger survived. So see, either this or this. So basically, if this is 30, this will be 70. If this is 70, this will be 30. If this is 20, it will be 80. If this is 75, this will be 25. So they are anyways opposites of each other. You refer this column or this column, that does not matter. Usually, most of them prefer the first column. Therefore, I also preferred it. But you can choose anyone. It does not matter at all. This is my column 0. This is my column 1. Okay. So now, when I say logreg.predict probability, so what am I going to see? See, first of all, if you find out the total of this will come to 1.0. If you find the total of this will come to 1.0, and so on and so forth. So the idea is I can actually choose one of this column. So it's like if I make it very simple, let's say if this value is 20, then this value would be 80. Now, you know what is it saying? If I just talk with respect to this, it says that this value says that there is a 80% chance that the passenger survived. This value says there is a 20% chance that the passenger did not survive. So now I can take any one of this column because it's like, let's say if I am the passenger in Titanic, the prediction says 20% chance that Darshan died, 80% chance that he survived. So model has to take a decision on the basis of any one of these values. So if I say there is a 80% chance that is survived, I am like, okay, if the probability of prediction is greater than equal to 0.5, I will say that survived, else I said died. So here in this case, because the column 1 says 80%, I survived. Or if I go as per this logic, then what will be the logic? If this value, as per this, let me use a pink ink over here. If I'm going as per this logic, then I say if the probability is greater than is equal to 0.5, I will predict that he died. Else I will predict that he survived. So essentially, see, I can go ahead with the yellow wala notation or I can go ahead with the pink wala notation, right? So that's exactly what we are doing. So I can refer either this column or this column. So in this case, I prefer to refer this with the yellow ink wala convention where I said that if it is greater than this, so which is this column? So for selecting this, we said if the result is saved into X, let's say, then I say I have to select colon. Colon means all the rows. And which column I want to select? First column. So I want to select all the rows of column number 1, which is this. So by default, internally, it looks for the threshold of 0.5. You can play around that threshold, which we'll see it later on. But yes, this is what it means. And on the basis of that only, it has created the entire table. Yes. So now we have got this. Now, you know what? Uh, I said, I said that if the probability in this column is greater than 0.5, he survived. If not, died. Who are you to decide this as 0.5, Darshan? It can be different also, now. Because what is the guarantee that 0.5 is a good value? It can be different also, and that is very much valid. It can be different, and it is very much valid. And let me tell you that here I was taking a decision on the basis of column number 1. So what I want to do is now I am planning to set the threshold. If I set it to 0.5, how do we get it? I say logistic regression dot predict probability. So I say if and only if the probability predicted is greater than 0.5, then you say the passenger survived. So wherever you see, as per this, false, 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 and this one survived. This is for 0.5. This is for 0.5. I want to add one more. If I say no, I want to go for threshold as 0.75. Then if I set the threshold as 0.75, so here I am saying that if and only if the probability of prediction is greater than 0.75, then the passenger survived. Then I get this as the result. Or let's say I am reducing it to 0.25. Okay, now see, I am not saying that whatever I am doing is correct. I don't know. I have to actually find out the right value of threshold. So what I can do is, see, I can straight away say np dot where. So wherever the value is greater than threshold, so I say threshold is equal to 0.5, and I say prediction with 0.5 threshold, and prediction with 0.5 threshold, prediction with 0.5 threshold over here, and printing predictions for different thresholds. Hmm. This variable name is not allowed, no? If you are setting the threshold at 0.5, you can see over here, these are the predictions. If you're setting it as 0.75, these are the. Now, see, which is the right value of threshold? We don't know. We don't know the right value of threshold. This is just what I am showing you. I don't know the right value of threshold. So, setting the threshold or shifting the threshold rather than 0.5, shifting the threshold may help us in increasing the result, because see, what is threshold? If you look into this figure, uh, this is threshold 50%, 0.5. If your model is more focused on minimization of false positives, then you would like to shift this threshold to the right hand side, because I want to minimize this. And if your model is focusing on minimization of false negatives, then you'll shift this threshold below this. Now we have to find out what is the right value of threshold. Is 0.5 the right value or not? Obviously, you don't have a figure like this. You will never be able to plot this figure. This is all in your mind. We have to find out. So what will I do? I know that the threshold can take any value between 0 to 1. So I am saying over here that let's try the model performance with different thresholds. So I am creating a list, and that list is going to be, I say, see, I want to try all these thresholds. Just now I showed you for 0.5, I showed you for 0.75, and showed you for 0.25. Now I say, let me try it for all the thresholds, right? So I'm dividing by 10. So if you want the 5 thresholds, you can divide it by 20, sorry. So 0.5, 0.05, so on and so forth. You can go this way as well. So let's say these are the various thresholds which I used to, or which I want to try. So how am I going to do? So obviously I am not going to create a model every time. I'm not going to create a model every time. This is the new thing that you are going to learn. So what am I doing? Pay attention over here very carefully. I'm going to create a cutoff data frame. So I say, 0.5 threshold. 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 So I say, 0. So I'm going to create a cutoff data frame where I am going to say that I want to zip together the y test and the logistic regression dot predict of this. Right. So right now it is just an empty data frame where I say columns will be actual, predicted probability, and predicted class. And first I will just show you this empty data frame. Right now there is nothing in this data frame. So because contents are not there, na? Contents are not there. We asked it for contents. Y test is there. And logistic regression or predict with this. And see, this is just an empty data frame right now. Right, empty data frame. I want to add in values over here. Right now it is just an empty data frame and I want the values to be added. So y test is already here. So I say, let me add it now. So I want to zip together y test will be there. Then y prediction is what I'm going to calculate at various thresholds. So y prediction test. And then I want to calculate the prediction as well. So np dot where, and I am going to, let's say, set it up for this. Let's show that. This is for all the values. So what I did is, if you're setting the threshold as 0.5, then the first passenger actually did not survive because the probability which is predicted in the first column is 0.03, which is less than 50%, because I set the threshold at 0.5, and therefore the model predicted 0. So this passenger is predicted as survived because the probability is above 0.5. So it is predicted as survived and he actually survived. And this is only with respect to this class, right? This is only with respect to this class, but I want to do it for all. So because I want to do it for all, what am I doing is I'll simplify this by populating this numbers. And then I say for threshold in numbers, I'm going to create a cutoff data frame where I will be having this mm, uh, we already had this, so I will only say cutoff data frame is equal to cutoff data frame dot I will take this predicted probability because this is the threshold deciding factor. So predicted probability, and on that I am going to map if the value is greater than this, then 1, else 0. And cutoff data frame of I, because we are not I, threshold. And then I'll just look at this. So you know what have we done? We have why was the threshold only up to 0.5? Oh, yeah. So I went from 0 to 0.5, 0.1, so on and so forth till 1. So if I am setting the threshold as 0, if I'm setting the threshold as 0, that means if the predicted probability is greater than 0, you say he survived, else you say he did not survive. So everything is survived, because if this value is greater than 0, he will say survived. Next time, let's say if I'm talking with respect to this column, left side I'm talking with respect to this. So if the value in this column is greater than 0.5, he survived, else he died. So check over here. This is the only value which is greater than 0.5. So that 0.5 column says he survived here. So I have tried it out at various thresholds. Now that I have tried it out at various thresholds, this is what I see. Now we have this thing. Now later on, I'm going to make it. No, this is little advanced stuff, but yes, from sklearn.metrics, I want to import confusion matrix. Now we know that true positive is nothing but in our confusion matrix. If you choose the index at 1, 1, that is nothing but true positive. In the same way, true negative is at index 0, 0, and FP is at 0, 1, and FN is at 1, 0. So I am directly creating a list of various thresholds. So it goes from 0, 0.0, 0 0.1, right up to 1.0. And I am going to create a cutoff data frame 1, which is going to be pd dot data frame. Inside this, the column will be not actual and all. The first will be the probability, and the second would be accuracy. The third will be sensitivity, and the fourth will be specificity. So this is what is created. And then I say for threshold in number, what I want to do over here is I want to calculate the confusion matrix for that particular threshold. So I say confusion matrix in between the cutoff data frame ka actual column and the cutoff data frame ka threshold. From that, I'll calculate the total, which is nothing but the sum of it. That is the sum of all the values, TPTN, FPFN. Similarly, this TPTN, right? So then we also calculate the accuracy as TP plus TN upon the total. You calculate specificity as TN upon TN plus FP. Similarly, sensitivity you calculate. And in the cutoff data frame 1, I would say cutoff data frame dot LOC of threshold, and you are going to append the threshold value, accuracy, sensitivity, specificity. And I need not even index it and all. Let me just plot it. So at various probability values, what is the accuracy? So yesterday, if you remember, this was the accuracy that we got because the default threshold value was 0.5. This was the accuracy that we got because the default threshold value was 0.5. But now I have the accuracies at various thresholds. Where do you see the accuracy to be maximum? That is the best value. But wait, you don't only look into that. Now, that's the most important concluding thing. I want to plot these all against the threshold. So I'm going to create a nice figure where I don't want to go ahead with this figure. It is just that it is recommending. My figure is something different. I just want to see what GitHub Copilot recommends. Oh, this is more better than what I was planning to get it for you. So now, if you see over here, where is it actually intersecting? So if I actually see, if I look at the point of intersection, which is here, can you tell me where is it intersecting the x-axis? Exact value as per you when you look into this figure. Exact value, whatever best comes to your mind. It's not 0.3, little higher is what I see. Anything 0.31, 32, 31, 31. Chalo, let's go with 0.32. Huh? More or less 0.32. So 0.32, right? Most of you are saying 0.32. I'll go ahead with 0.32. Little bit does not make a difference, but what we did essentially is we got this data frame. So I said what is plotted on the x-axis is the threshold going from 0 to 1. And on the y-axis, I have the metric value, which is y-axis is this. So basically here, when it is 0.0, accuracy is 0.8, this is 1 and this is 0. So when this is 0.0, accuracy is 0.8, which was the sensitivity is 0.8. Accuracy value is this, which is 0.4, and this is 0 for specificity. In this way, you plotted all these three and you joined it. And the best value that you see over here is what you all said is 0.32. So you know what it says? It says that Darshan, what you are trying out as 0.5, 0.5 ideally is not a good value. 0.5 is not a good value. 0.32 is a good value. This is what it is trying to say. 0.32 is a good value. And if that is the case, 0.32 is ideally a good value, then they say it's better you go ahead and create a model with that. So what will I do is now I say, since the best value of threshold is 0.32 as per the above graph, we will use that for our final prediction. So I say np dot where logistic regression dot predict probability of this threshold if it is greater than 0.321 else 0. I can actually show you that. So I can look into the accuracy score by giving y test and this. And on the test data, the accuracy is 0.79. And this is what we understand. So earlier, when you actually plotted accuracy, here, You see over here, we have got the testing accuracy as 0.81. So it was expected. In fact, it is expected. We might have done some small mistake. I don't know. But it is expected that you get this value above 0.81 because this is a more promising value of threshold. Now, why it didn't come, I don't know, but it should have come. It always comes. Maybe I did some small mistake while teaching, but yes. So basically, this is one possible way where we try to make the model output more better. This is one possible way where we try to make the model output more better. So you can rely on these all techniques as well. But this should be the second option. The first option should be changing the hyperparameters. 0.31, yeah, we can try it. That's not a problem. Let's say if I try with 0.31, 78. So I think let's say I try with 0.33, 79.88. 79.88. 79.32. So 0.33 looks good. So basically, see, we did so many things, right? I plotted such a big curve and all. If you don't want to get into all these things, I sometimes follow a very smarter approach as well. What I do is I just take this logic and put it in a for loop and I try out all the values of threshold. So if you don't want to get into all of these things, then what I can do is I can also suggest you that this is my style, you follow it or not. So I can say threshold is equal to whatever values I think, 0, 0.05, and so on going till the end. I try it out, right? And then I try out all the values of threshold, right? And I get the final predictions. Now this final predictions is what I get. Now I'll find out the accuracy with respect to each of this. So I will say, instead of putting it over here, mm, I can actually get this out. And I say threshold 0.5, not 0.5 actually, 0.0. Then we calculate it for 0.5, 10, 15. Quickly, if you don't want to get into all these things, you can do it this way. If you don't want to plot that sensitivity, specificity, and all these things, then you can try out this raw way also. It's just about copy pasting the code and changing the threshold value again and again. And I get it for all. It's your choice. I do it when no one is saying it. I actually do this thing also. And then I want to calculate accuracy for different threshold. So I am just calculating accuracies for all the thresholds and saving it. So if you don't want to do that, it's just about copy pasting the code again and again. Then I will like to print this. So now that you have all of this, you can choose where are you getting the highest accuracy. So here it says, see, this is the one. I think we went wrong above somewhere. So we were getting the highest accuracy at 0.5. At 0.5, it is highest. Then at 0.55, it is becoming a little small. At 0.45, also, it is becoming a little small. So I can see that in between 0.5 and 0.55, basically this range looks more promising. This range looks promising. So I will try to explore this even more. So 0.45 to 0.55 looks promising. See, we might have done some small mistake in the graph, but that's okay. So we say uh, 0.5 is usually the good value, but yes. Now, best values is 0.45 to 0.55. So 0.45 only, right? Yeah, 45, 0.46, 47, 48, 50, 51, 2, 3, 4, 5. This is the promising range that we have got. So now I'll do the same thing as above. Final predictions at 45, 46, 47, 48, 49, 50, 51, 52, 53, 54, 55, and then accuracies for each threshold 53, 54, 55, and I'm printing the accuracy for each. So it is just like, you're printing it again and again. That curve helps us to do that quickly. Your choice. You can do anything. Now you see over here where, at what threshold you are getting the best accuracy. At what threshold do you see the best accuracy? Tell me. 81.56 is the best, no? You're getting it at multiple values. Am I correct? 81.56 is the best, which we are getting at multiple values. Right, yes. So, some others as well. So we can say that the model is performing well on the test data set at threshold of 0.5. Yeah, I mean, multiple values, but I'll go ahead at 0.5. And that's what we are saying, that this is the final model and we are good with it. Yes, that's correct, Amitosh. You have to try it out at different values so that you are able to find out the perfect value. Usually 0.5 is the good in most of the cases. But in some cases, if you are really, before productionizing, it is always good to try out in case of logistic regression model, because by default, it will be assuming the probability value as 0.5. Right, yes. So this is how you should go ahead with the logistic regression. Now, after this, we created multiple models. That's fine. And I will go ahead with that only. I'm not changing it. What I want to do after this is this completes, and now I want to go ahead with logistic regression for multi-class classification problem. And how do I do it? Well, let us consider iris dataset. So the data set that I am considering is the iris data set of the Seaborn library. So importing Seaborn, and I am loading the iris data set, and let me show you the head, right? So logistic regression, we just understood that it is going to choose the probabilities. Now it's a very small case study, a very, very small case study, maybe 5 minutes, and we finish off this topic of logistic regression. So here, once we are loaded this data set, what is the very first thing that we end up doing? Because everything is good, we don't have to visualize everything. So I can say, let's divide the data into features, that is X, and target variable, that is Y. So X and Y is divided. Then I'm doing train test split. So 80-20 split done. I want to print the shape of each of it. 150 rows were there. I assume everyone knows what is the iris data set. It's a very small and easy data set. So I have just taken it so that I can finish off this thing in 5 minutes. So now we will scale the features. Now, what all are the features to be scaled? So this features to be scaled are this. From sklearn.preprocessing import standard scaler. Do that. Then I say, I want to do apply logistic regression for multiclass classification problem. This is the only new line that we have to learn. This is the only new line that we have to learn. Now, how do you actually get into interpretation of this? What I want to show you is logistic regression multi-class classification. So how does logistic regression work in the case of multi-class classification is what I want to show you. See, in binary classification, what were we doing? We were having independent and dependent variable, and there was a separation line created between class 1 and class 2. And whenever you get a new point, that new point was either plotted, sorry, it was plotted on this plot. If that new point comes out to be here, then we say it belongs to class 2. If that new point comes out to be on this side of the line, you say it belongs to the class 1. But here, in case of multi-class, it works with the OVR logic, one versus rest. If you remember, I said that when it comes to logistic regression, so logistic regression is in the industry popular for binary classification, not recommended for multi-class. If you do it for multi-class, let's say I am creating it for multi-class. Now, look at the problem. Because we are here to find out Setosa versus versicolor versus virginica, it creates three models. The first model is one versus rest, right? Setosa versus rest. Rest means non-Setosa. Then it creates one more model, versicolor versus rest. Then it creates one more model, Virginica versus rest. So here we understand over here that, see, imagine over here in this case, let's say this is Setosa. Let's say this is vertical. Oh, it took 4 classes. क्यों आ गए? Imagine this is not there. I should have taken the image carefully. I didn't see it only. So imagine this is not there. So let's say this is versicolor and Virginica. What it does, listen to me very, very carefully. It first creates rubbish, literally rubbish. I was actually looking for this image only. Maybe by mistakenly, I thought it is the same image. So consider this once again. Assume this to be Setosa, versicolor, Virginica. So what it does, as I told you, it creates 3 models. Model 1, which is Setosa versus rest, because I told you it works on the one versus rest approach. It creates one more model, versicolor versus rest. It creates one more model, Virginica versus rest. So what happens is, have a look at this now. The first thing what it does is, it will create a model, Setosa versus rest. So basically, this is going to be the line of separation. This is Setosa and this is non-Setosa. It creates a model. So obviously, just like we just saw predict proba. So it will predict whether it is Setosa or it is non-Setosa. Column 0 and column 1, just like we had survived or not survived. And it creates that model. In the same way, next it creates one more model, which is versicolor versus rest. So obviously, that's going to be the model over here, versicolor versus non-versicolor. One versus rest. Then it creates one more, which is Virginica versus non-Virginica, Virginica versus rest. And then when it is about prediction, let's say if you give it an unseen data point, then it will go to model 1 and it will say that, hey, what do you think? What is the probability of it being Setosa? So let's say it says that there is a 0.70 probability of it being Setosa. It goes to the next one. What do you think is the probability of it being versicolor? It says, let's say 0.10. What is the probability of it being Virginica? It says 0.20. Now, did you see the summation of all is 1? It will always be. And what is the max probability is 0.70. And what is that for? It is for the Setosa class. And therefore, the prediction is this particular data point is Setosa. So that's fine. But what is the problem? The problem is there are 3 models created, and therefore we can actually say it is computation heavy, because imagine instead of 3 you have 7 classes. Then it will be just not feasible in going for all of this. So that's the reason it is not preferred. But I'm showing you how to do that, but it is not preferred is what you all must make a note of. So are you all clear with the working? Implementation is very simple, but are you all clear with the working, how it works and why it is not preferred? There are many other algorithms other than logistic regression which can be used. Try to avoid logistic regression. No one uses it in the industry for multi-class classification. Yes, creating multiple binary classifiers. That's correct. So now I will apply. How do you apply? So it's very simple. You create a model, let's say logistic regression for multi-class, and you just have to set this parameter, right? See, this is very important. Solver is still okay. Random state. So here I say multi-class is equal to OVR, means O versus rest strategy. This is commonly used or compulsory for the multi-class classification problem. I ask it to fit, then I'll ask it to predict on this, and then I'll evaluate the accuracy and confusion metrics. So I'm printing the train and test accuracy, and I'm printing the confusion metrics. So you can see over here, 92% on train, 90% on test. And you see 10 setosas are perfectly identified as setosas. 8 for versicolor, 9 for this. And there are misclassification in versicolor, virginica, and virginica versicolor. So this is what we say. But wait a minute. What is the proof that it is generating multiple probabilities? I can show you. If I am considering X test all the rows of the no, not all the rows. If I'm considering the 0th record of this, mm, so I will have to say I lock. This is what I have got, and dot values. So basically, I'm considering this record minus 0.41, 1.0 on this record. And let's start over here, right? So this is important and easy as well. So here I want to tell you that K nearest neighbor is a lazy learning algorithm. Lazy means this is the only algorithm in machine learning where ideally no training happens. Yes. So no training happens at all. So we say, how does it predict then? Well, KNN is a type of supervised machine learning algorithm. It is very easy to implement. It's very easy to understand. It is lazy learning algorithm. Essentially, I'm trying to say that it does not have any specialized training phase. So every time you ask it to predict, it will say that, can you give me the complete training data? So obviously, till this point of time, we have studied linear and logistic. Once they fit, we know that they were using nothing but the equation of the line for predicting. They don't need the training data, but KNN says I need the training data. So it actually does the inference based on training data. So therefore, it is not helpful when the data is very large to go ahead with KNN. Now that's the interesting part.
it's a non-parametric learning algorithm. So it will not assume anything about the data, rather it will use the entire data. Like for example, if you see there are two types of algorithms. Parametric, like linear regression, logistic regression, neo bias, support vector, etc. And non-parametric like k nearest neighbor, decision tree, random forest, etc. Now see what is parametric. How does linear regression predict y is equal to mx plus c? How does logistic regression predict 1 upon 1 plus e raised to minus y, which is nothing but 1 upon 1 plus e raised to minus of mx plus c? So it is simply when you have the equation y is equal to 0.5x plus c, you are just substituting the value of x and you get the value of y. So it's just some parameter substitution and getting the answer. That's why we call these algorithms as parametric algorithms. So over here, if we get into this is again important question for the interview as well. This is not there in your syllabus, but they ask it, what is the difference between parametric and non-parametric algorithms? So parametric assumes specific form, like linear regression assumes that the data is linear. Non-parametric will not assume any specific form. So it is little flexible. For simpler models, parametrics are good. For complex models, you go for non-parametric. Parametric are generally fast to train. Non-parametric are slower to train. Parametric may perform poorly with complex data. Here, they are designed for big data and complex data. There is a low risk of overfitting. Here, the risk of overfitting is very high, especially decision tree, random forest. They are very high at risk of overfitting. And now we get into the KNN. Let me ask you, are you all aware of Euclidean distance? Did we learn that earlier? Euclidean distance? No? No worries. It's very easy. Very easy. So, this Euclidean distance, Manhattan distance actually came from Manhattan. So, Manhattan or New York, a very popular city in the world, located in the USA. This entire city is something like this. If you see carefully, uh, I had been to this city somewhere in 2019. So entire city is divided into blocks as you see. So, if you start walking from here till here, these are roads. So it takes around 7 minutes to 8 minutes to walk this much. So it's that much lengthy. And here it takes around 2 to 3 minutes. So you can imagine how much big this block is. And inside this block, there are at least 8 to 15 big buildings, tall. That's how the city of New York is. So I am sure everyone knows it, but still.
Ladies and gentlemen, welcome to New York City. Explore
So
the
this is how it is, right? So it's all divided into blocks. You see these roads.
sit back, relax, and soak in the mesmerizing aerial views of this iconic metropolis. Ladies and gentlemen, welcome to New York.
New York City is the greatest city in the world. Everyone wants to be here.
This is how every block is. So the left side is a one block, to the right side is another block. In between, we have the roads. So
Give yourself 28.
what I wanted to tell you is, you saw over here that how much you need to understand to how much to walk everywhere. So I just took one example over here for reference to make you understand how much it takes to walk from here to here. So obviously, if you say that if I want to go for from Dim's Palace, and let's say I am at the Park Avenue, so there is no way I don't have a helicopter. This direct distance is called as the Euclidean distance. But how will I go? I will have to follow the road. Maybe I go like this across the road, and maybe from here I reach that. So that's will be the route I take. Or maybe I come here, 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 and then I go here, right? There are n number of ways. This is called as darshan, walking along the road, right? So this road distance is what is called as Euclidean distance. Sorry, this road distance is what is called as the Manhattan distance. And this direct distance is what is called as the Euclidean distance. So this came from here, A to B direct distance, and this is the Manhattan distance, or this is the Manhattan distance. How do you compute it? Well, other than that, there is one more distance, which is called as Minkowski. It is mainly used by the planes to figure out the right distance. So Minkowski is basically a generalized formula. In the Minkowski formula, if you're substituting P is equal to 1, it becomes Manhattan. If the value of P is 2, it is Euclidean. And if the value of P is more than that, it is Minkowski. So this is Euclidean distance. If I want to find out the distance in between the points A and B, obviously I have the coordinates of it. So square root of x2 minus x1 the whole square plus y2 minus y1 the whole square. So 9 minus 3 whole square plus 7 minus 2 whole square in root gives me the Euclidean distance. Or even if I do the opposite, instead of 9 minus 3, I say 3 minus 9 whole square plus 2 minus 7 whole square in root still gives me the same value, you can see. So it does not matter the order, right? Whatever are the order of the points, it does not matter. This is what is your Euclidean distance. And Manhattan distance is the direct distance. this. So if I say what is the Manhattan distance in this, so I will have to go from here to here and then here to here. So basically I need to find out this distance and I need to find out this distance. The total of this and this is the Manhattan distance. And this distance is Euclidean, which we just understood. So now let us get into the understanding of the mathematics, which is very, very easy. Before that, let me ask you all, have you understood the Euclidean distance and the Manhattan distance? We need Euclidean distance right now. This algorithm is very, 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 very easy. Yes, it's so easy. So now if you see, I have a data where on the x-axis I have plotted income and on the y-axis I have plotted the loan amount. Income versus loan amount. So this data is like, this is independent variable 1, this is independent variable 2, and that's my dependent variable. So a person with income $5,000 and a loan of $10,000 is a non-defaulter. This is given to me. It's a supervised learning problem. So this person is a non-defaulter. So non-defaulter I'm marking by blue. A person with income 10 and loan of 15 is also a non-defaulter. marked over here just in the way income 85 and let's say loan amount of 70 is a loan defaulter. So in this way, when I plot this, this is how the data is. You see the blue and the red points over here as well. KNN does exactly the same thing. It plots the data. Then now let's say after plotting this data, that is exactly the training part where there is no training. So let's say after the plotting this data, you say I have a new point X and I want to know whether it is defaulter or not. So let's say I have a point 45 and 50. So where is 45 and 50 going to be? See, 45 will be here and 50 would be here. So the thing is, I'm trying to figure out whether this data point is a defaulter or not. So what it does basically to find out whether this data point is a defaulter or not, it finds out the Euclidean distance between this and this, 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 between this, between this, between this. And then it says, okay, Darshan, that is done. Now you tell me the value of K. So let's say if I say that, hey, the value of K is 3. From all of these distances which are computed, it will find out the smallest 3 distances. So let's say these are the smallest 3 distances. I have put it in circle. Now out of these 3, how many belong to loan defaulter and how many belong to defaulter? Non-defaulters are 1 and defaulters are 2. So we say, boss, this is going to go into the red wala class. So it is going to get into the loan defaulter class. Finish, 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 finish. We are done. It can't be more easy. So ideally, there is no training happening. It is just distance comparison and concluding every time. Have you understood? Dare you say you don't understand? There is nothing over here. It's so simple and so straightforward. Find the distance and see. The only challenge is how do you choose the right value of K? Other than that, it's all good. In terms of effectiveness, K-means versus logistics, which is better? We don't know. We don't know. It depends on the data. If there was a clear evidence that logistic regression is better, then K-means would have never existed as an algorithm, KNN. They would have simply removed this algorithm implementation. So sometimes KNN works good. Sometimes logistic regression works good. So you need to try out both. It hardly takes any time. Anyways, you don't need the mathematic every time. You just need to import, create an object, fit, and predict. So people try out both. Right? Yes. Let me ask you. Yes, one important thing, right? You should always choose the value of K as odd number. If you choose even and you find 2 from blue and 2 from red, then don't keep on crying. The machine can predict anything in that case because 50% probability. So whatever it predicts, it's one and the same. Therefore, always choose K as odd. That's it. If you have understood, I think we are good to get into the implementation. Please confirm if this is understood to everyone. Implementing this. So first thing that we need to do is we do all the necessary imports. I am taking the iris dataset. So I'm loading the iris dataset and I'm looking at the head of it. We just did that for logistic regression. We have got the accuracy and all other things. It's available here only, right? Here only we got the accuracy. 92 and 90%. Now, I loaded the iris dataset. The next thing is you divide the data into X and Y. So I do that. After dividing, this is what is my X and this is what is my Y. Then I'm doing the 75-25 split. So 150 rows are there, 112 and 38 is what I understand. After that, feature names is equal to x dot column. So I'm scaling it. So I say, create an object and scale it. You know that well. If you want, you can take a moment to understand. The hyperparameters of the k nearest neighbor, because now the modeling starts. So there are so many hyperparameters which the k nearest neighbor has. First, I will go ahead with the basic and then I'll come over here. So what I said is, see, this is where it exists. From sklearn.neighbors, import the k neighbors classifier. It has number of neighbors, weights, algorithm, leaf size. P is 2 means Euclidean, 1 means Manhattan, metric is Minkowski, and this is okay. Right now, I'm just saying that, hey, in our example where I told you the mathematics, I assume the value of k as 3. Here I'm assuming as 5 because I have more points. Let's say 5 is a good number over here. So I do that. And then I say KNN, go and fit over it. After predicting KNN, go and predict on X train, go and predict on X test. And then I'm asking it to print the accuracy on train and test. And you can see I am getting 96% accuracy and 97 over there. So little fishy, maybe try changing the random state. But before that, let us understand the parameters. You can see over here, the first parameter as we have is the number of neighbors. We know what it is. In the industry, for solving any problem, values like 3, 5, 7, 11 are the very common values which people try out. Weights by default. They talk about how the influence of neighbor is calculated. Uniform means the neighbors are given equal weight, and distance means the neighbors which are closer are given higher weight as compared to the far away ones. So both are often tested. Distance sometimes gives better accuracy. Distance. Algorithm. Now that's another part of mathematics. How to compute the nearest neighbors. Auto is the best one, as they say. But you have other algorithms like ball tree, KD tree, brute. Auto is default and works well. For large data sets, they say KD tree or ball tree can be good. Leaf size affects the speed of the tree-based neighbors. So if you are using ball tree or KD tree, then so usually 20 to 50, default is 30, can be used. I don't touch it ever. P is equal to 1, Manhattan, P is equal to 2, Euclidean. Metric, Minkowski, Euclidean, Manhattan. We know that metric parameters, none. Standard metrics usually suffice. N jobs, we will not talk about it, but it is about how extensively you want your core processor to be used. So -1 means it will be using all the cores. This applies more strongly when you are doing decision tree algorithm. So right now they are not very important and we will not get into it. So I come over here and this is the one. I can actually show you Y test versus Y predicted test. I zipped together both of this and I'm converting to list. So the first one is Virginica. Actually, I predicted as Virgilica. Versicolor, predicted as versicolor, and so on. Then I say, you know what am I saying? See, I got this. I am saying that can you tell me, listen to this very, very carefully. I'm trying to calculate misclassification. Can you tell me where my prediction is not equal to actual? So where my prediction is not equal to actual. So wherever you get true, there my prediction is not equal to actual, like the last record. So tell me how many times was the prediction not equal to actual? That is the misclassification count, and it was only one time. Okay, that is the total. I say on an average instead of sum. I said mean. So 2% of the times prediction is not same as actual. And if I actually say 1 minus this, say 97.36% is the accuracy on the test data set. Here you got how much? 90 only. On the test, you got 90 on logistic. And now we have got 97.36, which is far, far better. To show you the confusion matrix. Now this is the confusion matrix. This is the only misclassification. But to understand it better, what is actual, what is predicted, I just printed it in a stylish way. If you see it now, predicted, true. See, this is the one where we understand the versicolor is predicted as Virginica once. Versicolor predicted as Virginica once. Okay, so I just printed it in a little bit stylish way. I got the confusion matrix. I converted it to a data frame with the index having the classes, columns having the classes, and then we just plotted a heat map with annotation values. And this is what we have. So from this confusion matrix, we know that we can easily calculate the precision, recall, and all other things. So precision is having this formula, which means out of all the predictions for a particular class, how many were actually correct. And from this, uh, No, I guess this was for a random example. My bad. Hmm. Okay, but we know this. Then, but now the most important thing. Now the most important thing is I did this whole thing, and I'm sure you also understood. But the $1 million question is the number of neighbors equal to 5, which you assumed correct? Because here we said we are getting accuracy of 97%, but is that really correct? So what am I actually planning to do is now I am going to create a plot that will look something like this. Have a look at this plot. I am planning to not try only the value of k as 5, but I am planning to try many k values, right from 1 till 40. I am saying I want to try out all the k values, k equal to 1, 2, 3, 4, 5, 6, so on and so forth. I say I want to try out all the k values. And here in this, on the y-axis, I will find out the mean error. Now, what is this mean error? Come on, you know it. I just showed you what is the mean error over here. On an average, tell me how many times the actual is not equal to predicted. So, let's actually do it now. So, see over here, how am I doing it? I'm creating an empty list. You can call this by any name. Empty list where I'm going to show or save all the mean errors. So I say I want to go from 1 to 30 line. Every time, let's say when k value is 1, I'm creating an instance with the number of neighbors as 1. Fit on it, predict on it, and after prediction, I want to find out how many times is the actual is not equal to the predicted or predicted not equal to actual. And that average value, we want it to be appended to this list. Error dot append. These are all explanation, which you already know. So basically, this is the logic which will keep on executing for all the values of k. And then I'm plotting on the x-axis numbers from 1 to 39. On the y-axis, I'm plotting these received 39 errors in red color, line style dashed, marker style. Oh, readable. So we can clearly see over here. This is what you see. What have we plotted? We have plotted the various values of k and the wheel error. Then you also see I'm plotting a horizontal line for the average of all. So basically this value, this value, this, all these values ka average comes out to be this. I plotted that. That's just for reference. Now, when I look at this, do you see that the value of k remains lowest in between 3 to 18? Important thing. Very, very important thing. So I say interpretation. There is an initial drop in the error at k is equal to 1. It is directly going. As k increases to 3, the error sharply reduces to 0.025. Then flat low error region. K equal to 3 to 17. It is considered low. This suggests that the model performs well in this range. This flat section indicates stability, meaning the model predictions are not overly sensitive to the changes. Then after that, we see there is an increase in the error beyond k is equal to 17. You can see that zoom. So obviously this is not the right value. And later on, it's very, very high. It's going up and up and up only. This is the place where it is stable. K equal to 3 to 18. So I say k is equal to 3 to 18 or 3 to 15 gives the lowest and the most stable range. A commonly chosen value of k is k is equal to 5 or 7 could be ideal starting point. Always choose odd values. Avoid too small, avoid too large values. So in this case, I say that the right value of k is 5 or 7. Now,